Hello, 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 hello. Hey guys, are you all able to hear my voice? Or hello? Is the voice audible? Hey guys, are you all able to hear my voice? Hey guys, what's up? This is Jonathan Matthew, and you can all call me as John sir. That's what everybody calls me. And most of you all will not be familiar with me. Who am I? Okay, who am I? And what I'll be teaching you all. So what are we going to do? First of all, yeah, that's my name. My name is Jonathan, and you can all call me as John sir. Okay, and I'll be teaching physics along with Yavar sir for this game of NEET 3.0. And this is a very interesting topic that we're going to start with, because modern physics, yes, low voice, is the voice low, is the voice low? Yeah, I'll tell everything, है ना, I'll tell everything. Okay, I'll tell everything for this game of NEET 3.0. And this is a very what about the voice? Can you just confirm me about the voice? Okay, can you just confirm me about the voice? Yes, can you just confirm me about the voice? Is it audible? Is it audible? Clear, it's clear. Voice is low, voice is low. Okay. Clear. Okay, low sir. Okay, I'll just increase it. Okay, I'll just increase it. Okay. I'll just increase it. Okay, just a second, just a second guys. Yes, just a second, just a second. Okay. Yeah, till then let's talk. I'll just adjust the volume over here, people. Yeah, just a second. Okay, just the second. Okay, just a second. Hello. Hey guys, is this fine? Is this fine, sir? Is this fine? Is this fine, people? Is this fine? Is this fine? Is this fine? Is this fine, people? Yes. Hello. Hey guys, is this fine? Is this fine? Okay. So again, so yes, my name is Jonathan. Yeah, as I said, and obviously I am from Kerala actually. Yes, so Ellarum Sugamano, uh, and okay, a bit more loud. Then I'll have to call my tech people. Okay, increase. Just people. Just a second. Okay. Yes, so we would be covering, yeah, till then the tech team arrives. I would just talk with you. Okay, Ellarum Sugamano. I am from Kerala, but yeah, I know a little bit of Hindi and everything. Yes, Sugamanam. Okay, chalo. So we would be covering modern physics today. So modern physics consists of 3 chapters. भाई voice low है. अश्विनी मैम को एक बार बुला ले please. या किसी कोई tech team को किसी को तो बुला ले please. मतलब हाँ. Okay. Yes. So again, so complete modern physics, we would be completing dual nature of radiation and matter, atoms and nuclei. These are the 3 chapters that we will be focusing, we would be covering, and I would be covering from basics till advanced. Okay. And obviously this lecture can also be watched by the students who are preparing for JEE as well. Okay, so that is the type of content that I'm going to that I'm going to provide. Yes, we are not going to extend it till 3 or 4 a.m. people. Don't worry about it. I would be keeping it in a very concise manner, but I would be covering everything about it. Okay, I would be covering everything about it. So this is the flow that we are going to do. First, we'll be starting off with dual nature of radiation and matter. So the main important part over here is photoelectric effect that we have to study. Then we will be studying the atoms part, and then we will be studying the nuclei part as well. So all these three topics are very important. Okay, yes, very important, because just a second people. Okay, because as you can see from dual nature, हाँ भाई किसी को बुला ले यार क्योंकि वॉइस लो है पूरा माइक का नहीं बिकॉज नहीं माइक इन द सेंस कि आउटपुट थोड़ा कम आ रहा है करके वो एक सेटिंग करता है वो मुझे नहीं मालूम उसके लिए किसी किधर बैठते हो लोग मुझे नहीं कॉल कर शिवा सर को कॉल कर या अश्विनी मैम को ये वाले जो लंबे हैं वो चलेगा क्या वो वाले नहीं नो शिवा सर वो वाले नो तो बुला जल्दी. Okay, so yeah, I would be providing. So dual nature of radiation and matter, 2 questions come, that is just 4%, atoms and nuclei 5%, and then semiconductors again, which is again part of modern physics, 6%. So just modern physics along with semiconductors, it is just close to 15% of your syllabus. Okay, it is close to 15% of your syllabus. Okay, so that is the reason it is very important that we should study, and it is a very easy chapter as well. And this is the Telegram channel that you can join. You can just scan over here and you can join the Telegram channel. I'll upload the notes over here, so any of you all who want to access the notes can join the Telegram channel, and I will upload the notes here as well. Okay, so this is something which you can scan. Next, moving on, I also teach in NEET Alchemy as well. Okay, this is my primary channel, NEET Alchemy by Unacademy. If you can notice, I'm actually running a series, all NEET aims and AIPMT PYQs from 1988 to 2025. So chapter wise PYQs, I'm solving it over here. So if anybody wants to look out, you can come here and join. Okay, people? Yes. Okay. Cool. Okay, people. So can I get some fire emojis in the chat? And then we can start off with dual nature of radiation and matter. Okay, and then we can start off with dual nature of radiation and matter. Okay, can I get some fire emojis? Can I get some fire emojis in the chat, people? Yes, can I get some fire emojis? Cool. And from where are you all joining? In which part of the country you are watching this lecture? No semiconductors in this class. We will only be covering dual nature, atoms and nuclei. Okay. Cool. No, I'm not from Kashmir. I'm from Kerala. Yes. Okay, cool. Andhra Pradesh, Kashmir. Okay, let's go. Haryana, UP, Andhra Pradesh, Karnataka, Andhra Pradesh, Maharashtra, Tamil Nadu, Manipur, Imphal. Okay, very good. Tamil Nadu. Very good. And you have to smash the like button, guys. Okay, you have to smash the like button. Okay, and then we can start. Okay, so with your permission, people, we are going to start with this complete modern physics game of NEET 3.0. Here we go. Okay, here we go. Dual nature of radiation and matter. Okay, so first of all, let's understand what the chapter really means. Okay, so we're going to understand the dual nature of what exactly? We are going to understand the dual nature of radiation and matter. Now people, you have to understand that this radiation over here, this actually means light. Okay, so the radiation word over here, it actually denotes light. So the dual nature of light and also matter, we are going to study in this particular chapter. Okay, we're going to study in this particular chapter, and let's move ahead. This is my Telegram channel. You can all join. Okay, so this is going to be the flow of the chapter that we are gonna follow. First, we are going to study quantum theory. Then we are going to study the linear momentum and the effective mass of the photon. Then we will move on to Rutherford's gold experiment, a very important experiment, radiation force and pressure, photoelectric effect, matter waves or de Broglie, Davisson Germer experiment, Bohr quantization condition, and a lot of J NEET aims PYQs. Okay, people. So I'm going to also practice a lot of questions with you all. Okay, I'm going to practice a lot of questions with you all. Okay, people? Yes. Just let me just adjust your comment section over here, people, so that I will be able to see your comments. Okay. Okay. Chalo, let's start. Let's start. Okay. So first we are going to study about the quantum theory or energy of a photon. Now before we move on, what exactly is a photon? What exactly is a photon? So photon is basically called as an energy packet, or it can also be called as a quanta. Okay, it can also be called as a quanta. So photons or quanta are called as energy packets. Okay, they are energy packets. So basically, if I have a source over here and if it is radiating light, okay, if it is radiating light, so these photons are responsible for basically making the energy travel, and these photons are called as energy packets. Now in this diagram, okay, I'll be denoting photon as something like this. Okay, I'll be denoting photon something like this. So this is one packet of energy which is basically making the energy travel. Okay, understood? This is very easy. Okay, this is very easy. Okay, low voice, I will be rectifying it, don't worry. Okay, I will be rectifying it. Okay, don't worry. Just a second. Okay, just a second. Okay, yes. So energy radiated from a source propagates microscopically in the form of packets, and these are called as photons or quanta or energy packets. Okay, now what is this? This is not a bacteria, this is not a cell. This is actually the very recent image of scientists, recent image of a photon which scientists rendered. Okay, so this is not part of a syllabus, but just for curiosity, this is actually an image of a photon. Okay, this is actually an image of a photon. Cool. This is an image of a photon, a very recent image. So that is exactly what a photon looks like. Okay. Okay. Chalo. Let's move ahead. Now this is a very interesting thing that we are going to look about. Now, as the chapter name suggests you, we are going to study the dual nature of radiation and matter. Okay. Now this is where things are going to get interesting. Okay. This is where भाई low output आ रहा है थोड़ा बहुत. मतलब आवाज आ रहा है but low output आ रहा है. एक बार अश्विनी मैम नहीं तो शिवा सर को देख ले. हाँ. Okay, so what is basically the energy of the photon? So energy of one photon is given as E is equal to h mu. Okay, now this is basically the energy of one photon. Now I'll just write it over here that this is energy of one photon. This is energy of one photon. Okay, now people, now what is exactly h mu and everything over here? Now I want to derive this formula more over here. Now people, you have already studied that E is the energy, h is the Planck's constant, and mu is the frequency of the light. Now I already know one more relation. What is the relation? That frequency is basically c divided by lambda. Frequency is basically c divided by lambda. Okay, now this formula right over here, is actually a wave formula. Now if you understand a little bit wave physics and everything, you understand this formula comes under the wave physics actually. From where this formula comes? From the wave physics. That is mu is equal to c by lambda. Now over here, I'm going to substitute this mu over here. Now when I substitute over here, that is E is equal to, this becomes E is equal to hc by lambda. This is also one more formula that I get for the energy of one photon. Now people, I have already integrated two different criteria over here into the same formula. Now this is a particle formula, that is because photon is a particle, and this is basically the energy of the photon. But I've also used the formula of wave formula inside this, and I've integrated it. So I've already integrated the dual nature of radiation over here. Yes, you have to write notes. Okay, you have to write notes. Okay people, okay. You have to write notes. Yes people. Okay, so I've already integrated it over here. Okay, I've already integrated it over here. Okay, now people, let's understand. So let's write it over here. H is basically your Planck's constant. H is basically your Planck's constant, and everybody knows the value. The value is 6.6 into 10 ki power minus 34 kg meter per second. Kg meter per second. Yes, people. Now, how did I derive this? This is very easy. This is very easy. Okay, this is very easy that we can understand this. So, what is energy? So, if I want to understand how did I derive this quantity, it is very easy, people. That I know that Planck's constant will be E divided by the frequency. E is basically work. Yeah, energy. The unit is basically work itself. That is force into displacement. Force is basically mass into acceleration into displacement, and this is frequency. That is, what is frequency? Frequency is basically 1 by t. Okay, that is basically 1 by t. So this is again this becomes, yeah, this is 1 by t itself. So this is kg, this is kg, acceleration is meter per second square, and displacement is again meter, and this becomes a time period. This goes ahead. Okay, so this is how I derive it. Okay, this is how I derive it. Okay, moving ahead. This is Planck's constant over here. My voice is very low. Am I? Hey guys, and this becomes a time period. This goes. Is the voice low, people? Is the voice low? Yes, yes, it is enough. Just a second, people. Let me adjust the volume over here. Then voice is perfect. Okay, till the tech team arrives. Okay, till the tech team arrives, just manage with this. Okay, I'll try to speak loudly, and then you can. Okay, okay, okay. So this is the Planck's constant. Then what is mu over here? Mu is basically the frequency over here. Mu is basically the frequency of the light over here. Frequency of the light. Very good. What is then what is c? C is basically the speed of light. C is basically the speed of light. Okay, very good. And its value we already know that it is 3 into 10 ki power 8 meter per second. Very good. Then what is lambda? Lambda is basically the wavelength of light. Wavelength of light. Okay, people, clear? Yes. Okay, I will be slow. Okay, I will be slow. Okay, people. Okay, so again this is energy of photon. Then I've used mu is equal to c by lambda over here. So I got E is equal to hc by lambda, and h is your Planck's constant, mu is your frequency, c is your speed of light, and lambda is basically your wavelength of light. Clear? Okay, now people, now you have to understand that h is in the SI unit, c also is in SI unit, lambda also in SI unit. So overall you will get the SI unit of energy as in joules. Okay, you will get the SI unit as in joules. Okay, so the SI unit is in joules. So that is what you will get over here. Okay, people, but obviously you are preparing for NEET, you are preparing for JEE, you are preparing for various competitive exams. So you have to increase your calculation speed over here. You have to increase your calculation speed over here, and that is where some John Sir's tricks comes over here. Okay, some tricks comes over here. Tricks for your calculations. Tricks for your calculations. The first formula that you have to keep in mind. Energy is basically equal to 12400 divided by lambda. Now you have to keep in mind that this lambda should be in angstrom over here. And the total and the unit of energy that you will get is electron volt. An electron volt. Okay, people. Okay, people. So this is basically, you can take a screenshot right now, people. You can take a screenshot right now. Okay. Just a second, people. Just a second. Till then you can write. Okay. Okay, people. So, okay. So E is equal to 12400 divided by lambda, and lambda should be in angstrom, and the total unit that you will get is in electron volt. Okay. One more formula that you can use over here. Is basically E is equal to 1240 divided by lambda, and this time lambda is in nanometers, and again you will get it in electron volt. Okay. Yes, and again you will get it in electron volt. Clear? Yes sir, it is proper clear. Now some people, they don't understand what angstrom is, and they don't understand what is nanometer, so I'll just write it over here. So 1 angstrom is also a unit of length, and it corresponds to 10 ki power minus 10 meter, and 1 nanometer, as the name suggests, nano, it is 10 ki power minus 9 meter. This is one of the conversions that you should know to ace this chapter. Okay? Okay people? Yes. Okay, now this is very much clear over here. This is very much clear over here. Okay, clear? Okay, very good. So these are the formulas that you should use if you want to increase the calculation speed over here. Otherwise, you can use this formula, and then obviously you have to calculate more, Okay people, can we move ahead? Yes, we can move ahead. Next. Now let's understand the linear momentum and effective mass of photon. Okay, let us understand the linear momentum and effective mass of photon. People, look over here. Momentum P is basically equal to h by lambda. Okay, we do not have to go into the derivation of it, you just have to understand. Okay, so momentum of a photon is basically denoted as h by lambda. Now you will be like, nah sir, it does not look good. Please make it a little good. Okay, so I'll make it a little good. Okay, what I do, I multiply by c and I divide by c over here. Now I already know what is hc by lambda. Oh my god, it is e by c over here. It is E by C over here. So the momentum of a photon can also be written as the energy of the photon divided by the speed of light. Speed of light. Now I'll come back to this. You just write it and keep it. I'll come back to this. Okay, people? Okay. Now, what is the effective mass of photon? What do I mean by effective mass of a photon? Now, first of all, you have to understand the rest mass, okay? The rest mass, this m naught corresponds to the rest mass. Rest mass of the photon is considered to be 0. Now, and I'll explain you what exactly is the rest mass. So, imagine that this is a photon, okay? Okay, now let's understand. Okay, this is the ball. If this is traveling with 2 meter per second velocity, I also have to carry a weighing machine in 2 meter per second velocity to measure its weight. Yes or no? I'll explain it again. That if this ball is traveling in 2 meter per second velocity, okay, in order for me to measure its weight, I also have to move the weighing scale in 2 meter per second velocity. Yes or no? Yes, this series is enough. Okay, this series is enough. Okay. Okay, so that is basically the rest mass. This is known as the rest mass. So if this ball is traveling with 2 meter per second velocity, the weighing scale also should travel with 2 meter per second velocity, and that is how I'm able to measure the mass of this ball. Now, when it comes to the rest mass of a photon, when it comes with the rest mass of the photon, now I have to understand the photon travels with the speed of light. Now we know that any object in this world cannot travel with the speed of light. So if this photon is traveling with the speed of light, I also have to move this weighing scale with the speed of light, and that is not possible. And that is the reason I'm telling the rest mass of a photon is 0. It is not defined. Are you all able to understand that what exactly is rest mass over here? Yes, we have understood what exactly is rest mass over here. But the effective mass of a photon, this is the effective mass. I'll write it over here. This is effective mass. Effective mass of a photon is basically E divided by C square. Okay, yeah, I'll tell the concept again. Don't worry. Okay, I'll tell the concept again. Now, I'm going to substitute the value of E over here. So this becomes hc by lambda, and this becomes c square. This c and this c gets cancelled. So I get something h lambda by c. H divided by lambda c. This is what I'm getting. Now people, this is m, that is effective mass of the photon. H is a constant. C is a constant. Now, can I basically say the effective mass of a photon is inversely related to the wavelength? Can I basically say this? Yes or no? Can I basically say this yes or no? Okay, because H is a constant, C is a constant, so I can basically say the effective mass of a photon is inversely related to the wavelength. That means greater the wavelength, less the mass. So smaller the wavelength, more the mass. That is the reason. That is the reason. If I understand Vibgyor over here, okay. So this is basically the visible spectrum, Vibgyor, है ना? Vibgyor. I know that lambda increases in this direction. Yes or no? That lambda increases in this direction. So if lambda is increasing in this direction, red will have the maximum wavelength. Red will have the maximum wavelength, and if red has the maximum wavelength, it will have the smallest mass. The photon of the red color will have the smallest effective mass, and violet having the least wavelength, it will have the most mass, the maximum effective mass. So that is why I am written. So mass of violet light photon is greater than mass of red light photon, and rest mass of a photon is always 0. Are you all able to understand this, people? So output is low, sir, for some reason. No, this is YouTube. Okay, just a second. The technical team has come. Okay, just a second, people. Okay. Yeah, obvious. Okay, just a second, people. We are just seeing the tech over here. Okay, and then we'll rectify it. Okay. Yes. Okay. Okay, so we have all understood that Vibgyor over here, as the lambda increases, red has the most amount of lambda over here, and that is the reason the mass will be the least. And violet over here has the least amount of lambda, and that is the reason the mass will be highest over here. Okay, that is something that we know. People, is the volume now okay? People, is the volume now okay? Can you all confirm? Sir, एक minute, comments. Is the volume okay now? Is the volume okay now? Yes, I will explain it again. Yes. Okay. Yes. Okay. Chalo. Now I'll explain the rest mass again. Okay. I'll explain the concept of rest mass again. Okay. What is rest mass? For example, if this ball is traveling with 2 meters per second velocity, I also have to have a weighing scale traveling in 2 meter per second velocity to weigh it. Yes, obviously. And when I weigh it, this is basically called as the rest mass of the ball. Now, when it comes to photon travels with the speed of light. Oh my god. And we know, according to Einstein's relativity theory, that no body in this universe can travel in the speed of light other than light itself. We know that. So if I want to measure the mass of this photon, I'll have to move this weighing scale in the speed of light itself, which is not possible. Okay, black screen. Just a second. Yeah. I'm back. Yeah, I'm back. I'm back. I don't know what is happening. Okay, I don't know what is happening. Yes, I'm back. I am back. Am I back? Am I back? Yes, people. Am I back? Yeah. Okay. Okay. Yeah. So did you all understand the concept? So the photon is traveling at the speed of light. So I'll have to move the weighing scale with the speed of light, which is not possible itself. And that is the reason I'm saying that the rest mass of the photon is 0 over here. Okay, people. Yes, Adipoli, let's go. Okay. So over here, we are able to understand, this is basically the spectrum that we have. We are able to understand that this is violet light. This has lambda minimum. And this has lambda maximum. And due to the lambda being maximum, the mass is minimum over here. And the mass is maximum over here. This is something that we are able to understand. Okay, people. Yes. Okay. Can we move ahead? Can we move ahead, people? Now, coming back to the momentum of photon over here. Now, people, I'll try to explain this also. Okay, I'll try to explain this also. Okay. Now, the total energy of a moving particle, now this is not there in your syllabus, but I just need you to feel this actually. Okay, the total energy of a particle is actually square root of m naught c the whole square plus pc the whole square. This is actually the energy of a moving particle. Now, people, we all know that the rest mass of a photon is 0. And that is the reason this term becomes 0 over here. So this becomes E is basically equal to PC, and that is how I get that P is equal to E by C. Is it clear, people? Is it clear? Yes or no? Amazing. Yes. Can I move ahead? People? Now let's talk about the intensity of light. Okay. Now let's talk about the intensity of light. Yes. Okay. Now what is intensity of light? Now, people, please keep in mind, okay, this should be inside your medulla oblongata. What, sir? Whenever I talk about intensity of light, it is always directly proportional to the number of photons. Whenever you hear the word intensity, sir, number of photons should come in your mind. Okay? Number of photons should come in your mind. So, intensity is always directly proportional to the number of photons. It is always proportional to the number of photons. That means more the intensity, more the number of photons. Less the intensity, less the number of photons. Clear? It should be there in your medulla oblongata. What? That the intensity should always be correlated with the number of photons. Clear, people? Clear? Okay, I'll be slow right now. I'll be explaining each and every concept over here. Okay, now let me define intensity over here. What is intensity? Intensity I'm going to define with I over here. I is basically the amount of energy E passing through per unit area in per unit time. I'll explain it again. If this is the area that I'm talking about, okay, this is the area that I'm talking about, and this is basically the energy E that is passing through it. This is basically the energy that E that is passing through it. This has area A, and E energy is passing through it in per unit time T. So intensity can basically be defined as the amount of energy which passes this area in per unit time. Are you all able to understand this? People? Chamka, clear hai? Okay. So intensity, it can be defined as, this is a very important formula, people, please mark it in your notebooks. That intensity is the amount of energy passing through an area in per unit time. Very good. People. Now, one more formula. Now, people, you have all studied. What happened? Okay, now you have all studied what is energy by time. Sir, energy by time can also be written as power. So I can also write energy is basically equal to P divided by A, where P stands for power. Over here. So this is one more formula that you get. Now, how do you understand whether in your question you have the intensity word is mentioned here or not? You have to look for the units over here. Now, over here, E stands for joule. Okay, the unit of E will be joule over here. A will be meter square over here, and this is second over here. So joule per meter square per second is your intensity, or you can also say power is watt over here. Watt per meter square is also your intensity. Again, your intensity. Yes, people, is it clear? People? Is it clear? Okay. Now, people, we all know what is basically the energy of a one photon. Sir, energy of one photon is E is equal to h mu. Sir, what will be the energy of n photons then? The energy of n photons will be n into h mu. Very logical. Yes, very logical. Okay, people. Now I want to find out some formula regarding intensity as well. I want to find out some formula regarding intensity as well. Okay. So we all know that intensity is basically the amount of energy passing per unit area in per unit time. Okay, very clear. So what is the energy? Energy is basically N H mu divided by area into T. Divided by area into T. Yes, very good. Very good. Now people, now comes the most interesting part over here. It now comes the most interesting part over here, people. What does n define over here? N is basically the number of photons. T is basically the time. So people, can I basically say n by t is number of photons passing in t seconds? Number of photons passing in t seconds. Yes. So basically, can I basically say if n photons, if n photons pass in t second, in 1 second, can I basically say n by t photons pass through it? Can I basically say in 1 second, n by t photons pass through a unit area? Yes or no? Simple unitary method. Simple unitary method. So I'm going to define one quantity over here. I'm going to define this n by t as small n. And what is small n? It is basically the number of photons which pass through a unit area in 1 second. Very, very important. Very, 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 very important. So what does this n by t give over here? N by t gives small n. Small n h mu divided by a. Divided by a. This is something which I'm getting over here. This is something which I'm getting over here. Okay. This is something which I'm getting over here. Very, very important to understand. I hope so you all understood this. Next, people. Now, I have already derived it over here. I also know that intensity is also equal to power divided by area. I also know that intensity is equal to power divided by area as well. I'm going to move it to the next page. I also know that intensity is basically power divided by area, which is also equal to NH mu divided by A. NH mu divided by A. So I can basically cancel out the A's over here. So what I'm getting? I'm getting power is basically equal to NH mu. Power equal to NH mu. Okay. And what is mu? Mu is basically C by lambda. Mu is basically C by lambda. Yes or no? Yes, mu is equal to C by lambda. I just have to substitute over here. I get P is equal to NHC by lambda. What I'm getting the formula for n. I can also substitute and get the formula of n as P lambda divided by Hc. A very, 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 very important formula when it comes to your exam. Very, very important formula when it comes to your exam. Clear people? Clear people? Yes or yes or no? Clear? Yes or no? I'm going to say it again. Intensity is the total energy passing through an area in per unit time. Clear, sir? Energy divided by time is power. So I also get intensity is power divided by area. Good. Now I want to find out the number of photons that are passing through this area. How to find it? Is the voice low, people? Clear? Okay. Now next. What is the energy of one photon? E is equal to h mu. But if n photons are passing, what is the total energy? It is going to be capital N into h mu. I'll write it over here. That capital N is basically number of photons. Okay. Disturbance, array. Hello. Echo is there? Okay. Is it clear now, people? Yeah, I don't know why are so many problems coming in today. Disturbance, array. Is it clear now, people? Is it clear now? Is it clear now? Okay, chalo. So this is the energy of n number of photons. Now I want to find out the intensity is your intensity also. So I just substituted the value of E over here. So n h mu divided by AT. Very okay. Now what is n by t? Can I basically say n by t is the number of photons passing through 1 second? How did I find out? If n photons are passing in t seconds, can I basically say in 1 second n by t photons are passing? Yes, and this I am denoting it as small n. And this I am denoting it as small n. So this becomes n h mu divided by A. Clear? N h mu divided by A. Now I also know that intensity is power divided by area, which is also equal to n h mu divided by A, which we have derived right now. A and A gets cancelled. I get P is equal to n h mu. Frequency is equal to C by lambda. I just substitute over here. P is equal to n h c divided by lambda. So the number of photons passing through 1 second is P lambda divided by hc. P lambda divided by hc. Clear? Is it clear, people? Yes. Now, this formula you can use if you want to calculate in SI units, but obviously you need to fasten your calculations as well. Okay, you need to fasten your calculation as well. So I'm gonna give you the formulas that you have to use in your exams. Over here. Okay, in your exams, which all formulas that you have to use? The formula that you have to use is n is equal to P lambda into 5 into 10 ki power 24. This formula you're going to use. When everything is in SI units. That means power is in watt, lambda is in meter, and so on. Power is in watt and lambda is in meter and everything else. Everything else is right then. This formula. But this formula, that is n is equal to P lambda into 5 into 10 ki power 14. This formula you are going to use when the power itself is in watt and lambda is in angstrom. Okay, people, please mark this. This is very important. This is very important. Yes. So this formula you're going to use when everything is given in SI units. So P is watt, lambda is in meters. This is the formula. 5 into 10 ki power 24, n is equal to P lambda. Okay, and this formula you're going to use when power is in watt but lambda is in angstrom. This is the formula that you're going to use. Otherwise, you can use this formula as well if you want it in SI units. Simple. But obviously, this calculation is a very tedious thing because the value of h and c you have to multiply and then you have to divide and everything. Clear? Can I move ahead, people? Can I get some fire emojis in the chat if you have understood this? If you have understood this, can I get some fire emojis in the chat if you have understood this? Okay. Clear? Awesome trick. Okay, very good. Okay, we all understood it. You have all understood it. Very good. Moving on, the next topic that we have to understand is radiation force and pressure. Ari, but before that, I have to ask you something. Okay, I thought some of you would ask this doubt, but theek. People, just comment down or just comment what is actually the rest mass of photon. What is rest mass of photon? Yes, what is the rest mass of photon? This is your question. What is the rest mass of photon? Let's just revise what we have studied. Yes, what is the rest mass of photon? Zero. Yes, zero, obviously. So if the rest mass of photon is zero, how come we are getting a momentum? Because we know linear momentum is P is equal to mv, and if mass is zero, shouldn't P be zero? Shouldn't the linear momentum be zero? This is one doubt, or this is one question that I'm gonna, just give it to you. It is your responsibility to find out. Why can't we use P is equal to mv over here, or why isn't the momentum zero? And this suspense I'm going to disclose in our next class. Okay, people? Okay, this suspense I'm going to disclose in your next class. Even though the rest mass of a photon is zero, why are we getting a momentum over here? Okay? This is suspense for you all. Okay? This is suspense for you all. Okay. Now coming back to radiation force and pressure. Okay, coming back. Yes, rest mass of every photon is 0. Okay. Okay, people. Now coming back. Now coming back. Okay. So does a photon exert pressure and force on a surface? Yes, they do, but a very small quantity. They do, but a very small quantity. Okay, people. Now let's understand over here. Okay, let's understand over here. Now, people, we all know that momentum is a vector quantity, and if it's a vector quantity, we have to give it direction as well. Okay, we have to give it direction as well. So this direction I'm going to denote as negative, and this direction I'm going to denote as positive. Okay, people. Now, I have a photon over here. I have a photon over here which is traveling in this direction, and it is going to strike a surface over here. And this surface is actually a perfectly reflecting surface. Okay, it's a perfectly reflecting surface. Okay, people. So can I basically say the initial momentum over here is basically minus h by lambda? Why minus? Because it is in this direction. I've already denoted that this direction has to be negative. Okay, so this is the initial momentum of the photon. Now after reflection, what happens? This photon gets reflected point, and it gets reflected back again. Okay, it gets reflected back again. So this photon over here, it gets reflected back. Now right now, the P final or the final momentum can be written as plus h by lambda. Plus h by lambda, because I've just changed the direction over here. I've just changed the direction over here. Okay. Now, according to Newton's second law, okay? Newton's second law, we know that the rate of change of momentum is basically equal to the force. Yes, we all know this. Yes, we all know that the rate of change of momentum is basically equal to the force. So basically, I can calculate the change of momentum, and then I can find out the force over here, and then I can find out the force over here. It's a very simple explanation that I'm doing over here. Okay. So what is the change of momentum that I'm doing it over here? That it will be P final minus P initial divided by the delta T, and this is going to be the force over here, and this is going to be the force over here. Yes or no? Yes. P final. What is P final? It is h by lambda. H by lambda minus. What is P initial? Minus minus plus. So this becomes minus of h by lambda over here, the whole divided by delta T, and this is basically your force over here. And this is your force over here. Yeah, I'll explain it again. Don't worry. I'll explain it again. Don't worry. Okay, people. I'll explain it again. Okay. Now coming over here, this fellow becomes 2h divided by lambda delta T, or I'll just write T over here. I'll just write T over here, and this is basically the force that I'm getting. This is basically the force that I'm getting. Yes. Now people, now just understand. I've written this formula only for one photon. But obviously there are going to be n photons. There are going to be n photons, and that is the reason I'm just going to multiply an n over here. I'm going to just multiply an n over here. Now people, just tell me, what is n divided by t? What is n divided by t? It is going to be small n. It is going to be small n. Yes sir, it is going to be small n. So over here it becomes f is equal to, this becomes 2hn divided by lambda. Divided by lambda. Clear? Clear people? Yes or no? 2hn divided by lambda. Now, earlier only I have derived this formula that n is basically p lambda divided by hc. P lambda divided by hc. So what do I get over here? This happens 2h by lambda. This is p lambda divided by hc. So if I cut it over here, lambda gets cut, h and h gets cut. So the formula of force that I get is 2p divided by c. This is the formula of force that I get. This is the formula of force that I get. So initially I've just taken one photon. Initial momentum is minus h by lambda in this direction. It gets reflected by final momentum h by lambda. According to second law, rate of change of momentum is equal to force. So rate of change of momentum can be written as Pf minus P initial divided by delta T. I just substituted the values, I get something like this. I multiplied by capital N because for n number of photons, n by t becomes small n. The value of n I substitute, that is P lambda divided by hc, and this is the formula that I get. If you all understood it, fire emojis in the chat. If you have understood it, fire emojis in the chat. Now people, you have to understand that this P over here is power. This P over here is power, okay? I'll just write it over here for no confusion, that P over here is power, okay? This is power. This is power, okay? Very good. Crystal clear? Very good. So F is basically 2P by C over here. Now I want to find out the pressure. Over here. Now this is very easy. I already know that what is pressure. Sir, pressure is no, sir. Pressure is force divided by area, sir. Sir, pressure is force divided by area. Why did I multiply by n? Because I was only calculating for one photon over here. But I want to find out for n number of photons, because n number of photons can strike a surface. That is the reason I multiplied by n. Okay. For pressure is equal to force divided by area. What is force? 2P by C. What is force? 2P by C. So 2P divided by C into area. Now people don't get confused. This is power and this is pressure. This is power, this is pressure and this is power over here. People, what is P divided by A? What is P divided by A? P divided by A, sir, is intensity. So I get the pressure as 2I divided by C. 2I divided by C. So the pressure, so the force due to n number of photons on a reflecting surface is 2P by C, where P is power, and the pressure due to n photons on a perfectly reflecting surface is 2I by C. Clear? Clear? Where did T go? I've already told you. What is n by T? N by T, number of photons traveling in 1 second. I've already told this. Where is it? Yes, n photons in t seconds. So n by t is small n. So the number of photons which travel in 1 second. Clear? Clear? Okay. Now, so this is very easy. So if photons are traveling and they strike a surface, obviously they'll strike the surface with a force, and that force is called as radiation force. Simple. And obviously as they are striking an area, they will also exert pressure in that surface, and that is called as radiation pressure. Simple. Okay, clear? If you've understood this, can you get some fire emojis in the chat, people? Okay. Now people, if you have understood perfectly reflecting surface, I think so it is very easy to understand perfectly absorbing surface. Let's understand this. It's very easy for perfectly absorbing surface. So again, this direction corresponds to negative, this direction corresponds to positive. Simple. So I have a photon over here. Which is traveling in this direction. So basically, can I say P initial to be minus h by lambda? Yes, sir, I can tell it. I can. Now, once it gets absorbed, because this is an absorbing surface, no photon will come out. So the final momentum is 0 over here. Now, it's very easy. You can derive it yourself. We know that dP by dt is basically your force. So I can write it as force is P final minus P initial divided by delta T. So F is basically, what is P final? It is 0 minus of P initial is h by lambda. This becomes h by lambda divided by delta T. So force comes out to be h divided by lambda delta T. But this is only for one photon. Okay? This is only for one photon. I just multiplied by n to get for n number of photons. But I multiplied by n to get n number of photons. Simple. So I already know what is n by t. N by t is basically small n. So this becomes F is basically n h divided by lambda. Now what is n? It is basically P lambda divided by hc, and this becomes h divided by lambda. So I just cancel h and h gets cancelled out, lambda and lambda gets cancelled out. So the force that you get is P divided by C. Clear? Did you all understood this? If you have understood this, so if you have understood this derivation, if you have understood this derivation over here, this is a very easy derivation. This is a very easy derivation. Okay, I'll slow down. Okay, I'll slow down. What did I do over here? The initial momentum is h minus h by lambda. The final momentum is 0. So the rate of change of momentum is basically force. dP is P final minus P initial. P final is 0. P initial is minus h by lambda. 0 minus minus becomes plus. So this becomes h by lambda divided by delta T. But I need it for n photons. So I multiply it by capital N over here. So I get something like this. But n divided by T becomes your small n. That is what you get, n h by lambda. Now what is n? P lambda divided by hc. The force that you get is F is equal to P by C. Clear? Now see this. Earlier for a reflecting surface you were getting the force as 2P by C. Now you are getting it as P by C, and it is quite evident because one of the photon, all the photon got absorbed, got absorbed over there. P over here corresponds to power. Okay. 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 So the formula is required over here. The derivation is not required, but for you to understand this, because you have to understand the derivation over here, because in your exams, if a complex question occurs, then you need to know how did the formula come over here, so that you can, basically derive it over there if any complex questions comes. Okay, people. Okay. Now let's understand. If this is the force, can I basically find out the pressure? Yes, sir, I can find out the pressure, because pressure over here, pressure is basically force divided by area. What is the force? Force is P by C, sir. It is basically P divided by C into A. What is P by A? It is intensity. So intensity divided by C is your pressure. Can I get some fire emojis in the chat? Can I get some fire emojis in the chat? Can I get some fire emojis in the chat if you have understood this, people? Can I get some fire emojis in the chat if you have understood this? So people, for a perfectly reflecting surface, you get the force as 2P by C and the intense pressure as 2I by C. For a perfectly absorbing surface, you just get the half of it. Force is P by C and intensity becomes, pressure becomes intensity by C, I by C. Okay, clear. Now moving on. As I said, we will be solving a lot and lots of P by Qs. We will be solving lots and lots of P by Qs. Okay, lots of P by Qs, people. Lots of P by Qs. Okay, see this, people. Monochromatic light of frequency this much is produced by a laser. The power emitted is this much. The number of photons emitted on an average source per second is how much? This is what we have to calculate. So people, we already know the formula that n is basically equal to P lambda divided by hc. And I've already told you the formula that you can use this formula. Where is it? You can use this formula for faster calculation. But if you can see over here in this question, they have asked us, in this question they have already given the value of frequency. So basically you can't use that formula. You have to use this formula itself. I'm going to give you one more. Manipulation over here. People, we already know that E is basically equal to hc by lambda. Yes or no? Over here, this is also hc by lambda, but inverse, no? So I can write it as P is basically equal to P divided by E. So I can also write it as P divided by h mu. Yes or no? Now it is very easy. What have they told us to calculate? The number of photons emitted on the average source per second. That is what they asked us to calculate. It's very easy. So n is basically equal to, power is how much? 2 into 10 to the power minus 3. I need the answers in the chat, people. 2 into 10 to the power minus 3. H is your 6.6 into 10 to the power minus 34 into the frequency is basically 6 into 10 to the power 14. 6 into 10 to the power 14. Yes, people. So this is what we are getting. Now I'm gonna explain how to basically fasten your calculation, how to increase the speed of your calculations. Okay, how to increase the speed of your calculations, see, this is very easy. Two ones are and this is two threes are over here. Okay, this is two threes are. Now 66 into 3 is 198. So 6.6 into 3 is 19.8. Can I write 19.8 as 20? Approximately 20. Yes, I can write approximately 20. I can write it as approximately 20. So this becomes 10 ki power minus 3, the whole divided by 20 into 10 ki power minus 34 into 10 ki power 14. This is what we are getting. Now this is very easy. So 1 divided by 20 is 0.05. Simple. So this becomes 5 into, this is just the decimal calculation, minus 34, 14, 3. Yes, this becomes 5 into 10 ki power 15, and this is your answer. Clear? Clear, people? Did you all understood it? Did you all understood this, people? And please like the session, people. Please like the session. Did you all understood this? Did you all understood how did I calculate it fast? How did I calculate it at fast? Yes. Very good. Very good. Okay. Very good. If you have understood this, then I can have some fire emojis in the chat. Okay, this is something that we are going to solve afterwards because we have not yet completed it. Just a second, people. We'll just solve this afterwards. Yes, I think we'll solve this over here. We'll solve it over here. Yes. Okay. Clear? Very good. Okay. Last step, man. See, I'll just explain it in a very quick manner. N is equal to P lambda by Hc, but they have not given us lambda. They have given us frequency. So Hc by lambda or lambda by Hc can be written as 1 by E. So N is equal to P divided by E. E can be written as H mu. So N is equal to P divided by H mu. Power 2 into 10 ki power minus 3. H, that is Planck's constant. Mu, this is your frequency. Now 2 ones are, this is 2 threes are. Now 3 into 6.66, 19.8. 19.8, you can write it as approximately 20. So 1 by 20 is 0.05, and rest, this is just the calculation of tens. That's it. Okay, clear? Okay. Now moving on, let us understand the photoelectric discovery, a very, very important part of the chapter that we're going to start. Okay. You can watch anything. Okay. Now, what exactly is photoelectric effect? Photoelectric effect is basically the effect in which a light of suitable frequency is falling on a metal. And due to this energy, the electrons are ejected out. And obviously once the electron starts flowing, the current also starts flowing. Yes or no? People? Is this clear? Again, what is photoelectric effect? Photoelectric effect means when a light of suitable frequency falls on a metal, the electron starts ejecting and it starts flowing, and then you get current over here. That is basically what a photoelectric effect is. Now, let's understand. It is a phenomenon of ejecting electrons by falling light of suitable frequency or suitable wavelength. We'll understand this on a metal. Ejected electrons are called as photoelectrons, and current flowing due to the photoelectrons is called as photoelectric current. This is what we are able to understand. Now you are able to see 3 sirs over here. Now we'll understand one by one. So Leonard sir, this is Leonard sir. Leonard sir was actually the one who discovered this effect. This photoelectric effect was discovered by Leonard sir. And the laws and all the laws that you study was given by, I'm so sorry over here. The effect was discovered by Hertz over here. And all the laws that you studied is basically given by Leonard over here. Okay. And Einstein was the one to explain this effect using the quantum theory of light. and he gave us the photoelectric equation. Clear? Clear? So this effect was discovered by Hertz, and laws of the photoelectric effect were given by Leonard, and it was explained by Einstein using quantum theory of light. That is exactly what happened. Okay, people, a little bit of history, and no need of understanding it. Okay, now let's understand electronic emissions over here. Now, as I said, what is photoelectric effect? In photoelectric effect, the main idea is that electrons are getting ejected out of the metal. Now, there are multiple ways by which you can do this. There are multiple ways. Let's look. The first one, thermionic emission. The name only speaks for itself. Thermionic emission, that is by use of thermal energy. By the use of thermal energy, you provide thermal energy, and due to that thermal energy, electron gets excited and gets thrown out of the metal. Electron gets excited and gets thrown out of the metal. That is what happens in the Davisson-Germer experiment that we're going to look into the future. So what happens is that there is a filament over here. Okay, there is a filament over here which is made up of tungsten metal. This tungsten metal gets heated, and because of that, the electrons gets ejected out, and this is called as thermionic emission. And the electrons which get ejected out in this manner are called as thermions. So it's not a new particle. It's just electron. It's just a special name for the electrons who come out of this method. That's it. Clear? I hope so. This is clear. Next is field emission. What is field emission? Field emission is also very easy. Very easy. You already know that if this plate is at a lower potential 0, if this plate is a higher potential V, there is an electric field. There is an electric field over here in this direction. Yes, sir. So obviously what happens is that in this electric field, or due to this electric field, if there is an electron over here, this electron experiences a force in the opposite direction. And due to this electric field, the electron comes out. But obviously the electric field has to be quite strong in order for the electron to come out of the metal. That is basically what is field emission. Clear? Clear, people? That is basically field emission. So by applying a very strong electric field of the order 10 to the power 8 volt per meter to a metal, electrons can be pulled out of the metal as in a spark plug. Okay, people? Okay. Now, this method is also known as cold cathode emission. Okay. This method is also called as cold cathode emission. Okay, people? Clear? Now comes the photoelectric emission that we are all interested in. So obviously, when a light of suitable frequency illuminates a metal surface, electrons are emitted from the metal surface. We are going to study this in detail. So a metal surface, when light strikes, electron gets the energy, and due to this energy, the electron gets out of the metal. That is what is happening. There is one more type of emission which is not there in your syllabus, but I just thought that I can say it for curiosity. Okay, that is called as secondary emission. It is called as secondary emission. What is secondary emission? Just look over here. What is secondary emission? In secondary emission, you are using an electron itself. You are using a high speed electron itself to basically collide with the electron inside the metal and push it out of the metal. So basically, an electron comes, a fast moving electron comes, it collides with an electron, and this gets ejected out of the metal. That is basically called as a secondary emission. Clear, people? Is this slide clear? Absolutely perfect, crystal clear. Can I get some fire emojis in the chat if this is clear? Okay. Can I get some fire emojis in the chat if this is clear? Okay. Thermionic emission due to thermal energy, field emission due to electric field, photoelectric emission, that is due to the photons or due to the energy of the light. Okay. And secondary emission, electron pushes the other electron out. This is obviously this is a very redundant method. Okay. Okay, take it. Now let's understand work function. Let's understand work function, people. Let's understand work function. Okay, people, what exactly is work function? Work function is basically money that the metal wants. Okay, money that the metal wants. That is exactly what work function is. Work function is basically the money that the metal wants in order for you to take the electron out. Metal will be like, if you give me certain amount of energy or that minimum amount of energy, you can take this electron and go. I don't have any problem. But yeah, you should give me that minimum amount of energy. Otherwise, I'm not going to send this fellow. Okay. That is exactly what is work function is. Now, this work function can be denoted as phi or W over here. This is also an energy, but that is basically the minimum energy that should be there. Minimum energy that should be there in the photon in order for you to get this electron out of the metal. Is this clear, people? Is this clear, people? That means this is also equal to some energy, so H into mu naught. H into mu naught. H into mu naught. So let's understand this. Let's understand this. What is work function? It is the minimum energy required by an electron to escape from the metal surface. That means this much minimum amount of energy should be there. It should be there, otherwise the electron is not going to come out. The electron is not going to come out. Okay, are you able to understand? Okay, so this is basically the work function. This is basically the work function, and over here, this mu naught, this corresponds to the threshold frequency. This is basically the threshold frequency. In order for this frequency, in order for this photoelectric effect to happen, the incident frequency should be greater than or equal to the threshold frequency. This is one condition that is must. This is one condition that is must. Clear? If the incident photon has this much amount of frequency, then the electron can come out. It may come out. It's not guarantee also even over here. I'll tell you why it's not a guarantee. I'll tell you why it's not a guarantee. It can or it may come out. Okay. Now people, see, this is very important to understand. Very important to understand. Can I basically write this phi as H, this mu naught as C divided by lambda naught? C divided by lambda naught. Yes, sir, we can all write this. So over here, this lambda naught denotes the threshold wavelength. The threshold wavelength. The lambda naught denotes the threshold wavelength. Okay, clear? Okay. So let's understand. This work function is directly proportional to the frequency. So what is frequency over, or what is threshold frequency over here? Threshold frequency is the minimum amount of frequency that the incident photon should have in order for the electron to come out of the metal. Okay. What is lambda naught? It is inversely proportional. So lambda naught is the maximum wavelength. It is the maximum wavelength that a photon should possess in order for an electron to come out. You have to understand it again. Okay, you have to understand it again. You have to understand it again. What is frequency? What is threshold frequency? The minimum frequency that a photon should have in order for the electron to come out. What is threshold wavelength? As it is inversely related, it is the maximum wavelength. Greater than this wavelength, electron will not come out. Greater than this wavelength, electron will not come out. So this is the maximum wavelength that the photon should possess if you want the electron to come out. Okay, people. Are you all able to understand this? Are you all able to understand this? So can I basically say, I can also write this as, this becomes 12400 divided by lambda naught. I can also write this as in this formula itself. Yes, I've already written this formula. Okay. Yeah, don't worry. Just ignore the spammers. we'll look onto the content over here. Okay, just ignore the spammers, we'll look onto the content over here. Yes, people. Okay, now this is very important to understand. Very important to understand. Now let's okay, now let's understand this, people. Let's understand this, people. Okay, now the electron, the metal be like, okay, so the metal is saying I need at least 5 electron volts of energy. The metal is saying I at least need 5 electron volts of energy. You are like, okay, I'll only give you 4 electron volts of energy. Obviously, as this is greater, the electron is not going to come out. Electron is not going to come out. But if you give exactly 5 electron volts of energy, if you give exactly 5 electron volts of energy, the electron may come out. The electron may come out. Electron may come. This is the pakka impossible. This is the pakka impossible. Here also it is may come out. If the metal wants 5 electron volt, but you give it 7 electron volts of energy, here also electron may come out. Sir, why may? Why not absolutely it will come out? I'll tell you the reason. I'll tell you the reason afterwards. I'll tell you the reason afterwards. But this is exactly the thing that you should understand. This is exactly the thing that you should understand. So people are able to understand that the energy incident should be greater than or equal to the energy required, or that is the threshold energy. So energy incident is H into mu. It should be greater than or equal to H into mu naught. H and H gets cancelled, so mu is greater than or equal to mu naught. This is one of the conditions that is required for the photoelectric effect to take place. Okay. No. 6 electron volt, it will not come out for sure. I'll tell you why it is me. Okay. I'll tell you why it is me. Then again, I can also say that mu can be written as C divided by lambda, and this is greater than or equal to C divided by lambda naught. C and C gets cancelled out. This gets reversed, reciprocal, the sign changes. So lambda is less than equal to lambda naught. So this is also one more criteria for the photoelectric effect to take place. Are you all able to understand this, people? Are you all able to understand this? Now let's understand the condition for photoelectric effect. I'll tell you. Now the suspense will go, okay? Now the suspense is going to vanish away. Don't worry. Now people, what happens is that 6 electron volt. Just imagine a photon is coming with 6 electron volts of energy. This metal requires only 2 electron volts of energy. That is, the threshold energy is of 2 electron volt. So this photon will come, it will strike the surface, the metal will take 2 electron volts of energy. Now the remaining 4 volts of energy, you will be like, sir, the electron will come out with 4 electron volts of energy. But I'll tell you why it may come out. Now why the may word is important. It may happen that as soon as this photon strikes with 6 electron volts of energy, this the metal takes away 2 electron volt of energy, 4 electron volt of energy is still left with the electron. But this electron starts colliding with the other electrons, and the energy gets wasted. So out of 4, only 2 electron volt energy is remaining, because 2 electron volt gets wasted in the collision. And again it gets collided, and again it gets collided with another electron. And so the 2 electron volt also gets wasted over here. That is the reason the electron will not come out. But also there is also one more case. That 6 electron volts strike the surface, 2 electron volt is taken by the metal, and with no collisions, the electron comes out with 4 electron volts of energy. Clear, people? Clear? Are you able to understand this? Or it also may happen that 6 electron volts of energy will strike the surface, 2 electron volt the metal will take itself, 4 electron volt is remaining, and the electron only collides once. So the remaining energy is 2 electron volt, and the electron comes out with 2 electron volts of energy. It may happen so. Are you able to understand this? Or it may happen that 6 electron volts, the photon strikes with 6 electron volts, 2 electron volt is taken by the metal, so 4 electron volts remaining. All of the energy that 4 electron volt of energy gets wasted due to the collisions, and an electron comes out with 0 electron volts of energy. Just comes out of the metal. Just comes out of the metal. Are you all able to understand this? Are you all able to understand this, people? Yes, that is the reason I said that the electron may come out. Because there is always a chance that the electron loses its energy due to the collisions inside. Okay, clear, perfect. Okay. Now, this is something that you have to understand. Okay, clear. So, the one thing that you have to understand is that the incident frequency should be greater than or equal to mu naught, and the lambda should be less than or equal to the lambda naught. This is the necessary condition for photoelectric effect to take place. And here also it may happen, है ना? May happen. You all know why I've used the word may over here, because over here the electron's energy can get wasted due to collisions. Perfect. Perfect, clear. Okay, so when it will not happen, obviously it will not happen if the incident frequency is less than the minimum frequency which is required, or if the lambda which is incident is greater than the lambda which is required. In this condition, it will not happen. It will not happen. It will not happen. You said electron need minimum 5 electron volt. Okay, I'll just explain it again. So the metal needs 2 electron volts, that is the threshold energy. Photon has 6 electron volt. It will just strike the surface, metal will take the 2 electron volt of energy, the remaining amount of energy is 4 electron volt. So it may happen without any collisions, the electron will come out with 4 electron volt of energy. But due to collision, it loses more 2 electron volt, so the electron comes out with 2 electron volt. But with more collisions, the electron loses the 4 electron volt energy also, and that is the reason the electron will just come out of the metal itself with 0 electron volt of energy as well. Okay, people? Okay, clear? Is this clear, people? Are you all able to understand this? Are you all able to understand this? Yes, can I get some fire in the chats if you're able to understand this? Can I get some fire in the chat if you're able to understand this, people? Okay, chalo. Let's understand. Let's solve this question. Let's solve this question. What is it? The work function of cesium and lithium metals are 1.9 electron volt and 2.5 electron volt respectively. If we incident a light of wavelength 550 nanometer on these two metal surfaces, then photoelectric effect is possible for the case of which? Okay. So you have to understand, it is very easy. In order for photoelectric effect to take place, the energy incident should be greater than or equal to the threshold energy over here. Yes, threshold energy over here. Yes or no? So can I basically say incident light is of wavelength 550 nanometers. Okay. So energy over here is 1240 divided by 550. And this is the formula that I'm using. This is the formula that I'm using over here. So the formula that I'm using is E is basically equal to 124 divided by lambda but in nanometer. And the energy is in electron volt. Okay. So this comes out to be, how much is this, people? How much is this? I need the answers in the chat, people. I need the answers in the chat. It comes out to be 2.25 electron volt. Now, what is the incident energy of the photon, people? The incident energy of the photon is 2.25 electron volt. Hai na? The work function. Now, what is the work function? The work function of cesium is 1.9 electron volt. Obviously, the incident energy is greater than the work function. Then obviously, cesium is going to show a photoelectric effect. 2.5 electron volt for lithium. Arey yaar, the energy incident is less. So it's not going to show for lithium. So it is only going to show for cesium over here. Option 2. Clear? Clear, people? Yes? Let's move ahead. Okay, now let's understand the Leonard experiment. Okay, now let's understand the Leonard experiment. What did Leonard do over here? Okay. So obviously, this is basically a vacuum. This is basically called as the emitter plate. This is called as the collector plate, and this is connected to a battery over here. And this is an ammeter which measures the current. Okay. Now, light over here. So photons are so photons are incident, है ना? So the photons are incident, with each photon having energy greater than equal to the work function over here. Obviously, otherwise the photoelectric effect is not going to take place. So the energy of one photon is greater than the work function itself. Okay. So the photons are coming and they're getting incident to this emitter plate. And due to this, the electrons are getting ejected out. And obviously this is the electron. This is the electron which are getting ejected out. Okay. This battery is also connected. So this is the negative potential. So obviously this will have negative potential over here. And this will have positive potential over here. And it is very much easy to understand that the electrons will get attracted to the positive potential over here. And so the electrons are going to travel something like this. They are going to travel something like this. And as the electrons are traveling something like this, in this direction, the current will be flowing in this direction. The current will be flowing in the opposite direction. Are you all able to understand this? Yes. So this is basically the Leonard observation. We're going to come back to this observation. Okay. This was just the gist of what he observed. Okay. We're going to come back to this observation. Clear? Let's move ahead. Now let's understand. Now we were talking about the particle theory. Okay. Now let's understand, why did wave theory fail explaining the photoelectric effect? This is very important to understand. People. Now I'll tell you what is happening over here. Okay, people. See this. If the work function of the metal over here is 6 electron volt, okay, this is metal over here, and this is photons of 3 electron volts of energy, okay, of 3 electron volts of energy. Now you have to understand, if the light was considered as a wave, 3 electron volt photon would strike the surface. One more photon of 3 electron volt would strike the surface, and the electron would be ejected out. But this is not happening. Obviously, there are two problems over here. One problem, the first problem. In this experiment, you have to understand, as soon as the light is incident on the emitter plate, the photoelectric effect starts. The electron starts coming out. As soon as the light is incident on the emitter plate, the photoelectric effect starts. It starts after some 10 ki power minus 7 to 10 ki power minus 8 seconds. Are you able to understand this? As soon as the light is incident, after the duration of 10 to power minus 7 or 10 to power minus 8 seconds, the photoelectric effect starts. But according to wave theory, if the work function is 6 electron volt, 3 electron volt photon will strike, and one more 3 electron would strike, and the electron would come out. So obviously there should be a time lag. Because obviously it would take some time for two photons to strike the surface, right? It would take some time for 2 photons to strike the surface and eject the electron out, but it's not happening. In reality, the photoelectric effect is instantaneous. It is instantaneous. And one more thing. You have to understand this. Over here, you have to understand this. One photon will eject only one electron. one photon will eject only one electron. This is something that you have to understand. This is something that you have to understand. One photon is going to eject only one electron. This is not possible. This is not possible. This is not possible. This is according to the wave theory of light, that if the work function is 6 electron volt, so 3 electron volt and 3 electron volt, total 6 electron volt, so the electron should come out. No, this is not possible. This is not possible. Because it should be instantaneous. If this is the case, it would have not been instantaneous. Are you all able to understand this? Are you all able to understand this? So, according to the wave theory, when light incident on a surface, energy is distributed continuously over the surface, so that electron must take a time interval to accumulate sufficient energy to come out. But in this experiment, there is no time lag. Are you able to understand this? Are you all able to understand this, people? So, the electron needs 6 electron volts of energy. If according to the wave theory, 3 electron volt photons would be striking the electron. So, there would have been a time lag before the electron comes out. But it's not the case, because electron just comes out instantaneously. And two photons will not eject one electron. It is always that one photon is going to eject one electron. Are you all able to understand this? Yes. Clear? Next. Now people, this right over here is basically the theory of wave theory. According to, now tell me, according to when I started the chapter, what did I tell you? What is intensity directly proportional to? What is intensity directly proportional to? What is intensity directly proportional to? You will be like, sir, according to particle nature, intensity is directly proportional to the number of photons. Intensity is directly proportional to the number of photons. But according to the wave theory, when the intensity is directly proportional to the energy, intensity is directly proportional to the energy according to wave theory. So more the intensity, more the energy according to wave theory. Now there is one problem over here. That means if you just increase the intensity, you are increasing the number of photons. If you are increasing the number of photons, the energy is getting increased. So there should not be any concept of threshold frequency at all. There should not be any concept of threshold energy as well. Are you all able to understand this? If just increasing the intensity increases the energy, why there is a concept of threshold frequency, that this minimum amount of energy should be present in one photon? Just increase the intensity, just increase the number of photons, and you will get photoelectric effect. Are you all able to understand this? So when intensity is increased, more energetic electrons should be emitted, so that stopping potential should intensity depend, but it's not observed. So I'll explain this afterwards. What is stopping potential and everything. So what I'm saying is, according to wave theory, more the intensity, more the energy of the photons. And if more the energy of the photons, there should be no concept of threshold frequency at all. Are you able to understand this? Okay. And the third is, according to wave theory, if intensity is sufficient, then at each frequency, electron emission is possible. It means there should not be existence of threshold frequency. Yeah, that is what I was saying. There should be no concept of threshold frequency at all, that this is the minimum amount of energy that is required, or this is the minimum amount of frequency that is required by the photon, so that the electron can come out of the metal. If I am saying, if I can just increase the intensity and the energy is getting increased, why should I care about the frequency? That is the reason. All of this is the failure of wave theory. These are all false. Okay, these are all false over here. Yes, people, is it clear? Now let's understand Einstein's photoelectric equation. Chalo, let's understand the Einstein's photoelectric equation. Are you all ready, people? Are you all ready to understand Einstein's photoelectric equation? It's very important. Very important. So, in order for the photoelectric effect to take place, the condition is the energy incident should be greater than equal to the threshold energy. This is the condition that we know. Okay, this is the condition that we know. Yes, sir. This is the condition that we know. Now, people, just look over here. Okay, just look over here. Okay, if the threshold energy, of this metal is 2 electron volt, and the incident energy of the photon is 6 electron volt. Obviously, the photon is going to strike the surface. 2 electron volt the metal is going to take, and assuming that there is no collisions, all of the energy that is still remaining, that is 6 minus 2, 4 electron volts of energy would be the kinetic energy of the electron itself. Yes or no? Now, so basically I can say something like this, that if E is the incident energy, if E is the energy of the incident photon, some energy will be taken by the threshold energy itself, that is, some energy will be taken by the metal itself. So the remaining energy is basically going to be the kinetic energy or the maximum kinetic energy of the electron, assuming there are no collisions. Yeah. I'm going slow, don't worry, people. Yes. Are you able to understand this? That means if E is the energy that is incident, phi, that is the threshold energy, some part of the energy will be taken by the threshold energy, and the remaining energy will get converted into the maximum kinetic energy of the electron, assuming that there are no collisions. I can also write this as something like this, that half mass of the electron into V max square, that this is the maximum kinetic energy of the electron. This is basically equal to kinetic energy max, and this is basically energy incident minus phi. This is also one of the ways that you can write the photoelectric equation. Now, what is this? This is basically the kinetic energy of the fastest electron. This is the kinetic energy of the fastest electron. I'll give you dinner break, don't worry. When do you want the dinner break? When do you all want the dinner break? When do you all want the dinner break? It's just 6:30 right now. We'll move ahead. Okay? Yeah. So this is the kinetic energy of the fastest electron, because there is no collisions. But people, obviously I've said that the kinetic energies always happen in ranges, because there will be some electrons obviously with the maximum kinetic energy, and obviously there will be some electrons which collide with each other and then come out of the metal. So there is a possibility that 6 electron volt of photon strikes the metal. 2 electron volt is taken by the metal itself, so 4 electron is remaining. Due to one collision, 2 electron volts is lost, and this comes out with 2 electron volts of energy. Or it may happen 6 electron volt strike, 2 electron volt is taken by the metal, and due to collision 4 electron volt is taken up by the collision, and this electron just comes out with 0 electron volts of energy. Okay, people? Yes, I'll give you break then. Okay, people, are you all able to understand this? That means other electrons. If I talk about other electrons, their kinetic energy is going to be less than E minus phi. They're going to be less than E minus phi. Yes, did you all understood this? Obviously, it's going to be less than the maximum kinetic energy due to collisions. Yes. So the kinetic energy of the other electrons would be less than this. Simple. So can I basically say this, that the range of kinetic energy, is going to be K, and this is going to be less than maximum kinetic energy, and obviously it is going to be greater than 0 itself. This is basically the range of kinetic energy that you will get over here. range of kinetic energy that you will get. So some electrons would be in the mid range due to collisions. Some electrons would have the maximum kinetic energy because of no collisions, and some electrons would have just zero energy because of collisions. They have lost all energies due to collisions. Clear, people? Have you all understood this, people? Have you all understood this, people? Yes or no? Have you all understood this, people? If you have understood this, can I get some fire in the chats? Can I get some fire in the chats, people? Yes. Clear. Okay. Very good. 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 Okay. ठीक है. मतलब you all understood this. Very good. Now let's move ahead. Let's move ahead, people. है ना? Let's move ahead. Okay. Now, people, see this. Kinetic energy max is basically equal to half into mass of the electron into V max square, that is the maximum velocity of the electron. This is also equal to E into V naught. Now, what is this E into V naught? I'll explain it later. Okay, I'll explain it later. This is equal to the energy incident minus the threshold energy. Okay, very good. This is the equation that you have got. I can also write this as kinetic energy max is basically equal to H into mu minus H into mu naught. This is something that I'm getting over here. This is something which I'm getting over here. Okay. Now, if I look over here, okay, if I look over here, I'm going to draw a graph of this. So over here, this is y, this is m into x, this is plus c. Okay, this is plus c. Let's draw a graph of this. Yes. Over here, you will be able to understand. Okay. So m over here is Planck's constant, so that is a positive constant, so you're getting a positive slope. But the y-intercept over here is negative, minus h mu naught. So you will get the equation something like this. Something like this. Yes or no? Yes or no? Did you all draw the graph, people? Did you all draw the graph? So this is basically kinetic energy. And this is basically your frequency or energy. This is E or mu. Yes, people. Did you all understood this relation over here? Now, from this graph only you are able to understand that this is theta, and tan theta over here is basically your slope, and that corresponds to your Planck's constant. Slope is equal to h. Yes or no? Yes or no, people? Yes, sir, we are able to understand. this. Okay. Now one more thing, people. I can write this equation as one more thing. I know that is E into V naught is basically equal to H into mu minus H into mu naught. I'm dividing this whole equation by E itself. If I divide this whole equation by E, I'm getting V naught is basically h divided by E into mu minus h divided by E into mu naught. This is what I'm getting. This is what I'm getting. Yes. Now, let's draw the graph again. Okay? Let's draw the graph again. Let's draw the graph again. Okay. Over here it's the same thing. This corresponds to V naught and this corresponds to mu. Same thing over here, people. Y is equal to mx plus c, negative intercept and positive slope. Negative intercept and positive slope. Negative intercept and positive slope. Same graph you'll get. Same graph you'll get. Same type of graph. But the only difference being, I'll tell you. The only difference being that this is theta and tan theta over here is basically your slope, and this comes out to be h by E. This comes out to be h by E. Y is equal to mx plus c. Y is equal to mx plus c. Clear? Are you all able to understand this? If you have understood the graphs, can I get some fire emojis in the chat? Both the graphs, they are very important. Both the graphs, they are very important. Very important. Yes, slope is equal to h by E. It's not C, it's h by E. Okay, h by E. Okay, great. Now people, a very interesting question can come over here, and very interesting question can come over here. Very interesting question can come over here. Okay, the question is, I'll write the question over here. Okay, the question is, I have a graph. I'm going to draw a graph over here. Draw a graph over here. Okay, and this graph actually belongs to V naught, and this is mu. Okay, and this is mu. And I have a graph over here, something like this. Okay, this is first metal, this is second metal, this is theta 1 and this is theta 2. I want you to identify which metal is copper and which metal is aluminium. Okay, which metal is copper and which metal is aluminium. Is one copper and second aluminium, or is one aluminium or second copper, or this is option A for you all, this is option B, and option C, I don't know, and option D is not possible. Yeah, if you get a graph something like this, yes, I'll tell you, Hena, I'll tell you. So this is the question. V naught and mu, the graph, this is the graph that I've given you. This is the line that I've given you with theta 1, theta 2 slope, 1 and 2. You have to basically say which one is the correct answer. Option A, 1 is copper, second is aluminium. Option B, 1 is aluminium, second is copper. C, I don't know. D, not possible. Yes, tell me people. Don't worry, even if you give the wrong answer, you don't have to worry, because you're learning right now, hai na? Because it's much better that if you commit mistakes now rather than at the NEET exam. Okay, tell me. Okay, so I can see A, C, D, A, I don't know. A, C, C. Okay. So the correct answer is, people, so the correct answer over here is option D. Option D is your correct answer. Not possible. This graph is not possible. I'll explain you why. See this, people. If you look into this equation, this equation is basically V naught is equal to h by E mu minus h by E mu naught. Okay, people, tell me, what is the slope? The slope, sir, is h by E, irrespective of the metal. Irrespective of the metal. Irrespective of the metal, if you see, the value of m is always a constant. See, h is a constant, 6.6 into 10 to the power minus 34, and E, charge of E, 1.6 into 10 to the power minus 19. Irrespective of the metal, for every metal, you'll get this graph. You'll get this graph. The slope should be same. That is the reason that this is not possible. This is not possible. Are you all able to understand this? Yes, lines must be parallel to each other in order for this to be a correct graph. In order for this to be a correct graph. Are you all able to understand this? Because in this equation you are able to understand the slope is constant irrespective of the metal. Are you all able to understand this? So mark this. So you should mark this question, and also you should mark this graph as well. That is the reason I've drawn basically two different graphs over here. Yes or no? Okay. Yes or no? Chalo. Kya baat hai? So in this equation you are able to understand the slope is constant. So irrespective of the metal, you'll get parallel lines for different metals, but the slope should be same for every metal. That is the key takeaway that we know from here. Okay. Now let us understand the graphs. Very, 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 very important. Very important. Okay. Now, people, before moving, there is some certain things that you have to understand. There is some certain thing that you have to understand. Whenever you hear the word intensity, it is always directly proportional to the number of photons. It is always directly proportional to the number of photons. That's it. You don't have to care about anything else. But when you hear the word frequency, you always have to correlate it with energy. Okay, you always have to correlate it with energy. Okay, people. This is one thing that you should understand. This is one equation that you should understand in order for you to understand graphs. Clear? Can we move on to understand graphs? Okay, let's move on. People, let's understand the effect of intensity. Effect of intensity. Okay. Okay, let's understand this. Let's understand this, people. So if you all notice over here, they have written over here, they have written I3 is greater than I2 is greater than I1. This is what they have written. So this is the photocurrent and this is the collector plate potential. I'll make you understand what exactly is this. So it's very simple. As you increase, see, for I1 intensity, you are getting the current over here. For I2 intensity, a little more up. For I3 intensity, a little more up. Obviously, because as the intensity is getting increased, the number of photon is getting increased. So people, are you all able to understand this? Are you all able to visualize this? People, the number of photons has increased. Provided each photon has energy greater than the threshold frequency. Threshold energy required. So I've increased the number of photons, and one photon ejects one electron. More photons, more number of photons will come into this plate. More electrons will get ejected. Then the current will also increase. Yes or no? Again I'll explain it. More intensity, that means more number of photons. More number of photons will strike the surface. More number of electrons will come out of the surface. More electrons, that means more current. That means I can write people. Can I write something like this? That intensity is directly proportional to the number of photons. Yes, and I can also say it is also directly proportional to the number of photoelectrons as well that is getting ejected out, and it is also directly proportional to the current I that is getting produced. And it is also directly proportional to 1 by d square or 1 by d. Now what is this 1 by d and 1 by d square? I'll explain you. I'll explain it to you. I'll explain it to you. Okay? 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 Now what is this d and d square? I'll explain it to you. D is basically, what is this d? D is the, d is basically the distance of the source. Distance of the source from the observer. Okay? More intensity, more photons. No. Not more energy. No more energy. I've already told you, intensity is just directly proportional to number of photons. No energy. Energy is the concept of waves. This is particle nature that we are studying. This is particle nature that we are studying. Okay, people. Okay. Yes. I is directly proportional to number of photons, number of photoelectrons, number of I, and what is this d? This d is basically distance of light from observer, and this is basically for point source. This is basically for point source, and this is basically for line source. Okay, line source. That means, see, this is very easy to understand. This is very easy to understand. Okay, see this. Okay, see this. Okay, this is a light source. If I increase the distance, the intensity is less. That is the reason we are getting inverse proportional. Intensity and distance is inversely related. And for a point source, it is 1 by d square. And for a line source, so basically a line which emits a radiation, it is 1 by d. If I decrease the distance, more intensity. If I increase the distance, less intensity. This is more intensity because more number of photons are falling into your eyes. Less number of photons are falling into your eyes. Are you able to understand this, people? Are you all able to understand this, people? Yes. Yes. Yes, people. So this is the relation that you have to understand. Now this, isn't this graph very easy to understand? Photoelectric current is directly proportional to intensity of light. Obviously, intensity is directly proportional to the current. Obviously, why? Because increasing the intensity increases the photons. Increasing the photons will increase the number of photoelectrons getting ejected. Increasing the number of photoelectrons will increase the amount of current flowing in the circuit. Directly proportional. Simple. Now comes the main question. Okay. Number of photons would it be equal to the number of electrons? Would this be equal? Is this true? Yes or no? Is this true or is this false? Is this true or is this false? Is this true or is this false? That the number of photons that you have basically thrown at the plate or the metal plate will be equal to the number of electrons coming out of the plate. Is this true or is this false? See, this is how NTA tricks you, and this is how you lose your number. This is how NTA tricks you, and this is how you lose your number. And you are saying, why I'm not able to crack NEET? See, people, very, 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 very important. The answer is false. Why? I'll tell you. People, I've already told you that electrons will come. Some of the electrons will eject the electrons. So the photons will come and some of the photons will eject the electron. But there are some photons, even after getting the threshold energy over here, because of collisions, the electrons will not come out. So the number of photons is not equal to the number of photoelectrons getting ejected. People, are you all able to understand this? Are you all able to understand this? Yes or no? Very, very important. Very, very important. Please mark this. Please mark this in your notebook and keep it. Please mark this in your notebook and keep it. Yes. Was it a good question? Was it a good question? Yes. I've already told you. Yes. Very good. Okay, sir, got it. Very good. Okay. Now let's understand what exactly is the stopping potential. What exactly is the stopping potential? Coming back to the diagram. Coming back to the diagram. Which diagram? The Leonard diagram. Where is it? Okay. The Leonard diagram. Okay. Now people, now see this. Now as I said over here, where is it? Where is it? Where is it? Where is it? That the electrons which are getting ejected will have zero kinetic energy as well, will have some intermediate kinetic energy as well, and will have some of the electrons will have maximum kinetic energies as well. Yes. So can I basically say from this diagram that I am looking over here, where is the diagram? Yes. In this diagram, can I basically say, okay, I'm just gonna copy this fellow. Okay, copy this fellow and array yaar. Okay, see this. Okay, see this. Okay, now this is very important to understand. This is very, very, very important to understand. Okay, very, very important. If you understand this, if you visualize this, then it's very easy. These are all the electrons. These are all the electrons. Okay, and some electrons over here. Yes, exactly. Haseen has, you know, no salt on your jhakkam. Okay, okay. Haseen, yeah, yes, you are absolutely right. So let's understand that this, if this electron has some maximum kinetic energy, this also has some maximum kinetic energy. This has some K2, this has some K1, this has some K3, and this has some K max kinetic energy. Okay. Okay. This is basically the range of kinetic energies of these electrons. Okay, people? Yeah. Now what is happening? Now what is happening? Because of this battery, this has negative potential over here, this has positive potential over here. So electrons be like, yay, I'm going to the positive potential. They all run. They complete the circuit and the current is moving. No issues. Now what I'm doing is, I am decreasing the potential of the collector over here. I'm decreasing the potential of the collector over here. So if I'm decreasing the potential, the attraction would be less. Yes, sir, the attraction would be less. And if the attraction would be less, obviously there would be some problem for the electrons to move, but the electrons still have sufficient kinetic energy to move to the collector plate. Yes, we have to understand. Yes, but then I am like, okay, I'm decreasing it furthermore. What I do is I change the polarity of the battery. So right now what is happening, this becomes the positive terminal and this becomes your negative terminal, and because of that this has some positive potential and this has negative potential. Arre yaar. So right now it is negative over there, it is positive over there. The electrons are facing a repulsion, but still electrons are like, no, I have sufficient amount of kinetic energy to move to the collector plate and complete the circuit. Yes. Yes or no? Yes or no? I'm saying, okay, I'll reduce it even more further. I'll reduce it even more further. And when I reduce it, when I basically keep it more negative, okay, I'll keep it more negative. Because of that, this K1, K2, this K2, this K3, they are not able to travel to that place. Okay, they are not able to travel to that place. But kinetic energy maximum electron, they are like, no, I have sufficient energy, I can still travel to the collector plate. But then I'll still decrease the potential over there. And this potential is basically V naught. This is V naught. No, they won't get attracted because they have kinetic energy in this direction. No, they have kinetic energy in this direction. That is the reason. Okay, but obviously these all electrons would get attracted back again, those who have less kinetic energy, those who have less kinetic energy. Okay, kinetic energy max, I've done this, the potential is now minus V naught over there. Now in this minus V naught, in this minus V naught potential, this maximum kinetic energy electron is also not able to reach there. This is not able to reach there. So no electrons are able to reach the collector plate, and that is the reason, you are getting zero current over here, not in zero potential, but in negative potential, and this is called as the stopping potential. This is called as the stopping potential. Are you all able to understand this, people? Are you all able to understand this, people? That is the reason. Now I will explain you why kinetic energy max is equal to E into V naught. This V naught is basically your stopping potential. This V naught is basically your stopping potential. Why? Because see, I'll make you explain this. What do I mean by this? This is basically what potential should I provide? What potential should I provide in order that the electron gets accelerated to this kinetic energy? But if I reverse the polarity, this is basically what potential should I provide to stop this maximum kinetic electron from reaching the collector plate? Yes or no? Yes or no? Yes or no? Are you all able to understand this? So what is EV naught? EV naught is basically V naught is the potential difference by which you have to accelerate the electron so that it has a kinetic energy of half mv square. But if I reverse the polarity, this becomes what kind of negative potential I have to provide so that I can stop a maximum kinetic energy electron from reaching the collector plate. Is this clear? Now let's understand. Now let's understand why having different intensities, all of them having different intensities, they have the same stopping potential. They have the same. Why do they have the same stopping potential? It's very easy. People, intensity, number of photons. Intensity, number of photons. Intensity is not related to energy. Intensity is not related to energy. Intensity is just increasing the number of photons. You have not basically increased their energy. Intensity does not increase their energy. Intensity only increases the number of photons. The energy of one photon is still the same. Energy of one photon is still the same. So all of the photons in I3, I2 or I1, they all have the same energy, and due to all of them having the same energy, minus V naught potential is the retarding potential or the stopping potential by which you can stop the photons. Are you all able to understand this? If you did understood this, I want fire in the chat. 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 In this condition, in this graph, the frequency is constant. The frequency is kept constant. The frequency of the of the photons is kept constant. So each photon has the same amount of energy. That is the reason every photon over here has the same stopping potential. I mean, is it absolutely freaking clear? Have you ever understood it this way? Have you ever understood and visualized this way? Have you ever understood it this way? Yes, people. So, in conclusion, if I want to repeat it again, more the intensity, more the current. More the intensity, more the current, because intensity directly proportional to number of photons. Number of photons, that means number of photoelectrons will increase. So number of photoelectrons will increase, so the magnitude of current will also increase. That is the reason you are getting different values of photocurrent over here. But all of them still have the same, the photon have still, all of the photons though having different intensities, have the same amount of energy. How much? H mu. So in order for them to stop, you need to have just the same stopping potential. That's it. That's it. Simple. Now, one more thing. Why are you getting this parallel lines over here? This lines are called as the saturation current. This line is called as the saturation current. Saturation current. Now what is the explanation? Very simple explanation. Very simple explanation. All of the where is it? All of the photons that have striked the emitter plate, and due to which the electrons are getting ejected, some electrons are getting ejected over here, all of the electrons have reached the collector plate, and the current has saturated over there. It has attained a constant value because all of the electrons which have formed over here have reached there, and that is the reason a constant value, you are getting a constant value. No more electrons are getting produced. That is the reason a constant magnitude of current you are getting. Able to understand it? Are you able to understand it? So we are basically literally, like in Hindi we say, no, पूरा निचोड़ दिया है, है ना? Just one graph, I've just explained the full history of photoelectric effect. Are you all able to understand this, people? Is this clear? Is this clear? And this is a very easy graph, directly proportional. That's it. Clear? You all have to practice this graphs. Okay, you all have to practice this graph. Okay. Effect of frequency. Effect of frequency. Effect of frequency. People, I think we have made this graph already. This is V naught is equal to H by E into mu minus H by E into mu naught. This is the graph. Theta, tan theta is equal to M is equal to H by E. This is basically the work function. This is basically the work function. Yes, we have already completed this graph. We've already completed this graph. Yes, already completed. Now, this is again a very interesting graph. Very interesting graph. Now, if you have understood the story which I have already said before, this is a very simple graph that you can all understand. Okay. What is this, people? 3 different lines, and here one common line. So basically, can I say, if the current is constant over here, the intensity is constant. Can I basically say this? That is the reason you are getting the saturation current for every line as the same, no? The intensity is constant. That is the reason you are getting same current. But different stopping potentials. Why? Because right now the frequency is not constant. See this? They've already said the frequency mu3 is greater, mu2 is V3 is greater than V2, it is greater than V1 itself. Obviously, V1 being the least amount of energy, electron energy, it will have the least amount of retarding potential. This having a much more greater frequency, you have to give the stopping potential a much more negative value. This is the maximum energy. V3 is the maximum energy of the electron, of the frequency. That is the reason you have to give a much more negative value to stop it. That is the reason three different stopping potentials you are getting, but the intensity is constant, so the current is same. The current is still the same. Are you all able to understand this? Yes or no? No, stopping potential is not related to intensity. Stopping potential is not related. You can all write it over here. That stopping potential is only related to the frequency. Are you all able to understand this? See this. Intensity is constant over here. That is the reason you are getting the same current value. Same current value. But frequency is not constant. Frequency is changing over here. Frequency is changing. So this is for even energy. Even energy. Even energy. This is for E2 energy of photon and this is for E3 energy of photon. Obviously, more the energy of the photon, if you have increased the frequency, see this, if you have increased the frequency, of the photon, that means I've increased the energy of the photon. Yes, sir. If I've increased the energy of the photon, the maximum kinetic energy of the electron would be increased. Yes, sir. If the maximum kinetic energy of the electron is increased, more negative potential has to be given in order to stop it. Did you understood this? Once more. Sir, intensity is constant. That is the reason we are getting current as same. Okay, very clear. But sir, if I've increased the frequency of the photon, I'm increasing the energy of the photon. Yes, sir. If I'm increasing the energy of the photon, the maximum kinetic energy of the electron will also increase. Yes, sir. If the maximum kinetic energy of the electron has been increased, more negative potential has to be given in order to stop it. Yes, sir. That is the reason. That is same thing is happening. More frequency, more negative potential. Fire in the chat if you understood this. Fire in the chat if you all understood this. Simple. That is what it is. That is what it is. Simple. Now, one more question for you all. One more question for you all. The question is, if I increase, okay, if we double the frequency, if we double the frequency of photon, what would happen to kinetic energy of the electron? Option A, double, less than double, D, more than double, and E, less than double, more than double. I don't know. This is the question. Yeah. So the question is, if we double the frequency of the photon, what would happen to the kinetic energy of the electron? Would it double? Would it be less than the double, more than double, or I don't know? Let's see. Double. Okay, everyone is saying A. Friends, my dear friends, okay, my dear punter log. You know, this was one question that I gave you, and you all fell into the pit that I made. And this is one more question that I made, and you again fell into that pit which I made. Okay. See, when I was explaining, I never mentioned the term double. What I said was, if I increase the frequency of the photon, the energy of the photon would increase. Yes, sir. If the energy of the photon is increasing, the kinetic energy of the electron would decrease. I did not say it's less than double, more than double. The answer is, let's see, okay? Let's see the answer, okay? So basically, can I say that kinetic energy max is basically energy incident minus phi? I'm going to explain this using an example, okay? I'm going to explain this using an example, okay? See this. Let's assume that the energy incident was some 6, okay, 6 electron volt, and the threshold frequency is 2. So the kinetic energy maximum that you are getting is 4. Makes sense? Yes, sir. Now I have doubled the frequency. If the frequency is double, the energy will also get doubled. Obviously, baat hai na? Sorry, it is obvious, hai na? It is very much obvious, hai na? It is very much obvious. So this gets doubled, so this becomes 12. But the threshold frequency still remains threshold frequency because it is dependent upon the metal. It is dependent upon the metal. So you get 12 minus 2 as 10. Is kinetic energy max 10 double of 4 or more than double? It is more than double. That is your right answer. Are you all able to understand this? It will increase. It will increase. But see this. Did you understood it? Yo, ye kya hua? Did you all understood this? So the kinetic energy gets doubled, more than double, not just double, more than double. Repeat. Okay, see this. So let's assume that the energy incident is 6 and the threshold is constant. See this. I'll just write it over here. I just write it over here that the work function is constant for a metal. It is constant for a metal. It does not change. It does not change. It will not change. It does not change. Okay? It will not change. So the phi is constant. Phi is constant. So the energy is 6. Now I have doubled the frequency. If I have doubled the frequency, the incident energy will get doubled. That is 12. Threshold still remains 2. 12 minus 2. What is the energy? Maximum kinetic energy. It is 10. Is it double of 4? No, it is more than double of 4. If you all understood this, fire in the chats. Then I can move ahead. If you all understood this, fire in the chats. Okay, cool. Cool. Got it? Very good, people. Very good. Okay. Now, so see this. I've written definitions for you all. That magnitude of the minimum negative potential at which I becomes 0 is called as the stopping potential. Yes. That is what is happening, right? Stopping potential, no electrons can move right now. So no current. So stopping potential is that potential at which no electrons can travel to the collector plate, and hence the current is 0. At stopping potential, most energetic electrons are stopped, even the kinetic energy max is stopped. It means stopping potential measures the maximum kinetic energy of the photoelectrons, that is E into V naught is basically equal to K max, which is basically equal to half mv max square. Yes, it was not related to frequency, then how can we say based on it? Who was not related to frequency? Who is not related to frequency? Kinetic energy is related to frequency. Who said? I've already told you. Intensity is directly proportional to number of photons. Frequency is directly proportional to energy, and stopping potential is again related to frequency. ठीक है? Yeah. Question, people. Question. 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 Please read it. And I want the answers in the chat. Okay? It's very easy. In a photoelectric experiment, increasing the intensity of incident light would be what? increases the number of photons incident, I think so it is right, and also increases the kinetic energy of the ejected electrons. Does it increase the kinetic energy of the incident electrons? No. Intensity is just number of photons. Just number of photons. No energy. No energy. This is wrong. Increases the frequency of photons. How does intensity increase the frequency of photons? No. Increases the frequency of photons? No. Increases the number of photons? Yes. And the kinetic energy of the ejected electrons remains unchanged. Very good. Now is it coming? Now is it all coming together, people? Is it all coming together, people? Yes. Is it all coming together? Yes. Is the all theory coming together and we are able to understand what exactly is happening? Yes. Very good. So this was a JEE Main 2021 question. This was a JEE Main 2021 question. Again, a JEE Main 2024 question. JEE Main 2024 question. Okay. Which figure shows the correct variation of applied potential difference with photoelectric current at two different intensities? People, the intensities are different of same wavelength. That means if the same wavelength, that means same frequency. है ना? If you're same wavelength, मतलब same frequency ना? Yes. Same wavelength, मतलब same frequency. That is what they are saying. This same wavelength, मतलब same frequency. That is what they are saying. Okay. So people, tell me, if different intensities and they have already told that I2 is greater than I1, don't you think that I2 should have more current? I2 should have more current. Yes, I2 should have more current. I2 more current सही है, I2 more current सही है, I2 more current सही है, I2 more current सही है. Okay. Then we have to look into some other things. They have already told same frequency or same wavelength. Different retarding potentials. Wrong. Different. Wrong. Different. Wrong. Same. Sahi. Clear. Now are you all able to understand? Is it becoming easy, people? Is it becoming easy? Yes or no? Is it becoming easy? Yes or no? Very good. Next question. Again, JEE Main 2023. The threshold frequency of the metal is F0. When the light of frequency 2F0 is incident on the metal plate, the maximum velocity of the photoelectron is V1. Okay. When the frequency of incident radiation is increased to 5F0, the maximum velocity of the photoelectrons emitted is V2. The ratio of V1 to V2, we have to find it out. Let's see. People, we already know that kinetic energy max is basically half mass of the electron. Velocity max square is basically energy incident minus the work function. This is basically the formula that I have to use. So I can basically say, that Vm is, this 2 goes over here, m also goes over here. So 2 divided by m square root E minus phi. This is the formula. This is the formula, people. This is the formula. Did you all understood what did I do? Did you all understood what did I do? Did you all understood what did I do over here? Nothing. Just 2 over there, 2 over there, m goes to the denominator, then square root. This is what I get. This is what I get. So people, are you all able to understand the maximum velocity of the electron? So 2 and m being a constant, I can basically say that maximum velocity of the electron is directly proportional to the square root of E minus phi. E minus phi. Yes or no? Yes, sir. So V1 by V2 can be written as square root of energy incident. Threshold frequency is F0, light of frequency 2F0. So this becomes H into 2F0, H into mu minus H into F0. Yes, sir. The whole divided by increase to 5F0. So H into 5F0 minus the H into F0, because threshold frequency remains the same. Threshold frequency remains the same. This is how much? 2 minus 1, that is 1. 1. Yes. So this becomes V1 by V2 is square root of HF naught divided by 4 HF naught. Yes, cancel 1 by 4, that is 1 by 2 for you all. Yes, people. Is it clear? Is it clear? Is it clear? Is it clear? Is it clear, people? Did you all understood this? Did you all understood this? Did you all understood this? Yes. Easy peasy, lemon squeezy. Let's go. Next question. When, okay, JEE Main 2021, again, JEE Main 2021. When radiation of wavelength lambda is incident on a metallic surface, the stopping potential of the ejected photoelectrons is 4.8 volt. If the same surface is illuminated by the radiation of double the previous wavelength, then the stopping potential becomes 1.6 volt. The threshold wavelength of the metal is how much? No problem. We know that, people, that E into V naught, or kinetic energy max is equal to E into V naught, which is basically equal to E minus phi. This is the relation that we know. This is the relation that we know. Yes or no? Okay. Now, people, according to the first condition, the photoelectrons stopping potential is 4.8 volt. So the first equation that we can write is 4.8 EV, 4.8 electron volt, है ना? So 4.8 electron volt is equal to, what is the energy? What is the energy? Can I write this as hc by lambda? Hc by lambda, because lambda is incident, minus the work function phi, okay. Second condition, this is the first equation. Second, according to the second, same surface is illuminated by radiation double the previous wavelength, then the stopping potential becomes 1.6 volt. So this becomes 1.6 electron volt is hc by 2 lambda, है ना, double the wavelength, but the क्या बोलते हैं, work function still remains the same. So this is the second equation. Very good. Now it's very evident. This is 1.6, this is 4.8. I can just multiply this equation by 3. And then equate it to get the answer. So what I do is multiply this whole equation by 3. So what I get? I get 4.8 is basically 3 hc by 2 lambda is basically minus 3 phi. This is what I'm getting. So this equation is equal. Just equate them and you'll get your answer. Let's solve it. So hc by lambda minus phi. So hc by lambda minus phi is basically equal to 3 hc by 2 lambda minus 3 phi. Exactly. Is what it is? Yes. Okay, now we just have to solve this. So 3, so this goes over there. This is 3 minus 5. This becomes 2 phi. This becomes 3 hc by 2 lambda minus hc by lambda. And I give 2 over here. So 2 phi is basically hc divided by 2 lambda. So phi over here is hc divided by 4 lambda. So can I write work function as hc divided by lambda naught? Threshold wavelength. When I compare it, I get lambda naught as 4 lambda. Option. Is it clear, people? I have already told you that I would be practicing a very, very good questions of JEE Main and AIMS and NEET and everything. I've already told you. Is this clear? Can I get some fire in the chat box? If you have understood this? Yes, people. No, option C is not right. 4 lambda is right. 4 lambda. Yes or no? Yes, very good. So basically I can say I can say that everything is getting amalgamated into, you know, a single thing. है ना? Okay. So we are moving into the last part of the chapter. Then I would be giving you a break. Okay. Yes. What is it? Matter wave de Broglie hypothesis. Okay. Now, de Broglie. Okay. So this is the story. Okay. This is the story. है ना? This is the story. De Broglie, he was also studying physics. He went to his physics professor. Okay. So he went to his physics professor and he is like, sir, you know, light is radiation, and so light is both a particle and a wave. Yeah. So professor is like, yeah, yes. So I think matter also is a particle and a wave. Professor was like, you're gone nuts. You have gone nuts. What are you saying? What are you saying? So he's like, de Broglie is like, sir, the momentum of a photon is h by lambda. Yes, sir. And I think so. This is equal to mv. And de Broglie's professor was like, no, he has gone nuts. You're saying something else. But yeah, this was actually true. Why? Because de Broglie was like, if light can show particle and wave nature, in nature there is symmetry. So matter should also exhibit particle as well as wave nature. Okay, are you able to understand this? Because of symmetry in nature, de Broglie was saying that as light can show wave and particle nature, matter can also show wave and particle nature. And that is the reason he equated these two. And from here, what did he get? He got, that is, lambda is h divided by m into v. And this is called as the de Broglie wavelength. So people, so you all will be asking, sir, so what are you saying? Are you saying that when I walk, I also show wave nature? I have a wave coming out of me. Yes, you do. But due to your mass being significantly higher, as you can see, lambda is inversely proportional to mass over here. So greater the mass, less will be the wavelength. So you as an individual, as a human being, you are an enormous mass out there. That is the reason you have very small wavelengths which you cannot see. But subatomic particles like electron, which have very small masses, because of the small masses, they have a significant amount of wavelength. Are you all able to understand this, people? Now, one more thing. Many people get confused due to this waves thing. They think that this is matter waves is an example of electromagnetic waves. But no, this is not an example of electromagnetic waves. This is a separate distinction itself. Are you all able to understand this? People? It's a separate distinction itself. It's not an electromagnetic wave. Electromagnetic wave and matter waves. There are two types of waves, matter waves and electromagnetic waves. Are you all able to understand this? So you do also have a wave nature, but you are not able to see it because you have a much large mass. But electrons, subatomic particles, due to the less mass, you are able to see the wave nature inside it. Are you all able to understand this, people? Are you all able to understand this? Now, I just want to, play with this formula even more. I know that lambda is h divided by mv. Yes, sir. Now, people, in your NLM and everything, you must have learned, see, this is the momentum, right? This is the momentum, that P is equal to mv. है ना? This is basically that you have learned. I'll just square it. So this becomes P square is equal to m square into v square. I'll divide it by 2. So this becomes p square by 2 is m square v square divided by 2. Now I divide by m also. So this becomes m, this becomes m and m gets cancelled. So you get half mv square. Half mv square, this is basically your kinetic energy, which is basically your kinetic energy. So what you are getting that p square divided by 2m is your kinetic energy, or you can also say that p is square root of 2m kinetic energy. Are you all able to understand this? Are you all able to understand this? Yes or no? Yes or no? So people, I can just substitute this thing over here and I'll get h divided by square root of 2m kinetic energy. Clear? Clear? Clear people? Clear people? Why you divided with 2m? I'll tell you. See this. Because I wanted to make kinetic energy. So P is equal to mv, I squared it. So P square is equal to m square v square. Then I divided by 2 to get this half. Then I divided by m because there's an extra m square over here. No, there's an extra m. So I divided it. So I got half mv square. That is kinetic energy. So P square by 2m is kinetic energy. So P is basically square root of 2m times of kinetic energy. I just substitute it over here and I got this. And I got this. Okay. Yes, people. Is it clear? Is it clear now? I can even... Okay. See this. I also know that kinetic energy can also be written as Q into V, E into V naught, charge into potential, Q into V. Yes, I can write this. So I can also write this as H divided by square root of 2mQV. 2mQV. Yes. 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 So this is the main formula that we get. This is the main formula that we get. Now people, if I want to find out lambda for an electron, if I want to find out lambda for an electron, it's very simple. It becomes h divided by square root of 2 times of mass of electron. Charge of electron is E. Charge of electron is E and V is the potential. V is the potential. This is basically the de Broglie wavelength of an electron. De Broglie wavelength of an electron. Now, h is a constant, that is Planck's constant. 2 is a constant, mass of the electron is a constant, E is also a constant. Now you have to remember one value because it eases your calculation. This comes out to be 12.27 the whole divided by square root of V angstrom. Or for better calculations, you can also write this as 150 divided by V angstrom. The square root of 150 is 12.27. That's why. People, is this clear? Is this clear? In the same way, you can also calculate lambda for a proton. So it becomes h divided by square root of 2 times of mass of proton into proton charge, that is E itself, and V. You can also calculate it for an alpha particle. So h divided by square root of 2 m mass of the alpha particle, charge of the alpha particle, that is 2e. And I'll explain why is it 2e, but yeah, I'll explain it in atoms chapter. But yeah, this is how you calculate. Now I've already calculated the values for you all. This is for proton. This is, yeah, so this is for proton that you're getting when you substitute all the values. This is for deuteron that you're getting. What is deuteron? It's an isotope of hydrogen. Alpha particle. Yes, people. Are you all able to understand this? People? Yes or no? Yes. Pakka 100% clear. Is this absolutely clear? Yes, it's already given in your notes. You can, if you want, you can note it down, or otherwise you'll get this PDF. You will get this PDF. Okay. Can I move ahead? Can I move ahead, people? Can I move ahead? Can I move ahead? Can I move ahead? I'm moving ahead. Let's solve some questions regarding this. Let's solve them questions regarding this. It's a very recent JEE Main 2025. JEE Main 2025. Wave theory we're going to study in wave optics. Wave optics. Okay, wave optics. Okay. A proton of mass mp has same energy as that of a photon of wavelength lambda. Okay. If the proton is moving at non-relativistic speed, then the ratio of its de Broglie wavelength to the wavelength of the photon is how much? Is how much? That is what the question is asking. How we remember? You don't have to remember all of these. Mainly, they only ask regarding the electron. But if you can remember the other particles as well, it's very easy. Okay, so it will be helpful for you all. But the main thing that you have to keep in mind is for electron. Okay. Yeah. Then let's solve this. Let's solve this. Let's solve this. Okay. Now, people, can I basically say the de Broglie wavelength of a proton is basically h divided by square root of 2 times of mass of proton into charge of proton into V. Yes, into V. Or also, if I can say that this EV turns out to be the kinetic energy. This is basically the kinetic energy. This is one of the formulas that we derived as well. H divided by square root of 2 mke. Yes or no? Yes, sir. So I have used lambda of proton over here. Now, people, can I write energy of a photon as hc by lambda? Yes, sir, I can write this. So the lambda of a photon, it comes out to be hc divided by E. Hc divided by E. Yes or no? Yes or no? And they've already said they have the same energy. So basically, this kinetic energy, I can substitute it as E over here. Because they have the same energy, E. Now they have told the ratio of de Broglie wavelength to the wavelength of the photon. So basically, I just need to divide this one equation by 2. That's it. So when I do 1 divided by 2, what do I get? H divided by square root of 2 times of mass of proton into E. When I divide this whole fellow, this goes into the reciprocal. So this becomes E divided by Hc. So H and H gets cancelled. This is square root of E. Square root of E into square root of E is E. है ना? Square root of E into square root of E is E. So this E gets cancelled with this E and this becomes square root of E. Yes or no? Yes or no? Yes or no? Now, what do we have here then? What do we have here? We get something like this: lambda of proton divided by lambda of photon as 1 by c square root of E divided by 2 times of mass of proton. Third option. Clear? See, I have solved it ekdam slowly. And yes, people, did you understood it? Yes or no? Yes or no? Clear? I don't think so. You should have a problem over here understanding this. Yes, people? Yes? Okay, let's move ahead. Okay, what is this? Yeah, I'll give break. I'll give break. Only one more topic is remaining, and then I'll give you break. Okay, one more topic, and then I'll give you break. Okay. How did I strike this immediately? Because I've solved many questions, and that is why I'm a teacher right now. If you want to get perfect, you have to solve as many questions. That is it. That's how it gets. Yeah. Okay. An alpha particle, a proton, and an electron have the same kinetic energy. That means they have the same energy. Which one of the following is correct in case of the de Broglie wavelength? I've already told you de Broglie wavelength is h divided by square root of 2 times of m into kinetic energy or E. है ना? They've already told they have the same kinetic energy. That means E is a constant, 2 is a constant, h is a constant. So basically, can I say lambda is inversely proportional to the square root of m? Square root of m. Yes, sir. Now they have told you have to arrange. We have an alpha particle, we have a proton, we have an electron. So we know that the mass of an alpha particle is greater than mass of proton, and it is greater than mass of electron. This we know. This we know. So as this is inversely related, I can basically say lambda of alpha will be less than lambda of proton, will be less than lambda of electron. This is the order that we should have. So electron would have the maximum. Yes, second. JEE Main 2023. Everybody, there is no minimum to the questions, people. There is no minimum to the questions. There is no minimum to the questions. Great. More the number of questions, the better. More the number of questions, the better. Okay. Yeah. Yes, people. Understood? Very good. Now, people, acha, this is please, people, please mark this. Please mark this. Please mark this question. This is a different type of question. Okay, this is a different type of question. See, I have already told you for charged particle. Okay, if I'm talking about a charged particle. Okay, if I'm talking about a charged particle, the de Broglie wavelength comes out to be h divided by square root of 2m into E, that is your kinetic energy, or this is equal to h divided by square root of 2m into QV. Yes. But what about uncharged particle? What about a uncharged, neutral, gaseous particle? What about it? It's a very simple thing. You're gonna learn this in thermodynamics and everything. It's just a small gist that I'm giving you. People, if this is a gaseous particle, this has something called as degree of freedom. And this degree of freedom, we are going to restrict it to 3. That means it can only move in x, y and z axis. Only translational energy it has. Okay, it has only translational energy. That is the reason it has degree of freedom as 3. It can only move in x, y and z axis. So the kinetic energy over here, is 3 by 2 kBT. 3 by 2 kBT. What is kB? kB is your Boltzmann constant. kB is your Boltzmann constant, which you're going to study. Don't worry. Okay, don't worry. Which you're going to study in your thermodynamics. Boltzmann constant. Yes, you can. Okay. Boltzmann constant. Okay, people. And what is this Boltzmann constant exactly? The relation is R is equal to NAC. R is equal to NAC. That's how you can remember it. What is this NAC and all, sir? R is your gas constant. R. PV is equal to nRT R. Na is your Avogadro's number and Kb is your Boltzmann constant. So the ratio of R by Na is your Kb. And T is your temperature in Kelvin. Sir, why you replaced E with QV for a charged one? Was it symbolized for charged one? Where did I replace it, Hasina? The kinetic energy, no Baba? Kinetic energy, I've already told you, this is kinetic energy. Kinetic energy is equal to E into V, Q into V. I've already told you. See this MV, 2M, KE, QV. Yes. Yes. Simple. So what is the lambda over here? The lambda comes out to be h divided by square root of 2 times of your kinetic energy E. 2 times of kinetic energy E. Kinetic energy is 3 by 2 kBt. So this comes out to be h divided by square root of 2m, and this becomes 3 by 2 kBt. So 2 and 2 gets cancelled. So what you get is h divided by square root of 3m kBt. That's it. Yes or no? Yes or no? Understood? That is the final formula. H divided by square root of 3m kBt. Clear? Clear, people? As I've already told you, this is something that you're going to study in thermodynamics, so don't worry about it. But yeah, you can keep that formula in your mind for the uncharged particle. For an uncharged particle. Okay, people? So this, so this question over here, I'm going to give you as, okay, I'm not going to give you as homework. Let's solve it. Okay, let's solve it. No problem. De Broglie wavelength of a molecule in a gas at room temperature 300 Kelvin is lambda 1. If the temperature of the gas is increased to 600 Kelvin, then the de Broglie wavelength of the same gas molecule becomes what? So lambda is basically h divided by square root of 3m kBt. This is what the formula is for an uncharged particle or a gaseous particle. Yes? Okay. Okay. So the so see, they have not changed the molecule, so the mass remains constant. Kb is a constant, 3 is a constant, h is a constant, but they have changed the temperature. So can I basically say lambda is inversely proportional to square root of temperature? Yes, I can say it. So basically lambda 2 divided by lambda 1 is square root of T2, no, not T2, T1 divided by T2. This is what you are getting. So the first temperature is how much? 300. The second temperature is 600. So this becomes 1 by root 2. 1 by root 2. Yes or no? So lambda 2 is basically your lambda 1 times of root 2. Clear, people? Clear, people? Everybody? Everybody, people? Is it clear? Is it clear? Is this understandable? Is this understood? Yes or no? Yes. People, can I get some fire in the chat box? Can I get some fire in the chat box? Can I get some fire in the chat box? Yes, can I get some fire in the chat box? If you have understood this. Then we move on to the last topic. We move on to the last topic. Last topic and then break. Last topic, then break. This is, see, because I don't trust NTA. Okay. I don't trust NTA. That is the reason I am basically making you explain this. Okay. I don't trust NTA because this has been basically removed from your syllabus, but I don't trust NTA. They can do anything. So let's do this. Okay. This is just a setup that I'm going to explain. This is just the setup that I'm going to explain. Okay. This is a Davisson Germer experiment. So this is in this experiment you found out that electron shows wave nature. It confirmed that electron shows wave nature. How did it show? I'll tell you. Okay. How did it show? I'll tell you. So we have a circuit over here, and there is a filament over here, a heated filament. Just a second. Okay. We have a heated filament over here, and this filament is made up of tungsten, W, okay, tungsten. This is made up of tungsten, okay, and this filament is also coated. This is coated with a layer of barium oxide, okay, this is coated with a layer of barium oxide, and this voltage over here is a low voltage supply, Now, thermionic emission is going to take place. Due to thermal energy, electrons will get excited and it will eject out. Electrons gonna eject out of it. Okay. Then we have an accelerating anode over here. This accelerating anode is connected to a high voltage supply. This is connected to a high voltage supply over here. What is the function of this? It is basically going to accelerate the electron. It is going to accelerate the electron and it is going to hit this nickel target. And it's going to deflect. And when it's going to deflect, it will form a diffracted. It will form a diffracted beam, diffraction pattern. And you all know that diffraction is only possible if the electron behaves as a wave. If the electron behaves as a wave. Are you all able to understand? And you can see all of this using a movable detector over here. You can see all of this using a movable detector over here. Are you all able to understand this? Are you all able to understand this? Okay? Yes? Okay? Yes, people? So, okay. And the last one that I want to explain is Bohr's quantization condition, and then I'm going to stop. It's just a one line. That is the electron while circling in the orbit, obviously it shows a wave nature. It shows a standing wave nature over here. So if this is the radius of the orbit r, so 2 pi r, so 2 pi r n is equal to n lambda. This is basically the Bohr's quantization, and we are gonna study this in detail more. Okay, we are gonna study this in detail more. That is the circumference of the radius, sorry, the circumference of the orbit is equal to n times lambda. It is quantized. It is quantized. Okay, people, it is quantized. Okay, and I've already told you that lambda over here is h by mv. Yes sir, it is h by mv. Just substitute, so you get 2 pi r is equal to n h by mv. Okay, so what do you get? Just substitute over here. This becomes mvr is equal to nh by 2 pi, and I think this is something which you have studied in chemistry as well, in atomic structure. Angular momentum is quantized. Okay, okay people. So and yeah, one more thing, one more thing, people, can I just solve one question? Can I just solve one question and then we are done, and then we are done, and then we are done? Can we just solve one question and then we are done? Can we just solve one question and then we are done? Just one more question, just one more question and then we are done. Just one more question and then we are done. Okay people, just one more. This is a question of HCV, of HCV, of HC Verma. And this is the type of question, which is gonna take your marks, which is gonna subtract your marks. Okay, so see this people, very very important, very important. Please mark this question, mark this question. The frequency and intensity of a light source are both doubled. Consider the following statements. The saturation photocurrent remains almost the same. The maximum kinetic energy of the photoelectrons is doubled. Both A and B are true. Both and what is the correct answer? This you have to say. What is the correct answer? This you have to say. Yes. Tell me. Tell me people. Tell me people. Now I know what you are thinking. Now I know what you all are thinking. Sir, frequency of a light is doubled, so maximum kinetic energy also will increase. Yes. Intensity is also doubled, so saturation current should also increase. So this is wrong. If intensity is doubled, so number of photons should increase. Number of photon increases, photocurrent should increase. So this is wrong. And if frequency is doubled, the maximum kinetic energy should be more than double. Should be more than double. It's not just double, it should be more than double. So this is also wrong. So is it D? Is it D? Is it D? Huh? Is it D? How many of you all thought this way? How many of you all thought this way? That sir, intensity is doubled, so saturation current has to increase. So it cannot remain the same. Over here, frequency is doubled, so maximum kinetic energy, we have already studied that, yeah, maximum kinetic energy gets more than double. So this is also wrong. So according to us, it should be option D. It should be option D. है ना? It should be option D. Yes or no? How many of you all think the same way? How many of you all think the same way? Now, Now see the thing. People, see this, okay? See this, okay? I've already told people, I've already told that whenever you're using the relation, see, the relation that you're using is perfectly fine. But in that relation, when the frequency is getting changed, the intensity is constant. And over here, over here, over here, when the intensity is getting changed, the frequency is constant. So one of the thing is constant. Over here, people, both of the things are not constant. Both the things are not constant. Both the things are not constant. I'll tell you. Are you able to understand? So whatever logic you are using, you are correct. I'm not saying you're not correct, but you are wrong in this question. Why? Because both the things are changing. They are variable. They are not constant. You have to use the concept when one of the thing is constant. Are you able to understand it? So in over here, can I basically say n is basically equal to p lambda divided by hc? Yes, sir. Sir, what is power? Can I write power? No, the question was not wrong. The question is not wrong. Okay. Now, very easy. What is intensity? Intensity, sir, is power divided by area. So power becomes intensity into area. So this becomes intensity into area lambda, and this is h into c. H into c. And hc by lambda, I can write it as h into mu. Now people see this. Now people see this. Now people see this. The frequency and intensity of a source are both doubled. Sir, intensity is doubled, okay. Sir, frequency is also doubled, sir. So n value still remains the same. N remains same. Are you all able to understand this? Are you all able to understand this? No, 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 no. The frequency and intensity of a light source are both doubled. They are doubled together, not after one after. They have not told us that one after the other. No, 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 no. They have both doubled together. Are you all able to understand this? N is equal to P lambda divided by Hc. Power is intensity into area, and Hc by lambda is h mu. So intensity is doubled and frequency also doubled. Both gets cancelled out. N remains same. 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 So if N remains same, A is correct, that the saturation photocurrent almost remains the same. But the maximum kinetic energy of the photoelectrons is doubled. No, this is wrong. More than doubled is the answer. More than doubled is the answer. So A is true, B is false. Option B is your correct answer. So this logic you can apply anytime you want. Anytime you want. But this logic, so the logic that you all use, that when frequency is getting increased, the energy is increasing, the intensity has no role in it, that you can use when one of the thing is a constant. But over here, both of them are variable. That is the reason you can't use them. Are you all understood? Yes, did you understand this? Now people, I have given you a lot of practice questions over here, that you can all solve. These are all PYQs over here: 2020, 2017, 2016, 2000, 2010, 2009. I've given you a lot of PYQs over here, so that you can study it. Okay, people. Yes. So we're gonna take a break right now. Yes. Can we come back by 8:30? Sorry, 8:40. Yes. Can we come back by 8:40, people? Can we come back by 8:40? Tell me. Can we come back by 8:40? 8:40? Yes. 8:40? 8:40. Okay, people? 8:40. Yes. 8:40, 30 minutes? 30 minutes? Yes, I think 30 minutes is 30 minutes is more than enough. Okay, you can all freshen up. I will also freshen up. And yes, okay, people. Cool. Okay. Let's move. Let's move. Okay, I'll come back again. Okay, let's meet again at 8:40. Okay. Chalo, bye bye. Yes, guys. Hello, 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 hello. We are back. We are back again. We are back. Hello, 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 hello. Yes, I hope so. I hope so. Everybody has, had a very good break. You drank water and everything. Yes, and had food. Yes, people. Let's start. Okay, let's start. Yes. Hello, 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 hello. Yes. Just confirm. Just confirm whether everything is visible. Sorry, everything is audible. Yes, everything is audible. Is everything audible? Yes, yes. I had a little bit of chotu dinner. Yes, chotu small cute dinner. Yes, yes. Okay. Let's go. Okay. Welcome back. Yes, yes, yes. Let's start. Okay, let's start. Let's start with atoms. Yes, let's start with atoms. Hello, hello, hello. Audible, audible. Let's go, let's go, let's go. Let's have some fire in the chat box. Let's have fire in the chat box and then we're good to go. Let's have some fire in the chat box. Let's have fire in the chat box and also like the session. Okay, like the session, and then we'll start. Okay, and then we'll start. And then we'll start. Okay. ठीक है. Okay. ठीक है, चलो, let's start. So this is Niels Bohr for you. So he is saying chapter is easy, you don't have to worry. है ना, chapter is very very easy, just a little bit of concepts here and there and then you're good to go. The best thing about this is you have already studied about it in quite a detail in atomic structure. So it's a win-win for you all. It's just a revision for you all. Okay. So let's go ahead. So people, this is the question which haunted you all in NEET 2024. If you remember the controversy of NEET 2024, this question, it went to Supreme Court and IIT Delhi professors had to be brought in to answer this question correctly. This was a NEET 2024 question, and because in the old NCERT it was written that all the atoms are stable. In the new NCERT it was written that only some of the atoms are stable. So which of them is right? So IIT Delhi professor was like, physics is right. NCERT theek hai. Okay, just keep it aside. What physics tells us, that is the right thing. So even if you do not know the chapter, let us try to solve this question. Okay, let us try to solve this question even if you do not know how to solve this. Okay, what is the question? The question says atoms are electrically neutral as they contain equal number of positive and negative charges. I think this is something which everybody knows, that atom is electrically neutral. Yes, so I guess statement 1 is right. Yes, I guess statement 1 is right. Second, atoms of each element are stable. Is this correct, people? You already know that obviously all the atoms are not stable. If all the atoms are stable, then how can you explain radioactivity and everything? है ना? Because some of the atoms are not stable, they give radioactive decay. That is the reason you can say that this is wrong. Yes, so statement 2 is false. So so statement 1 is correct and statement 2 is incorrect is your correct answer. So even if NCERT says something else, if both the NCERT say something else, doesn't matter. Physics basically tells us, yes, atoms are electrically neutral, but all of the atoms are not stable. That is what we know. है ना? So chalo, let's start with the flow of the chapter. This is the flow of the chapter that we are going to study. Okay. Chalo, let's begin. Okay. Flow of the chapter. We're going to start with Dalton's atomic theory, then J.J. Thomson's model, Rutherford's gold experiment, Maxwell's electromagnetic theory, Bohr's theory of hydrogen atom, excitation and ionization energy, hydrogen spectra, and a lot of J NEET PYQs. That's what we're going to do. Okay, that's what we're going to do. Okay, that's what we are going to do. So let's start with the chapter. Okay, first we are going to study about Dalton's atomic theory. Okay, and what does Dalton's atomic theory say? Now this is something which you have studied in your earlier classes as well. So let's just revise, okay? So what does Dalton say? Dalton says that every material is composed of minute particles, which is known as the atom, and the atom is an indivisible that it cannot be subdivided into further more particles. That is what Dalton said. So basically, according to Dalton, if you zoom into a particle again and again and again and again and again, finally you reach to the smallest unit, which is called as the atom, which cannot be divided further. But as we all know that this statement is false. Obviously, atom can be divided into further subatomic particles like protons, electrons, neutrons, and further it can be divided into quarks as well, which is not in your syllabus, so we are not touching over there. Okay, we are not touching it. The second, it can neither be created nor destroyed. Obviously, this is very much obvious that you cannot create an atom or you can't destroy an atom. It is always there in the reaction. That is something which is true. Okay, this is atoms chapter. This is atoms chapter. All atoms of the same element are identical physically as well as chemically. That means even if you take an oxygen atom from America or even if you take an oxygen atom from India, both of them will have the same physical and the chemical properties. That is what they're saying. Whereas atoms of different elements are different in properties. I think this is self-explainable. This is self-explainable that different atoms will have different physical and chemical properties. Okay. Okay, people? Yes. Then the atoms of different elements are comparable to hydrogen atoms. So in earlier times, hydrogen was used as a comparative measure. Okay, and we all know that the radius of the heaviest atom is about 10 times that of the hydrogen atom, and its mass is about 250 times that of the hydrogen atom. This is something just for your information. And the atom is stable and electrically neutral. But are all atoms stable? No, all atoms are not stable. Okay, people, that all atoms are not stable. All atoms aren't. Okay, all atoms aren't stable, but they are electrically neutral. Clear? Moving further, now let's understand J.J. Thomson's model. Okay, people. Now this is something. This is a type of model. Yes, like reference. Okay. Now this is a model which you have studied in your previous classes, in your junior classes as well. But I'm gonna basically explain you some of the new things about J.J. Thomson's model. Obviously, I will be revising you with what exactly was the J.J. Thomson's model all about also. Now, the J.J. Thomson's model, he says, what does he say? That the atom as a whole is electrically neutral. This is something which we are able to understand. Yes, it is neutral. How is it able to understand? Obviously, J.J. Thomson said that the atom is an electrical sphere. Okay, it is an electrical sphere with the positive charge present uniformly, on the sphere, and the negative charge of the electrons present in the and the negative charge is basically equal to the positive charge. So basically, if this is the sphere that I'm talking about, this is the atom. This red color, in this red color, the mass and the charge is uniformly distributed. And in the case of watermelon, like watermelon seeds, the electrons are embedded into this positive charge. Okay, people? Is this understandable? Is this understandable, people? Yes or no? Yes. So a positive sphere and the electrons are embedded like a watermelon. Okay, that is why it's also called as the watermelon model as well. Atom, now this is a very important thing. Atom is a positively charged sphere of radius 10 to the power minus 10 meter. This is very, very, very important. That means the radius of the atom can be considered as 10 raised to minus 10 meter, or in the case of 1 angstrom, or in the order of 1 angstrom. The radius of the atom has the order of 1 angstrom. Now, why is this important? Because this I'm going to connect it with the radius of the nuclei as well. I'm going to tell. Okay? And in which the electrons are embedded in between, no problem. The positive charge and the whole mass of the atom is uniformly distributed throughout the sphere. This is something which I've already talked about. Now, what are the shortcomings of Thomson's model? The shortcomings of Thomson's model, every shortcoming is the same, that it could not explain the spectrum. Okay, it could not explain the spectrum, and the scattering of alpha particles cannot be explained with this model. It cannot be explained. I'll be explaining why it cannot be explained. Now, the new thing that you have to know is, that the question is this arrangement stable, or Is this arrangement in equilibrium? Is this arrangement in equilibrium? Or is it stable? That is your question. Okay. So the short answer is yes. Yes, it is stable. Yes, it is stable. This arrangement over here is electrically in equilibrium. That means the net force on the electron, on one of the electrons, is 0. But then what is the problem? The problem is, even if you displace one of the electrons a little bit over here, over here, over here, or over here, if you slightly displace the electron, then this whole thing becomes an unstable model. Are you all able to understand? Are you all able to understand? So this particle right over, this sphere over here is in equilibrium. But if you displace the electron by some distance, this whole system goes unstable and the atom ceases to exist. Are you all able to understand? Clear? Okay. ठीक है? Chalo, moving ahead. Let us understand Rutherford's gold experiment, okay, or Rutherford's alpha particle scattering experiment. Now people, this Rutherford was actually a student of J.J. Thomson. Okay, he was a student of J.J. Thomson, and he was like, okay, my teacher, he could not give me a perfect model of the atom. I think I will be able to give a perfect model of the atom. Okay, I think I will be able to give a perfect model of the atom. And what did he do? So basically, he did not do this experiment. His students, Giger and Martson, Giger and Martson were the one who performed this experiment, and the observations were given by Rutherford. So Rutherford actually told the students to perform this experiment, and the experiment was done by the students, and the observations were given by Rutherford itself. Okay, now what is happening? Let me try to explain the setup over here. Now, the setup is, you have a radioactive substance over here. Okay, you have a radioactive substance over here. This radioactive substance is bismuth or polonium. You can use any of the two, bismuth or polonium, radioactive bismuth or polonium, but you have to go, if you get a question in your exams, you have to go with bismuth. Why? Because in your NCERT it is written that they use bismuth over here. Okay? Okay, people? Yes. In NCERT it is written that they used bismuth. Okay? Yeah. Chalo. Then what happened was, then this radioactive substance was actually covered with a lead box. It was covered with a lead box. Now the functionality of this lead box, I'll try to explain it in some time. Now, due to this being a radioactive substance, it emitted alpha particles. It was emitting out alpha particles. Now, what are alpha particles? Chalo, let me explain. What are alpha particles? What are alpha particles? Alpha particles are nothing but they are nucleus. They are nucleus of the He atom. They are the nucleus of the He atom. So basically, this is helium for you, and if you ionize it, that means if you remove the 2 electrons from the outermost shell, what you get over here, that is helium plus 2, this fellow right over here is your alpha particle. Clear, people? Is this absolutely clear? Yes. So the helium, it has 2 neutrons, 2 protons and 2 electrons. I removed 2 electrons from it, and what you get over here is an alpha particle. So basically it is undergoing alpha decay. We'll be studying about it. So now, right now, what is happening is that this is basically the radioactive bismuth. Okay, this is the radioactive bismuth. Now, obviously, it will be throwing out alpha particles. Everywhere. In random directions, it will be throwing. It would be throwing alpha particles in a 3D direction. Obviously, it would be throwing. But we don't want to waste the alpha particles. We want all of the alpha particles to come in a straight line and collimate and fall into the gold foil. That is what we want. That is the reason we used a lead box over here. So this lead box, it does not allow the alpha particles to spread everywhere. It collects and it collimates. That is the word that is being used in NCERT. Collimates. The audio is, people, can you check the audio, people? Is the audio clear? Particles to spread everywhere. It collects and I think so, it is correct. I think so, the audio is, I think the audio is right. Yes, the audio is right. I think so, the audio is right. It's clear, 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 clear. Okay, okay. Clear, sir. Continue. Okay, okay. So this lead box, it collects all the alpha particles, it collimates all the alpha particles in a straight line. That is what the NCERT uses. That is what the word NCERT, that is what the NCERT uses. Collimates. I'm using the word collimate because I don't want you to be unfamiliar with this word. Collimates. It collects all the alpha particles. It does not allow the alpha particles to, just spread out everywhere. It collects all the alpha particles and the alpha particles move in a straight line. Very good. Now, the NCERT also suggests the energy of the alpha particles. The energy of the alpha particles, was around 5.5 mega electron volt. This was the energy of the alpha particles that was recorded. Okay? Okay. Now we are all able to understand. Now, then this alpha particles, okay, it was subjected to a gold foil. Now Rutherford was a very, very rich scientist actually, so he also got a gold foil. Now the interesting part of this gold foil was that this was very thin, very thin, very thin. The thickness was around 2 into 10 to the power minus 7 meters. That's how thin was. That's how thin it was. Because he only wanted a sheet of gold atoms. He did not want a group of gold atoms. He just wanted a sheet of gold atoms. That is the reason he used a very thin gold foil. And then this thin gold foil was surrounded by a deflection screen. And this deflection screen was made up of zinc sulfide. It was made up of zinc sulfide. Okay, clear. Now what happened? All of the alpha particles, when it crossed the gold foil, many of them got deflected, many of them did not get deflected, many of them turned back. That's something which we're going to discuss after some time. But after it crossed the gold foil, when it touched the zinc sulfide screen, you got this tiny flashes of light, like camera flashes, and these camera flashes were called as scintillations. Are you all able to understand? These were called as scintillations. So when the alpha particles strike the zinc sulfide screen, you got this tiny flashes, like camera flashes, and these camera flashes were this camera flashes were called as scintillations. And by this you were able to know that the alpha particle has crossed the gold foil and has now struck the zinc sulfide screen. Clear? I hope so that you have understood the setup completely over here. I hope so you have absolutely understood. Now I've also bought a cutout of the NCERT as well. Let's read it through so that you can be able to understand that whatever I've explained, you will be able to understand. See, what does it say? 5.5 mega electron volt alpha particles are emitted from a 214 bismuth 83 radioactive source at a thin metal foil made up of gold. Yeah, these are some of the things that we already discussed. Okay. Alpha particles emitted by a bismuth radioactive source were collimated into a narrow beam by their passage through lead bricks. Yes. The beam was allowed to fall on a thin foil of gold of thickness 2.1 into 10 to the power 7 meters. The scattered alpha particles were observed through a rotatable detector consisting of zinc sulfide screen and a microscope. The scattered alpha particles on striking the screen produced brief light flashes or scintillations. These flashes may be viewed through a microscope, and the distribution of the number of scattered particles may be studied as a function of angle of scattering. That is something which we are going to look. Clear? Yes. Is it? Did you all understood the entire paragraph? Yes. Very good. Very good. I can see some fire in the chats. Okay. Moving on. So this is again a schematic diagram what is happening. Now people, what happened was, this is the source of alpha particles being collimated. The gold, it struck the gold foil. Okay. Now what was the observation? The observation was that most of them, it got undeflected. Most of them went past undeflected. Went past undeflected. Only some, okay, only some, I would say that it was getting deflected by some angle theta. It was getting deflected by some angle theta. But of all the alpha particles, if I say 1 out of 8,000 alpha particles repelled back by 180 degrees. That means the alpha particles were coming like this and it repelled back by 180 degrees. Are you all able to understand this? So 1 out of 8,000 alpha particles, they repelled back, or by 1 theta is equal to 180 degrees. Clear? Are you all able to understand this? Okay. Okay. Let's understand now. Now people, one of the observations that they did was only 0.14% of alpha particles of alpha deflected by more than 1 degree. Deflected by more than 1 degree. This is the observation that they did, that for all the particles, of all the alpha particles that were coming over here, only 0.14% of it showed a deflection more than 1 degree. This is called as the scattering angle. This is called as the scattering angle, by how much it is getting deflected. So only 0.14% of the alpha particles that were coming deflected by more than 1 degree. Other than that, all of them got undeflected. And out of them 8,000, 1 out of 8,000 repelled back by 180 degree. Clear, people? Is it absolutely clear? Now, by these observations, how can we say that J.J. Thomson's model failed? Chalo, I'll explain. Chalo. This is the J.J. Thomson's model. This is positive charge embedded. Yes. This is the positive charge which is embedded. This is the positive charge which is embedded. And this blue color are the electrons. Now, when an alpha particle comes over here, due to the positive charge, don't you think all of the alpha particles should have just repelled back? All of the alpha particles should have just repelled back if this was true. But they did not. All of the alpha particles just passed through. And that is the reason Rutherford came up with his own model of the atom. And this is the model of the atom. So, what did Rutherford say? So, according to him, Rutherford said that as all the alpha particles, most of the alpha particles, it went undeflected, he told that most of the atom is an empty space. And all of the positive charge and the mass of the atom is concentrated at a tiny place at the center of the atom called as the nucleus. So in J.J. Thomson's model, the positive charge and the mass was equally and uniformly distributed. But over here, all of the positive charge, all of the mass of the atom is concentrated at a center of the atom called as the nucleus. And the rest is just empty space. And that is the reason all of the alpha particles just went undeflected. But some of them showed a tiny deflection, because when it was near the nucleus, it showed a tiny deflection. Why? Because alpha particle is also positive, nucleus is also positive. That is the reason they showed a little bit of repulsion, and due to that, deflection. Understood, people? And when I said that 1 out of 8,000 alpha particles repelled by 180 degrees. So when the alpha particles, one of the alpha particles came over here, head-on collision with nucleus, it just repelled back by 180 degrees. That's what happened. And that is the reason Rutherford came up with this planetary model of the atom. Clear, people? Clear? Yes. Chamka, kya baat hai? So Rutherford's model of the atom. So electrons, now see, electrons revolve around the nucleus in circular orbits. This is something which we are familiar. And now we all know that the electrons revolve around the nucleus in circular orbits. Rutherford in 1911 proposed a new type of model of the atom. According to this model, the positive charge of the atom, instead of being uniformly distributed throughout a sphere of atomic dimension, is concentrated in a very small volume at its center. At its center. Now, I'll explain. This central core is now called the nucleus and is surrounded by the clouds of electron, making the entire atom electrically neutral. Now, people, as I said, people, the radius of the atom was calculated as 10 to power minus 10 meter, that is 1 angstrom, and the radius of the nucleus, it was calculated as 10 raised to minus 15 meter or 1 Fermi. If you see, there is a difference of 10 ki power 5, 10 raised to 5. There is a difference of 10 raised to 5 meters. If you multiply this by 10 raised to, if you multiply this by 10 raised to 5, that's when you will get radius of the atom. So just imagine, it's something like this. If in a football stadium, you place a green pea matar, okay, matar ka dana, a green pea in the center of the football field, that is your nucleus, and the rest of the entire space is the atom. That is exactly the difference between them. That is exactly the difference between them. Are you all able to understand this, people? Are you all able to understand this? The atom is empty space, just empty space. Just empty space. Clear? Yeah, we'll do questions, don't worry. Do like the session, people. Now, again, why could not matter, that is green pea, matter is green pea, okay, green peas, okay. Okay, again, why could not explain? Again, could not explain the stability of the atom. Now, why could not it explain the stability of the atom? This is something that we're going to look in future. So Maxwell's electromagnetic theory, it disproved this, okay. Maxwell's electromagnetic theory. Okay. Now, again, it could not explain the discrete nature of hydrogen spectrum. Every model, it could not explain the nature of hydrogen spectrum. Okay, let's understand now. Okay, now distance of closest approach. Okay, distance of closest approach. People, very, very easy to understand. Very, very easy to understand. Okay, people, see this. If this is the nucleus, if this is the nucleus that I'm talking about, okay, this is the nucleus. This is the nucleus, and this is the alpha particle that is coming. This is the alpha particle that is coming with v velocity. Okay, this is the alpha particle that is coming with v velocity. People, what is impact parameter? Impact parameter is basically the perpendicular distance between the initial velocity vector and the nucleus. Chill, I'll explain. Let's see. That means, what is impact parameter? Impact parameter is basically, this is the initial velocity vector of the alpha particle. If I extend this line, okay, this is the dotted line, I have extended this line. This is the nucleus, I have extended this line also. What is the impact parameter? Impact parameter is basically the perpendicular distance between what? Between the center of the nuclei, the center of the nucleus, and also this initial velocity vector. This perpendicular distance is called as the impact parameter, and we denote it by B. Are you all able to understand this? Yes, this is useful for 12th board. Yes, at a certain r from the nucleus, the alpha particles closer. Okay. This is distance of closest approach. Where is? Acha, impact parameter. See this. This is impact parameter. So just a second. I'll just. Okay, no issues. So see this. So if you all notice, this is the alpha particle's trajectory. So this is the initial velocity vector. Hai na? This is the alpha particle. This is the center of the nucleus. So the distance between the center of the nucleus and the perpendicular distance between the initial velocity vector, that is basically called as the impact parameter. Now people, very easy to understand. Very, very easy to understand, people. Can I basically say the impact parameter B is inversely proportional to deflection or the scattering angle? Can I basically say this? That means That means lesser the distance, greater the deflection. More the distance, less the deflection. Obviously, that is something that we can say. Okay, okay, people. Or even I can say it is 1 divided by theta, that is the scattering angle. The scattering angle. Okay. So the impact parameter is the perpendicular distance of the initial velocity vector of the alpha particle from the center of the nucleus. Simple. Where to find notes? Where to find notes? It will be on my Telegram channel. On my Telegram channel, you can all find it over here. You can scan it. You can scan it if you want to, and you can find it out. Okay. Now distance of closest approach. Let us try to understand what is distance of closest approach. Okay. Now people, see, very important. Okay, very important. See this. See this, people. This is the alpha particle which is coming. This is coming with some initial velocity v. This is also a positively charged nucleus. So obviously this alpha particle will have a repulsive force over here. It will experience a repulsive force over here. So velocity over here, force over here, obviously it will have negative acceleration, hai na? And as the distances keep on decreasing, as the distance is keeping on decreasing between the nucleus and the alpha particle, the force will grow even more. The force will grow even more. And at some point, the alpha particle just stops and reverses the direction and turns back again, and turns back again, and turns back again. So, what is distance of closest approach? Distance of closest approach is the minimum distance that the alpha particle and the nucleus, the distance between the nucleus and the alpha particle, the minimum distance, that is called as the distance of closest approach. Are you all able to understand this, people? Are you all able to understand this? Yes or no? Yes or no? Yes. So, can I basically say, okay, yeah. So can I basically say something like this? See this. If this is the nucleus that I'm talking about, it has positive charge over here. This is the nucleus. This is the nucleus. And this is the alpha particle. This is the alpha particle. Now this alpha particle over here, right over here, has an initial velocity of v. How much time? Let's see. I don't know right now. It has an initial velocity of v. So this alpha particle right over here, it comes and it stops over here, and it again reverses its direction and goes back. So this distance, so over here I can definitely say, the final velocity becomes 0 and it reverses back the direction. So this distance is called as the distance of closest approach. This distance is called as the distance of closest approach. Okay. Now people, let's understand it over here. How to find out this r distance? It's very simple. Can I basically say that it's very easy. But this alpha particle had some kinetic energy. Yes sir, it had some kinetic energy. And over here, the velocity is 0, the kinetic energy is now 0. Now where did this kinetic energy went? It all gets converted into potential energy. So I will basically say that all of the kinetic energy gets converted into the potential energy. You can also derive it by total mechanical energy conservation, but we have not done work energy power. That is the reason I'm using this method. So all of the kinetic energy of the alpha particle gets converted into the potential energy of the system. Clear, people? So kinetic energy will be half m v square, which is basically equal to k q. What is q? Again, alpha particle. What is the charge of the alpha particle? It's a helium 2 plus. It has a charge of 2 plus. So 2 plus meaning 2 into E, hai na? 2 into E, that is charge. 2E, K, Q1. Q2. What is Q2? Nucleus. What is nucleus? The charge of the nucleus. The charge of the nucleus, let it be ZE right now. ZE right now. I'll explain it later. Okay, I'll explain it later. Z into E. Z into E divided by R. Divided by R. Cool, people? Cool? Are you all able to understand this? K, Q1, Q2 divided by R. Okay? So this is basically the potential. This is basically the potential. So from here, we are able to understand that R is basically K 2E ZE divided by, this is becomes 2 over here, this is M over here, and this is V square over here. This is a relation that we are getting, but the main important relation is that the distance of closest approach is inversely proportional to the mass. Inversely proportional to the mass. Mass of the alpha particle. Mass of the alpha particle. Clear? Clear, people? Understood? Okay. If you understood this concept, please, can I have some fire in the chat box? If you understood this concept, can I have some fires in the chat box? Okay, chalo, let's move ahead. Okay, so as I said, so this is not something that you have to keep in mind. This is just for observation. As I said, see, the experimental finding shows that only 0.14% of the incident alpha particles are scattered by more than 1 degree. Yes. Okay, and this is the graph that they got. So this orange line is basically the theoretical prediction that we did. And by experiment, we got all the points on the same line. So we were right about it. Okay, clear? So take it. Now people, this is the graph that we got for the number of particles scattered, and this is the degree by which it's scattered. Okay people, so this is a very easy question. Graph which depicts the results of Rutherford's gold foil experiment with alpha particle scattering. Again, this is a JPYQ over here. What is your answer? It's a very simple. This is your answer. We just looked at it. This is the graph that you get, like an hyperbole, and this is the graph that you get. Okay people? Yes, option C is your right answer. Okay, moving ahead. When an alpha particle of mass m moving with velocity v is bombarded on a heavy nucleus of charge Ze, its distance of closest approach from the nucleus depends in m as what? We've already studied this, people. We've already studied this. Where is it? Yes, we have already studied this, that the distance of closest approach is inversely proportional to 1 by m. Inversely proportional to m. So the correct answer over here is option A. Again, a JE PYQ. JE and NEET PYQ. Clear? It's not a hyperbola, but it's like a hyperbola. Okay, it's not a hyperbola, it's like a hyperbola. Next. Okay, I want the answer of this. This is a JE 2018 question. JE 2018 question. JE 2018 question. What does the question say? Most of the mass of the atom and all its positive charge are concentrated in a tiny nucleus, and the electrons revolve around it. It is the Rutherford's model. And I think so this is a correct approach. Yes, I think this is correct. Statement 1 is correct. Hai na? Because Rutherford model says all of the mass and the positive charge is concentrated at the center of the atom called as the nucleus. An atom is a spherical cloud of positive charge with electrons embedded in it is a special case of Rutherford's model. No, it is not. This is a special case. This is a case of J.J. Thomson's model. Hai na? It is a case of J.J. Thomson. J.J. Thomson. So, statement 1 is right, statement 2 is wrong. Statement 1 is true, statement 2 is wrong. Yes. Option B. Yes. Not A. Why A? Why A? It is not a special case. Why A? It is not a special case, no? They are basically describing the J.J. Thomson's model. Okay, clear? Clear? And yeah, you can all call me Anna also. Yes. Yes, I will give time. Don't worry. Malini, to all those who are watching, don't worry, you will get this PDF. My handwritten notes you will get, along with extra questions as well. You don't have to worry about the notes. Right now, you just focus on the explanation. Okay, you just focus on the explanation part. Try to grasp the concept as soon as possible. Then you can give time for your notes as well during your self-study. Okay. Okay, people. Yes. See, you are all able to solve J questions as well. See, I've already told you that I will make you fall in love with physics. Okay. Chalo. Choose the correct option. Yes, you can all call me Anna, Chetan, Chetai, Cheta. Okay. 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 So let's see. Okay. Just a second. Let's see. Let's solve. Okay. Let's solve. In the ground state of Rutherford's model, we have to say, acha, choose the correct option. Okay. In the ground state of Rutherford's model, electrons are in stable equilibrium. While in Thomson's model, electrons always experience a net force. I don't think so. They don't always experience a net force. I've already said J.J. Thomson's model is in stable equilibrium until and unless you basically displace an electron. Yes or no? Yes or no? Yes or no? So this statement is wrong. While in Thomson's model, electrons always experience net force. This is wrong because in J.J. Thomson's model, in the same model, obviously they are in equilibrium until and unless you just displace the electron. Also, this statement is also wrong that they are in stable equilibrium. This statement is also wrong because if you know a little bit of circular motion, you always know that the force is always directed towards the center. A net force is always directed towards the center, the centripetal force. So how can it be in stable equilibrium? How can it be in stable equilibrium? Did you get it? Yes. So this is wrong. An atom has a nearly continuous mass distribution in Rutherford's model. Is it so? No, it is not. It is true for the case of J.J. Thomson's model. Continuous mass, uniform mass distribution for J.J. Thomson's model. For Rutherford's model, it's not. It's a non-uniform mass distribution. All of the mass is concentrated at the center itself. It is wrong. It is wrong. Yes. Classical atom based on Rutherford's model is doomed to collapse. And the positively charged part of the atom possesses most of the mass in Rutherford's model, but not in Thomson's model. I think so D is the correct option. Why C is wrong, you'll come to know later. Why C is wrong, you'll come to know later. But I think so D is the most appropriate of it. Yes, people? Yes. Moving on. Now let's understand Maxwell's electromagnetic theory. Now let's understand Maxwell's electromagnetic theory. Now people, as I said it over here, that why Rutherford's atomic model could not explain the stability of atom. That's where Maxwell's electromagnetic theory comes in. Okay. Now Maxwell also was a very good scientist back those days. Okay. Okay. Now Maxwell also was a very big scientist those days. So when Rutherford gave his model, Maxwell was like, bro, buddy, hey buddy, I have a problem with your model, buddy. There's a big problem with your model. Let me say. Okay. Now what was Maxwell's electromagnetic theory? Let me explain. Okay. Let me explain. Yeah, it's a good hairstyle to have, no? It's a good hairstyle to have. It's a good. Okay. What does Maxwell's electromagnetic theory say? It says that when a charge is at rest, what does it produce? Sir, according to the limited knowledge that we all have, a charge at rest, it produces an electric field. I think this is something that we all can agree with. This is something that we can all agree with. Yes or no? Yes or no? Yes, sir. Sir, but when the same charge, sir, starts to move with some velocity, but which is a constant velocity, sir. At this point, this charge, it produces an electric field as well, plus a magnetic field as well. Yes or no? Yes or no? Yes or no? Now, if the same charge over here is right now getting accelerated by some acceleration A, at this point people, it emits electromagnetic waves or electromagnetic radiation. Did you all understood this, people? Did you all understood this, people? That means if a charge is at rest, it produces an electric field. If it is moving with constant velocity, it produces electric field as well as a magnetic field. But if it is accelerating, it emits electromagnetic waves or electromagnetic radiation, which is basically it emits energy out. It emits energy out. Okay, it emits energy out. Am I clear? Am I clear that it emits energy out? Okay, this is the most important part of it. Now we're coming back to electromagnetic theory. Now, according to Maxwell, sir, what is happening? If this is the orbit that I'm talking about, and this is the nucleus. This is the nucleus, okay? This is the nucleus, positively charged nucleus. And I have an electron, which is, electron which is rotating, which is revolving around this nucleus. Okay, people? Yes. Now tell me, people, this, and let's assume the radius to be r, okay? The radius to be r. Now tell me, this electron right over here, this electron right over here, is this charge accelerating or not accelerating? Is this accelerating or not accelerating? Yes or no? Is this accelerating or not accelerating? Come on, tell me. That this electron right over here, it is moving with some velocity v as well. It is moving with some v velocity as well. Hai na? Is this electron accelerating or not accelerating? Accelerating or not accelerating? Tell me. Tell me. Accelerating or not accelerating? Come on, I need answers from your side. I need answers from your side. See, it is accelerating. Okay, now for all those who have confusion right over here, I'll tell you. What is acceleration, people? Acceleration is rate of change of velocity. That means even if you change the magnitude of speed or change the direction, it is accelerating. It is accelerating. Did you all understood? Did you all understood? It is accelerating. It is accelerating. You have all studied in uniform circular motion that what is acceleration? Rate of change of velocity. In every point, the direction, the direction of velocity is keep on changing. It is kept on changing. It's keep on changing. So obviously this particle is accelerating. Obviously it is accelerating. No tangential acceleration because it is uniform circular motion. The speed is not increasing. Are you all able to understand? Yes. So because the direction is kept on changing because of the centripetal acceleration, that is v square by r. V square by r. Yes or no? Okay, so it is in uniform circular motion. It has constant speed, but but the velocity keeps on changing its direction. And as the velocity is changing, it is accelerating. It is accelerating. So people, you have a charge which accelerates, so it emits electromagnetic waves or electromagnetic radiation. So I have a charge over here which is accelerating. So it will emit energy. It will emit energy. It will emit energy. It will emit energy. And obviously, this electron does not have an infinite source of energy. So this electron will just spiral down and collapse into the nucleus. And this model, that is Rutherford's model, will cease to exist. Will not exist. Are you all able to understand Maxwell's electromagnetic theory? Did you all understand electromagnetic theory of Maxwell? Clear? Let's see this. Okay. Now, what does it say? According to the classical electromagnetic theory, an accelerating charged particle emits radiation in the form of electromagnetic waves. This energy, or the energy of an accelerating electron, should therefore continuously decrease. Yes. Okay. The electron would spiral inwards and eventually fall into the nucleus. Thus, such an atom cannot be stable. See, like something like this, zoom, 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 brush, khatam. Okay. Now, one more thing that I have to say. People, see, we have already studied that this electromagnetic wave has an energy E is equal to h mu. Yes or no? It has a frequency also. This mu is its frequency. So basically, the energy which is emitting has a frequency mu. Okay. One more thing. Okay. Okay. So this energy also has a frequency. Now, according to the classical electromagnetic theory, people, do you all know that this circular motion as well, that, okay, I'll just draw it over here. That is, if a particle is performing circular motion, if a particle is performing circular motion V, uniform circular motion, it also has a frequency. Obviously, it has a frequency. What is the frequency? Frequency is basically V divided by 2 pi r, if r is the radius. If r is the radius, this is the frequency of revolution. This is the frequency of revolution. Now, according to classical electromagnetic theory, a charged particle which is accelerating will emit electromagnetic radiations. And the second thing according to the classical electromagnetic theory is the frequency emitted by the charged particle, or the frequency of the electromagnetic waves emitted by the charged particle should be equal to the frequency of revolution of the charged particle. Are you all able to understand, people? Are you all able to understand what I'm saying? I'm saying it again. That means, according to classical electromagnetic theory, the frequency mu of the electromagnetic wave should be equal to the frequency of the charged particle revolving in circular motion. That is V divided by 2 pi r. This should also be true. Now, people, now comes the most interesting part. People, if this electron is spiraling down and down and down and down and down, the radius keeps on decreasing. Yes, sir. If the radius keeps on decreasing, the frequency would change. Yes, sir. Sir, if this frequency would change, the frequency of the electromagnetic wave also should change. That means I should be able to see different frequencies of electromagnetic radiations getting emitted. Yes or no? Again, I'm repeating it. If the electron is spiraling down the nucleus, the radius is decreasing, the frequency would increase, and if the frequency is increasing, the frequency of the electromagnetic wave should also increase. So I should be able to see different frequencies of electromagnetic radiation. Yes or no? I should see a spectrum. I should see violet, indigo, blue, green, violet, orange, red. As the frequency is changing, I should see all of the spectrum. I should see all of the colors. But I'm not getting it. I am only getting what? I am only getting a line spectrum. That is, only discrete frequencies I'm getting. So it is going against this also. I'm not getting a spectrum, I'm getting discrete frequencies. Is it clear? I'm getting discrete frequencies. So there is a problem. So Maxwell was like, buddy, Rutherford, your model cannot explain my Maxwell's electromagnetic theory. It is not able to answer my question. How are you able to understand or explain the stability of the atom? An accelerating charged particle will emit electromagnetic radiation and it will fall into the nucleus. And also, the frequency of the electromagnetic radiations emitted should be equal to the frequency of the charged particle revolving around the nucleus. And it is not happening, buddy. So your model has a problem. Thank you. So he was the scientist, who questioned Rutherford. Then comes this guy, Niels Bohr. Okay. Then comes Niels Bohr. Okay. Niels Bohr was a student of Rutherford. He was also a student of Rutherford. And he was like, no, buddy Maxwell, you can't question my teacher like that. I will prove you wrong. Okay. I will prove you wrong. Okay, no, no, you can't. Okay, you can't. You can't. I will prove you wrong. Okay. So obviously, as Niels Bohr was also a student of Rutherford, he also took some postulates from Rutherford's experiment as well. And you will see that some of the things that are written over here, Rutherford also said also. But yeah, some things are also new in this thing. Okay, let's understand Bohr's theory of hydrogen atom. What does it say? It says an electron in an atom moves in a circular orbit about the nucleus under the influence of Coulomb force of attraction between the electron and the nucleus. If you can see, this statement is same in Rutherford's model atom as well, that the electron in an atom moves in a circular orbit. Then the next part is something new. So what is happening? This is an hydrogen atom. Okay, let's see that this proton has some charge Ze. Okay, this has some charge Ze. Okay, and this is the electron. This has some charge E, and it is traveling with some velocity v or some speed v, and the radius between them is r. Okay, now as I said, for any particle to move in a circular motion, there is one acceleration which has to be there. It has to be there, mandatory. That is centripetal acceleration or the centripetal force. Okay, okay. I'll see Chaitanya. After this chapter, I'll be able to tell. Okay. So what I'm saying, that for any particle to be in circular motion, there has to be one acceleration which has to be mandatory, which has to be there. And that acceleration is the centripetal acceleration or the centripetal force. And this centripetal force is being provided by the Coulombic force of attraction, which is present between the proton and the electron over here. Are you all able to understand? So the centripetal acceleration is provided by the Coulombic force between the nucleus and the electron. So basically, can I say that mv square by r, that is the centripetal force, is provided by k q1, that is k q1 q2 by r square, that is k q1 q2 divided by r square. Yes or no? Yes or no? Can I say something like this? Yes sir, you can definitely say something like this. So r gets cancelled out, mass goes over there, so I get v is square root of kze square divided by mr. So this is the velocity or the speed of the electron. Clear? Are you all able to understand this? Simple. Okay. Okay, so now some more postulates. Now people, you have to understand that Bohr already said that whatever postulates that I am giving, it is only valid for isoelectronic species or hydrogen-like species. I'm telling you, Divina. I will answer that question a little later. Okay, I will answer that question a little later. Isoelectronic species. Iso means one. Okay, iso means one. So one electronic species or hydrogen-like species. So basically, hydrogen has only one electron. है ना? Hydrogen has only one electron. Then helium plus, lithium 2 plus, beryllium 3 plus. है ना? These are all hydrogen-like species or isoelectronic species. Yes or no? So we can only use his postulates for these species. This species. Okay. Now let's move ahead. What is the second postulate? The second postulate says only those orbits are possible for which the angular momentum of the electron is equal to an integral multiple of h by 2 pi. So basically he says, now let me define a new quantity over here. That is the angular momentum. Mass into velocity, mass of the electron, velocity of the electron, radius of the orbit in which it is orbiting is equal to some nh by 2 pi. Now people, let me give you a feel about it. What? Okay. Let me give you a feel about it. People, mass of the electron is fixed. Yes, sir. Sir, is the speed also fixed for an electron in an orbit? Yes, sir. It is fixed. Sir, is the radius also fixed for an orbit? Yes, it is fixed. So if all the three quantities are fixed, shouldn't the right hand side also be fixed? That is the reason he said that all of these three quantities clubbed together will give me a product which is an integral multiply. Obviously, if I change the velocity and radius, I'll get a new value, but it would be an integral multiple over here. Are you all able to understand this? Are you all able to understand this, people? Mass is fixed, velocity of an electron for an orbit is fixed, radius also is fixed for an orbit. So obviously this value also has to be fixed. This is the second postulate. We'll come back to this later, don't worry. Okay, now people, now very important, very important. So what did Maxwell say? Maxwell was like, duration, let's see, 4 hours or something, 4 hours or something, okay, 4 hours or something, okay. See this. Maxwell was like, buddy, Rutherford, and if an electron is traveling in an orbit, it is accelerating, it will emit electromagnetic radiations. Niels Bohr is like, buddy, you come over here. Maxwell, I'll tell you. According to my model, electrons will only revolve in certain stationary orbits. And if the electrons revolve in those stationary orbits, electrons will not emit electromagnetic radiations. And I repeat again, Niels Bohr said, in my model, electrons will revolve in those stationary orbits, and in those stationary orbits, electrons will not emit electromagnetic radiations. And those stationary orbits should follow this relation. The angular momentum should be an integral multiple of nh by 2 pi. Are you all able to understand this? Are you all able to understand this? Now, coming back. People, say something like this. This is the nucleus. This is the first orbit that I'm talking about. This is the second orbit that I'm talking about. This is the third orbit that I'm talking about. Okay? Just for an example. Okay? Just for an example. For an electron to revolve in the first orbit, the electron should have 10 rupees. For an electron to revolve in the second orbit, it should have 30 rupees. For in the third orbit, it should have 50 rupees. Okay? This is just an explanation. Just an explanation. Okay, people? So that means, okay, if the electron is over here, okay, in order, so if the electron, now the electron has 10 rupees, it has 10 rupees. It is following integral multiple of nh by 2 pi or integral multiple of h by 2 pi. It is revolving around this orbit, so it is not emitting radiation because it is following L is equal to mvr is equal to nh by 2 pi. It is following, okay, but it wants to jump, he wants to jump over here. He wants to jump over here in the second orbit. But in order for him to revolve in the second orbit, he needs to have 30 rupees. That means I will have to give him 30 rupees. I will have to give him more 20 rupees. I'll have to give him 20 rupees. So I give this fellow, I give this fellow 20 rupees more. And because of this, this electron jumps over here. This electron jumps over here and he revolves in this orbit. Because right now, he has 30 rupees in total. He has 30 rupees in total. Are you all able to understand this? Now, electron is like, no, sir. I want to go in this orbit. But he has only 30 rupees. He wants total 50 rupees. So, I give him more 20 rupees. 20 rupees. Now, right now, he has 50 rupees. So, he can jump over in this orbit and can revolve over here. Are you all able to understand this, people? Are you all able to understand this? Now the electron is over here. Electron is like, okay, I am, ho gaya yaar, I am satisfied. I want to go back to my home. So home, in order for him to revolve in his home orbit, he needs 10 rupees. But he has 50 rupees. So he has to give out 40 rupees. And then he can jump back to his home orbit. Clear? Yes, rupees are energy. Rupees here are energy. Clear, people? Clear, 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 clear. Yes or no? Yes. Are you all comfortable with this, people? Are you all comfortable with this? Okay. Yes, it will be available. Okay. So that means, people, that means, what is this? The electron moving in such allowed orbits. What is the allowed orbit? Called as the stationary orbit, which follows the angular momentum conservation, does not radiate electromagnetic radiations. Thus, the total energy of the electron revolving in any of the stationary orbits remains constant. Yes, it was constant. It was 10 rupees over here. It was 30 rupees over here. It was 50 rupees over here. It was not changing. It was not changing. Next, electromagnetic radiations are emitted if an electron jumps from a stationary orbit of higher energy E to another stationary orbit of lower energy E. The frequency of the emitted radiation is related by the Ruko. Chill. Now let's try to understand. Okay, just a second. If I just copy this fellow, okay, I'll have to copy this. Okay, I've just copied it. Ari. So right now, okay, just a second, guys. Hana? I'll just keep this clean. Okay, see this. Okay, see this. So the first orbit is at energy E1. The second orbit is at energy E2. The third orbit is at energy E3. Okay. Now, the electron is in the first orbit. Will it emit radiations? No, it will not emit radiations, as it is following the angular momentum conservation. L is equal to mvr nh by 2 pi. It will not emit electromagnetic radiations. But if he wants to move to E2, so over here, E1, E2, this is the relation. He only has E1 energy. He needs E2 energy to revolve in this orbit. So obviously, this fellow has to receive how much energy? He has to receive E2 minus E1 energy. That is the extra energy. Yes or no? That is the extra energy which is required. And when it will receive this extra energy, he can basically go over in this orbit. And he can revolve. Are you all able to understand this, people? Are you all able to understand this? Now again, if he wants to travel in this third orbit, he only has E2, he needs E3. So obviously, he will receive how much? He will receive E3 minus E2 energy. So he has E3 energy right now, he can jump over here. Energy absorbed. Now he is like, ho gaya, I'm satisfied, I want to return back. So he has E3 energy right now. He only wants E1. So he will release how much? He will release the extra E3 minus E1 energy. And he would go back to his home country or home orbit and revolve. That is what is happening. Now, this energy which you are giving, it can be of many types. First, it can be thermal energy, or it can be photon. It can be thermal energy or it can be photon. Yes or no? So can I basically say, people, that this E2 minus E1 is basically delta E energy, and this energy will be provided by a photon of h mu or hc by lambda. Yes or no, people? Yes or no, people? Yes or no? So that means this electron will need E2 minus E1 energy, or a photon of energy h mu or hc by lambda, which is equal to E2 minus E1, to go from E1 to E2 and revolve in the second orbit. And in the same way, if this fellow, if he's in the third orbit, he wants to go back to his E1 orbit. So the amount of energy that will get released is E3 minus E1, and this will be again equal to delta E, and this will be again equal to h mu, and this will be equal to hc by lambda. So a photon of energy E3 minus E1 or h mu or hc by lambda will be released over here. Is this clear? Is this clear? Is this clear? So that is what is written over here. That is what is written over here. Yes, people. Okay. I hope so. I hope so. You are able to understand each and everything. I hope so. You are able to understand each and everything. So right now, the first orbit is called as the K shell. You already know this. You have studied it. You have studied in your chemistry. That is K shell, L shell, M shell, N shell. So this is N is equal to 1, this is 2, this is 3, and this is 4, and so on. You have already studied. Okay, you have already studied. Okay, you have already studied. Okay. Now, demerits of the Bohr model. Okay. Demerits of the Bohr model. These are some of the demerits of the Bohr model, and I think you should all know it. And now let's understand. Shortcomings of the Bohr model. Now, this model could not explain the fine structure of the spectral lines. This model could not explain the fine structure of the spectral lines. Now, what exactly is this? What exactly is this? Now, you get some spectral lines. What are these spectral lines? I would be explaining them. I would just show you the diagram or something. These are the spectral lines. Okay, these are the spectral lines that you will get. Okay, this is the spectral lines that you will get. Now, what the Bohr model could not explain? What the Bohr model could not explain? Let me just explain it to you. It could not explain the fine structure of the spectral lines, and also the Zeeman effect and Stark effect. What is Zeeman effect and Stark effect? I'll just explain it to you. The splitting of spectral lines, splitting of spectral lines due to electric field and magnetic field is called as Zeeman effect and Stark effect. You don't have to basically go into deep details of it. You just need to know what is the definition basically. So due to when you apply electric field and magnetic field, the spectral line starts splitting, and this splitting is called as the Zeeman effect and the Stark effect. Okay, is this clear, people? Okay. Now, what is Zeeman effect? Zeeman effect is basically due to magnetic field, and due to electric field, it is called as the Stark effect. That's it. That's it. Okay. Next. Now coming to the question, I think somebody in the chat asked me, why only for hydrogen atoms? Why only for hydrogen atoms? Okay, why only for hydrogen atoms? This is the answer. This model is only valid for single electron systems. Why? It is very easy to understand. People, if you understand hydrogen over here, so this is the hydrogen nuclei. This is the hydrogen nuclei. It has only protons. It has one proton over here, no neutrons. And it has one electron in its orbit. It has only one electron in its orbit. Now, while Bohr was studying, he was like, buddy, it is very easy to understand the relationship between one electron and one proton. As soon as you add one more orbit, and there is one more electron inside it, you have to consider the relationship between these, the repulsion between these two electrons, the attraction between this one proton and this electron. There are many relations happening right now. There are many relations happening. Yes or no? Yes or no? There are many relations happening, and it is very difficult. Just a second, guys. Just a second. My mic just dropped. 4 hours. Yes, it will become more complex. So Bohr was very smart. You know what he said. You know what he said. I've read one of the research papers. I'm basically just paraphrasing it. He is like, I I made your life simple. I studied proton electron relations. I did it for isoelectronic species. I did my part. Now the rest of the world, it's your responsibility to find out for more complex relations. That is exactly what he said. Okay. That is exactly what he said. Okay. So it cannot explain electron-electron interactions. Okay. The model is based on circular orbits of electrons, whereas in reality there is no orbit. Obviously, you have studied it in chemistry that there are actually no orbits. There are orbitals. There are orbitals, and inside these orbitals, you find out the probability of an electron existing in these orbitals. है ना? You have node and everything. है कि नहीं? है कि नहीं? You have node and everything. Okay. So obviously there are no orbits. In reality, there are orbitals. So again, electron is presumed to revolve around the nucleus only, whereas in reality motion of the electron cannot be described. Again, Heisenberg uncertainty principle. This is Heisenberg uncertainty principle. What it's saying? It is basically saying, according to Heisenberg uncertainty principle, we all know that the position of the electron cannot uh, cannot be found out if you know the velocity of the electron, or if you know the velocity of the electron, you do not know the position, or if you know the position, you do not know the velocity of the electron. है ना? So it cannot be explained. This model could not explain the intensity of spectral lines. So basically the intensity, the bright and the dark fringes that you are getting, the dark and the white lines that you are getting, it could not explain. Now, it could not explain the doublets obtained in the spectra of some of the atoms. Now, what are these doublets? Doublets is basically, for example, in some atoms like sodium, in sodium atom, the spectral lines that you are getting are very close, are very close, very close. So Bohr was not able to explain that doublet. Okay. Bohr's model is semi-quantum model. It means it includes two quantum numbers E and L, but unfortunately considers circular motion of the electron. Now I'll tell. Okay. So Bohr is like, first of all, Bohr told Maxwell, है ना? Bohr is like, Maxwell, see buddy, whatever electromagnetic theory you are just throwing at me, है ना? You're throwing at me. It's all well and good. It's all well and good. But I'll tell you. According to Bohr, you cannot use concepts of mechanics or concepts of macro mechanics, है ना? That the mechanics of big objects in smaller objects, in atomic physics, in quantum physics. You cannot use that. Nah, buddy. Bohr. So Bohr was like, no, you can't. Bohr, your theory, everything is good, but your theory is only applicable for macro mechanics for bigger bodies. You cannot use it for smaller bodies like electron and everything. You cannot use it for quantum mechanics. But again, Bohr had a contradiction, because he assumed circular orbits, and circular orbits has centripetal acceleration, which again is a mechanics, it's a macro mechanic concept. So he was combining macro mechanics and quantum mechanics over here. So he was not able to explain the clear difference between them. ठीक है clear. Question people, question for you all. This is an important JEE 2018 question. If you have understood this, if you have understood everything that we have studied up till now, please, I want fire in the chats. Fire in the chats. Yes, I will. Okay. Planck's constant and angular momentum have the same dimensions. So angular momentum is L, that is equal to mvr. This is basically equal to nh by 2 pi. Now if you notice over here, n is constant, 2 pi is constant. L is angular momentum, that is mvr. So are you all able to understand that mvr, the dimensions of mvr is basically equal to the dimensions of Planck's constant? Yes, it is equal. You are able to see it over here. This is true. Okay. Second, linear momentum and moment of force have same dimensions. Again, moment of force is basically torque. Torque is RF sine theta. You don't have to write now because you have not studied rotational motion. And linear momentum is P is equal to mv. You are able to see that these are not equal, and dimension and unit wise they are not equal. So this is also wrong. This is wrong. This is correct. So statement 1 is correct, but statement 2 is false, and option 1 is your right answer. Okay. Yes. Okay. Okay. Tell me the answer. Tell me the answer of this. Tell me the answer of this, people. Tell me the answer of this. Tell me the answer of this. The Bohr model is applicable to hydrogen and hydrogen-like atoms only. Assertion is correct or wrong? Assertion is correct or wrong? Yes, Krumshika, I've read it. Yes, I think so. It is correct. है ना? Only for isoelectronic species. Assertion is correct. Assertion is correct. Second, the formulation of Bohr model does not include repulsive forces between electrons. Yes, it is true. It is true. It is true. And both of them are explaining each other. Both of them are explaining each other. Yes or no? Correct. क्या बात है ना? Let's go. Now people, before we move ahead, very important thing coming up. Very important thing coming up. I want, and I'm going to be slow at this. I'm going to be very slow. Because people, the thing which I'm going to explain is very important. Is very important. I want your pen and I want your notes as well. I want your pen and I want your notes as well. You are going to derive certain things with me, which is going to literally imprint this formula into your brain. Okay. So second, nothing, Baba. This is torque, no, R into F. If you calculate the dimensions, so R is basically L, force is mLT minus 2. है ना? This is the dimension of torque. What is momentum? This is mass, and velocity will be LT minus 1. So is it same? Is it same? It's not same. It's not same. That is the reason. That is the reason it's not equal. Okay. Okay. Reason. Reason because, Baba, it is only applicable to hydrogen and hydrogen-like atoms, isoelectronic species. Why isoelectronic species? Because Bohr was like the electron. If we add one more electron, we have to study the electron-electronic repulsion as well. But that is very complex to understand. That is the reason. Okay. Chalo. People, please write. The heading is characteristics of Bohr's model, and the first thing that we are going to study is the radius of the orbits. The radius of the orbits. Okay. The radius of the orbits. Very important. Very important. Okay. And you can even draw a diagram of this. So this is a nucleus. This is a nucleus which charge Ze. This is an electron with charge E, and also it has mass m. Okay. It has mass m. It is traveling with some velocity v. And the radius over here is small r. And obviously, okay. Yes. Now, this is revolving in circular motion. As this is revolving in circular motion, you have to understand that, as I've told you, if any particle is in circular motion, it has to have centripetal acceleration. So the centripetal acceleration would be directed towards the center, and this is AC, that is v square by r, v square by r. Or even I can say this, that this, or even I can say something like this: there is a centripetal force Fc, mv square by r, which is directed towards the center, and this is getting balanced, and or even I can say something like this: this is being provided by the Coulombic force of attraction between them. Yes or no? Yes, sir. See this. Simple. Can I basically say mv square by r is basically equal to k q1 q2 divided by r square? Can I basically say this? Can I basically say this? Yes or no? Can I say this? Yes or no? Have you all understood that the centripetal force is actually being provided by the Coulombic force of attraction between the nucleus and the electron? Yes. Substitute the value of K. So what I get is mb square by r is basically 1 by 4 pi epsilon naught, 1 by 4 pi epsilon naught. This becomes ze square divided by r square, divided by r square. Yes, okay. Now people, one more thing. We already know that L is basically equal to mbr, which is nh by 2 pi. This is one of the Bohr's postulate that we are using over here. Now, what is the velocity over here? What is the velocity over here? Can I write the velocity as nh divided by 2 pi mr? Can I write this? 2 pi mr. This is the velocity. Yes or no? Yes or no? Yes, very good. Now people, I want you to substitute this velocity over here. I want you to substitute this velocity in this equation. So when I substitute this, what happens? So okay, let's first cancel out this r first. This r gets cancelled over here. This r gets cancelled over here. Now let's substitute over here. What do we get? M into v square. So the squaring of everything. N square, h square, the whole divided by 4 pi square m square r square is equal to 1 by 4 pi epsilon naught ze square divided by r. Is this clear? Is this clear, people? Yes, this is clear. Now let's start cancelling. Let's start cancelling. This r gets cancelled with this r. This 4 and this pi gets cancelled. This 4 and this pi gets cancelled. This m and this m gets cancelled. Okay. Anything else? Anything else that we can cancel? No, I don't think so. Anything else that we can cancel over here? Okay. Now let's take everything into the right hand side and this r, sorry, everything to the left hand side and this r to the right hand side. Okay. So what do we get? We get that r is basically equal to r is basically equal to h square, है ना? This is h square epsilon naught, h square हो गया, epsilon naught हो गया, h square epsilon naught divided by pi m z, okay, pi m e square, and this is n square by z. Did everybody get this? Did everybody get this? Yes. Did everybody get this? Yes or no? 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 Yes, this is. Nothing much. mb square by r, value of k I substituted. Then L is equal to mvr is equal to nh by 2 pi, value of v I have calculated it over here. Just substitute the value of v over here. Then I'm just rearranging the terms to find out the value of r. This is what I get. Now this, I've deliberately written it something like this. I deliberately written it something like this. Okay. Now people, see this. See this, okay? Sir, is h square a constant? Yes. Epsilon not a constant? Yes. Pi a constant? Yes. M a constant? Yes. E square a constant? Yes. N can change, that is the orbit number can change. Z can also change, that is the atomic number also can change. है ना? Atomic number also can change. So this itself is a big constant over here. This itself is a big constant over here. That means I can write this as something like this. I can write something like this. This is basically equal to r naught into n square by z. R naught n square by z. Angstrom. Angstrom. Okay. Okay, people. Now, moving. Can I move on to the next page? 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 Yes, I hope so. This is very much clear. This is very much clear. Okay. So, now what I've got, I've got something like this. Sir, R is basically R naught n square by Z. What is this R naught? R naught is basically called as your Bohr radius. R naught is basically called as the Bohr radius. What is the Bohr radius, people? It's very easy. It's very easy. That means if you keep the value of n as 1 and z as 1, that means z is 1 is hydrogen, n is equal to 1 is also the first orbit of hydrogen. The first orbit of hydrogen. So the radius of the first orbit of hydrogen is basically equal to R is equal to R naught, and this has a value of 0.529 angstrom. So you can also write this as R is equal to R naught n square by Z, which is equal to 0.529 n square by Z angstrom. Or you can also tell that the radius of the orbit is directly proportional to n square bate Z, or n square by Z. Yes, people. How was it? Yes, people. How was it? Yes. How was it? How was it? Yes, 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 yes. Did you all understood this, people? Did you all understood this? Yes. So why did I teach you the derivation over here? I'm going to teach you derivation of everything because it's very important in your exams, because your NEET 2025 exam was a bit higher level. You need these kind of derivations to understand complex questions. And even if you forget the relation, what is R directly proportional to, you can just derive it something like this. In just a matter of 30 seconds, you can just derive it, and R is directly proportional to n square by Z. Yes or no? Angstrom, okay? Angstrom. Keep in mind it is angstrom. Angstrom. Okay? Yes, sir. Clear? क्या बात है? एकदम आगे बढ़ते. Keep in mind. Acha, please draw a table something like this, people. Please draw a table something like this. I'm giving you 30 seconds. 30 seconds for drawing this table. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. चलो हो गया. I've given you 40 seconds. ठीक है, चलो. Now people, I want you to write something like this. Okay. You have to write all the isoelectronic species. So this is hydrogen. This is helium plus over here. Hydrogen, helium, lithium. Lithium 2 plus and beryllium 3 plus. Okay. You have written it? Yeah, no, numerical also will come, people. Numerical also will come. Okay. Done. Done. Okay. So this is okay. Now over here in this column, you have to write n, the values of n. Okay, you have to write the values of n over here. Okay, so this is z, and this is n. So this is n is equal to 1. Okay, I'll do something like this. Just a second. Okay, you have to write the values of n over here. So n is equal to 1 over here, then 2, then 3, and then 4, and then 4. Okay, clear? Yes, people. Okay. Now, what are the atomic numbers over here, people? This is Z is equal to 1, this is Z is equal to 1, this is Z is equal to 2, this is Z is equal to 3, and this is Z is equal to 4. Now, people, this is one thing that you have to do along with me, okay? You have to do along with me, okay? We know the relations. What is the relation, people? The relation is R is equal to R naught n square by Z. This is the relation that we know. Yes or no? This is the relation that we have got. This is the relation that we have got. Now, using this relation, you have to fill this table over here. Using this relation, you have to fill this table over here. Now, I'll just do it for one of the rows. Then you can do it for the other rows as well. Okay. See this. R naught n square by Z. For here, n is equal to 1, Z is equal to 1. N is equal to 1, Z is equal to 1. So n is 1, Z is 1, you get R naught. So that is what we are getting. The radius of the first orbit of the hydrogen is R naught itself, Bohr radius. Yes or no? Yes. Yes, yeah, it will be same. It will be same for chemistry NEET. Okay. Next, helium. Helium. N is equal to 1. So this is 1. Z is equal to 2. Z is equal to 2. So this becomes R naught by 2. R naught by 2. Yes or no? Yes. Now for this people, N is equal to 1, but Z is equal to 3. So this becomes R naught by 3. Yes. Now for beryllium, N is equal to 4, but Z is equal to, Z is equal to 4, but N is equal to still 1. So this becomes R naught by 4. This becomes R naught by 4. Yes. Yes or no? Was everyone able to write this? Now I want you all to write this everything. I want you all to write this everything. I want you all to finish this. I want you all to finish this. Can I give you a minute? Can I give you a minute, people? Can I give you a minute? I'll give you a minute. I'll give you a minute. Okay, and your time starts now. Okay, chalo. Complete the table. Complete the table. Complete the table. Complete it. 26 seconds to go. Completed. 10 seconds. 9, 8, 7, 6, 3, 2, 1, 0. Yes. Done. Okay. Now let's do it. Okay. Let's do it. Okay. Now n is equal to, this is n is equal to 2, but z is equal to 1. Okay. So I think you have got 4 R naught over here. 4 R naught over here. Okay. Now over here, this is n is equal to 3, but z is equal to 1. So this is 9 R naught over here. Okay. This n is equal to 4, but z is equal to 1. So this is 16 R naught over here. Now see my speed. Okay. Now see my speed. Okay. Ready? 1, 2, 3. Okay. So this is 2 R naught, and this is 4 R naught by 3, and this is R naught over here. This becomes 9 R naught by 2. This becomes 3 R naught, and this becomes 9 R naught by 4. This is 8 R naught. This is 16 R naught by 3, and this becomes 4 R naught. Completed. Now how did I do this? Okay. Now how did I do this? Because I wanted you all to basically recognize a pattern over here. Recognize a pattern over here. See this. See this, people? Very, very interesting. Very, very interesting. See, people, this is R naught. This is the half of it. This is 1/3 of it. This is 1/4 of it. This is 4 R naught. Half of it is 2 R naught. 1/3 of it is 4 R naught by 3. 1/4 of it is R naught. This is 9 R naught. Half is 9 R naught by 2. 1/3 is 3 R naught, and 1/4 is 9 R naught by 4. This is 16 R naught. Half of it is 8 R naught. 1/3 is itna. 1/4 is itna. Did you all understood? Did you all recognize the pattern? Did you all recognize the pattern, people? Did you all recognize the pattern? Yes. Did you all recognize the pattern? Yeah, I mean, yeah, come on. Yeah, I think I deserve a like and fire, huh? like the live session, and also fire. Yeah, I think I deserve it. Okay, but yeah, this is a very important thing that you had to do it. Chalo, let's do it. Questions. Considering the Bohr model of hydrogen-like atoms, the ratio of the radius of the fifth orbit of the electron, Li2 plus and He plus, JEE 2015 question. JEE 2015 question. Okay. Okay. Chalo, let's solve this. Okay. What do we know? We know that R is directly proportional to n square by z. This is something that we know. Now, what they have said, for hydrogen-like atom, the ratio of fifth orbit of the electron in Li2 plus and He plus. So they have basically told us n is equal to 5 is common for it. So I can basically say R is directly proportional, sorry, inversely proportional to 1 by Z, because n is constant. Because n is constant, है ना? So I can basically say R of lithium divided by R of helium is basically equal to the atomic number of helium divided by the atomic number of lithium. What is helium? Hydrogen helium 2, hydrogen helium lithium, that is 2 by 3, and that is your answer, option B. Option B. Yes or no? Clear? Did you all understood this? How did I do it? Did you all understood it? Yes. Did you all understood this? Everybody, very, very, very important. Very, 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 very important. Very, very important. Yes. Chalo. Okay. So this is basically the question. Chalo, next. Assuming the validity of Bohr's atomic model for hydrogen-like ions, the radius of Li2 plus ion in its ground state is given by something. Where x is something and A0 is the first Bohr radius. Okay. So this I can basically say this is not A0, this is R0 itself. Okay, just to remove the confusion. Okay, just to remove the confusion. Okay, so we need to find out the Li2 plus radius in its ground state. Now, what is ground state? Ground state is basically n is equal to 1. This is the ground state. है ना? Ground state is called as n is equal to 1. Okay, so you can all write it over here as well. That n is equal to 1. N is equal to 1 is also called as the ground state. Okay. Now, acha chalo, we know that R is directly proportional to n square by Z. R is directly proportional to n square by Z. Yes. And we also know, acha, we can also write something like this, that R is equal to R naught n square by Z. Yes or no? Yes, sir. So R is equal to, sir, what is n? Hydrogen, helium, lithium. That is Z is equal to 3. Z is equal to 3. Yes, sir. Z is equal to 3. So this fellow becomes 3 over here. And ground state n is equal to 1. So this is 1. So this becomes R0 by 3. And if you compare this with this fellow, x is equal to 3. X is equal to 3. Clear? Yes, people. Is this understandable? Is this understandable? Did you all understood it? Did you all understood it? Yes or no? Clear hai, clear hai, clear hai. Chamka, chamka, chamka. Let's go. Aage badho. Now, people, are you all ready again? Are you all ready again? Are you all ready again to derive one more thing? Are you all ready again to derive one more thing? Let's go. So again, people, this is the nucleus. Ze is the charge, electron, E, everything clear. Now, we already know that MVR is equal to NH by 2 pi. This we already know, and from this we already know that V is equal to NH divided by 2 pi MR. 2 pi MR. This we already know. This we already know. Yes. Now, people, we also know the formula. We also know the formula of R. What is the formula of R? This is the formula of R. This fellow, है ना? This is the formula of R. Okay. So can we copy this formula? Let's copy this formula. That is h square epsilon naught. Okay, it is h square epsilon naught. R is h square epsilon naught. Okay, h square epsilon naught. Come on, everybody copy it. Divided by pi me square. Divided by pi me square. है ना? Pi me square. N square by z. Okay, n square by z. This is the formula of R that we got. Okay, yes, I would give you a break. Okay, nothing, people. You just have to substitute the value of R over here. You just have to substitute the value over here. Okay, you just have to substitute the value over here, and you will get your answer. Okay, if you want, you can substitute, or else you can move ahead. Okay, so let's substitute. Okay, so V is equal to NH divided by 2 pi m. Now, R is in the denominator, so everything gets reversed. है ना? Everything gets reversed. So this basically becomes h square epsilon naught n square pi me square into z. This is what we are getting. This is what we are getting. Now comes the cancellation part. Okay, so n and h gets cancelled, h and n gets cancelled. Okay, m and pi gets cancelled, pi and m gets cancelled. Okay, so that's it. So what do we get? That v is basically equal to, we get uh, e square divided by e square divided by 2h epsilon naught into z by n. This is what we are getting. This is what we are getting. Did everybody get this? Did everybody get this? Okay, did everybody get this? Everybody. Yes or no? Now, people, if you see this, E is a constant, 2 constant, H constant, epsilon not constant. So this whole fellow is a constant. Whole fellow is a constant. So what do you get over here? You get that this is basically equal to 2.19 into 10 raised to 6 into Z by N into Z by N meter per second. Meter per second. Yes, Cheta, Anna, thank you, sir. Yes, and for calculation basis, for the easiness of calculation, you can even approximate it as 2.2 into 10 ki power 6. You can even approximate this. Yes, people. So from this, what you are getting? From this, you are able to understand the velocity is directly proportional to z by n. Velocity is directly proportional to z by n. This is what you are getting. Yes or no? Is it absolutely clear? Is it absolutely clear? Is it absolutely clear? अगर हो सके तो ठंडा कर दो, कोई इशू नहीं है. हाँ नहीं, और ठंडा कर सकते हो एसी. हाँ, क्लियर, वेरी गुड. ठीक है, ओके. सो दिस इज व्हाट वी आर गेटिंग. डन है. लेट्स गो पीपल, लेट्स गो. Okay, so this is one formula. This is one question, people. Now people, even though you can calculate the velocity of an electron in any particular orbit for any isoelectronic species, okay, you have to understand one thing. That is, when the question gives you a certain value, you have to assume that value, even though that value is not right, even though it's wrong value. It's a hypothetical value that is given. It's an hypothetical value it's given. Are you able to understand? That means, for example, speed of the electron in Bohr's 7th orbit for hydrogen atom. So if you want to calculate the speed of the electron in the 7th orbit, it is going to be 2.2 into 10 ki power 6 into Z. Z is hydrogen is 1 and N is basically 7. So when you divide this, you do not get 3.6 into 10 ki power 6. You do not get this. 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 But still, you have to assume that value. That is a hypothetical value that has been given. That is a hypothetical value. You have to assume that. If it's not given, then you have to go along with this calculation. Are you able to understand this? Okay. Let's understand. The speed of the electron in the 7th orbit is this much. The corresponding speed of the electron in the 3rd orbit, it will be how much? We know that V is directly proportional to Z by N. Very good. Now, they have not changed the atom. So, Z is constant. So, I can definitely say V is inversely proportional to N. Now, we need to find out the speed of the electron in the 3rd orbit. So, V3 by V7 will be 7 divided by 3. Will be 7 divided by 3. Okay. So, V3 will be 7 by 3 times of velocity in the 7th orbit. So, that is 7 by 3 times of 3.6 into 10 ki power 6. So that comes out to be, this is 3 ones are, this is 3 ones are, this is 2s are 12, that is this is 7 2s are 14 and 1 7 is 7, 8.4 into 10 ki power 6. 8.4 into 10 ki power 6, option 4. Option 4. Sir, not getting, what did you not understand? Yes, understood people. Yes. Yes, people. If you understood this, can I get a fire in the chat box? Can I get fire in the chat box? Can I get fire in the chat box? V send up again, please. Arey, nothing. See, what I'm saying is, see, sometimes in the question they have already given that the speed of the electron in the 7th orbit is 3.6 into 10 to the power 6. But if you use the formula, you're not getting the speed as 3.6. You're getting something else. You're getting something else. But you have to use that hypothetical value. If it's not given, then you can use this value. Okay? Okay? Okay, what is V7? So see this. V is directly proportional to Z by N. So, but as we are not changing the atom, Z is a constant. So I can write V is directly proportional, sorry, V is inversely proportional to N. That means velocity of the 3rd orbit divided by velocity of the 7th orbit is 7 by 3. Inversely related. No, inversely related. Inversely related. What is the velocity of velocity of the electron in the 3rd orbit? Velocity of 7th orbit multiplied by 7 by 3. We already know value of V7. That is 3.6 into 10 to the power 6. That means khatam. Okay. Now, last. Not the last. Now we know. Now we need to find out time period of electron and angular frequency. We already know that time period is basically 2 pi by r. Sorry, 2 pi r divided by v. This is what we are getting, right? This is what we are getting. So we can basically say time period is directly proportional to r by v. This is something which we know. And we also know that r is directly proportional to n square by z and v is directly proportional to z by n. This is something that we know. Use this both of them over here. So can I basically say r is n square by z? That is r is n square by z. V is z by n. So this is z and this is n. So what I'm getting over here? I'm getting T is directly proportional to n cube by z square. N cube by z square. So if I want to find out the frequency is 1 by time period. So this is directly proportional to z square by n cube. Simple. 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 Now, what is angular frequency? Angular frequency is omega. That is time period is equal to 2 pi by omega. Again, you are able to witness that is T is inversely proportional to omega. Inversely proportional. Or you can basically say omega is inversely proportional to 1 by time period. So if 1 by time period is n cube by z square, omega will be z square by n cube, just the reciprocal. Just the reciprocal. Clear? Is this absolutely clear? Is this absolutely clear? Yes, people. If you understood this, fire in the chat box. If you understood this, fire in the chat box. Okay. Okay. Now, this is the final question before we move on to the most important part of the chapter. Okay. The time period of revolution of an electron in its ground state orbiting in a hydrogen atom is ethna. Okay. Ground state. Okay. The frequency of revolution of the electron in its first excited state. So basically what we can do is basically we can calculate the time period and then inverse it. Yes. So what do we know? We know time period is directly proportional to n cube by z square. That is time period is directly proportional to n cube by z square. Now, if it's an hydrogen atom, you're not changing the atom. So Z is constant. So I can definitely say T is directly proportional to n cube. I can definitely say this. So T1 by T2, T1 by T2 will be ground state and first excited state. Acha. What is first excited state, people? Do you all know what is the first excited state? First excited state, I'll tell you. If this is the ground state, n is equal to is called as the first excited state. Okay, first excited state. And this n is equal to 3 is the second excited state. I think this is pretty, you know, self understanding, okay, self explanatory. So T1 by T2, or I can definitely say this as T1, that is time period of the first orbit, divided by the time period of the, this is n is equal to 2, first excited state, है ना, first excited state, T1 by T2 will be equal to 1 divided by 2 the whole cube. Yes or no, people? Yes or no? Yes, sir. So this will be, this gives me T1 by T2, it gives me 1 by 8. It gives me 1 by 8. Now people, they need me to find out the frequency of revolution. Frequency of revolution of n is equal to 2. Now people, is 1 by T2 F2 itself? Yes, 1 by T2 is F2 itself. So I can basically say 1 by T2 is F2. It is equal to 1 divided by 8 into T1. That's it. That's it. So this becomes 1 by 8 and the time period is how much? 1.6 into 10 ki power minus 16. That's it. You calculate this and you get the answer. Calculate this and you get the answer. Okay. So this comes out to be 7.8 or something. Okay, this comes out to be option 3. Very good. Very good, very good, very good, very good. Okay. Chalo. Now people, very, 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 very important thing. Very, 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 very important thing. Very, very, very important thing. Very much important. Very important, people. Very important. People, see this. See this. Velocity, I've already calculated e square by 2. हाँ, ये देखो. See this, people. I have calculated the velocity. I have calculated the velocity. E square 2h epsilon naught z by n. This value, are you able to understand this? Now see this. Now see this over here. Kinetic energy is half mv square. The value of v is e square divided by 2n h epsilon naught. Exactly same cheese. Exactly same value. Exactly same value. I've just substitute over here. I'll get this. Okay. And potential energy is potential into charge. That is k q1 q2 divided by r. And I just substitute the value of r over here and I'll get something like this. Small break. Arey yaar, break. How will I complete the chapter then? Huh? How will I complete the chapter? Okay, I'll give it around 11 o'clock. Can I give it around 11 o'clock? Can I give it around 11 o'clock? From 11 I'll give a 15 minutes break, okay? I'll give a 15 minutes break from 11. From 11 I'll give a 15 minutes break from 11. Okay? A 15 minutes break from 11. 15 minutes break from 11, okay? 11 o'clock. Okay, 15 minutes. Okay, 15 minutes break from 11, okay? So see this, I have just substituted the value of v over here and I've already found out the value of v over here, no? See this, e square 2h epsilon naught z by n. E square 2n h epsilon naught. Now this is for hydrogen, so z is equal to 1. Just substitute it over here. So this is kinetic energy. This is potential energy. People, if you use this formula, you will get the answer in joule. You will get the answer in joule because everything is in SI unit. Everything is in SI unit. Okay, everything is in SI unit. But we don't have time. है ना? You don't have time. We don't have time. So the kinetic energy comes out to be okay, let me first okay, chalo. The kinetic energy comes out to be 13.6 into z square by n square electron volt. This is the kinetic energy in electron volt, people. In electron volt. Okay? Yes. So what is the potential energy? The potential energy, the potential energy is just minus 2 times the kinetic energy. Minus 2 times the kinetic energy. That is minus 2 into 13.6 into z square divided by n square. Yes or no? Minus 2 times this. So sir, what will be the total energy of the system? The total energy of the system or the electron that I am talking about will be kinetic energy plus potential energy. Okay. Now see this. Now see this, people. I'm gonna take a value over here. Okay. I'm gonna say that this is equal to x. This is equal to x. So if this is x, can I basically say that this is minus 2x? This is minus 2x. And I've just multiplied minus 2 with kinetic energy, minus 2x. So can I write kinetic energy as x, this as minus 2x? So I'm getting the total energy as minus x. Minus x. So that means the total energy comes out to be, the total energy of the system comes out to be minus 13.6 z square by n square electron volt. Clear, yes or no? Clear, yes or no? To all the people who are watching right now, people, please do not leave right now. Please do not leave right now. A very important slides are coming up right now. Very important. They are the crux of the chapter. Please do not leave right now. Hai, you have promised yourself to attend this game of NEET sessions from start till the end. But yet only few are there who stay till the end. We started with around 200 people or something watching. Hai, we don't, okay? This is just k q1 q2 divided by r, people. You don't have to understand the derivation. Don't worry. You don't have to understand the derivation. Okay? You don't have to understand the derivation over here. Okay? You don't have to understand. Don't worry about it. Don't worry about it. Okay? So this is x. This is minus 2x. And this is total energy comes out to be minus x. This is the total energy. Now, if you will notice over here, you will find out something. What is it, sir? We'll find out that kinetic energy is x, total energy is minus 2x, and the not the total energy, the potential energy, the potential energy is minus 2x. The total energy is basically the negative of kinetic energy. Negative of kinetic energy, or also called as minus x. Yes or no? Okay? Is this clear? Is this clear? Absolutely clear, people. Absolutely clear. Okay. This is something that we understood. Now we are going to use this. We are going to use this formulas very much. Now people, now you have to ask this question. What does this negative sign indicate in the total energy? What does this negative sign indicate in the total energy? Okay. So we have already known that total energy is basically minus 13.6 into z square divided by n square electron volt. What does this negative sign indicate? What does this negative sign indicate? This negative sign, it indicates that the electron is bounded to the nucleus. Meaning, just a second, people. I just tripped on my own mic. Meaning Whenever you have a negative sign in your energy, that means the electron is still bound to the nucleus. It is still revolving around the nucleus. As soon as the energy is zero, it is not bound to the nucleus. It is not bound to the nucleus. It is out of the atom. It is the out of the atom. If the total energy is greater than zero, or I'll say if it's zero, it is not bound to the nucleus. Not bound. The electron is not bound. But if the total energy is greater than zero, it is not bound. It is not bound, and as well as the electron has the kinetic energy as well. Electron has some kinetic energy as well. Clear, people? Clear, people? That means this negative sign indicates that the electron is still revolving around the nucleus. If the total energy is zero, it is not bound. It has escaped the nucleus. It has escaped the atom. But if it is greater than zero, if the total energy is greater than zero, it has obviously escaped the atom. The electron has escaped the atom, and it also has some additional kinetic energy as well. It also has some additional kinetic energy. Clear, people? Clear? Yes? Okay. Now, I want you all for a homework. Not a homework. We're going to do a homework over here itself. Okay? Illustration over here itself. I want you all to find out the total energy of each orbit for a hydrogen atom. So, for an H atom, Z is basically equal to 1. है ना? So the total energy comes out to be minus 13.6 divided by n square electron volt. So that means if I calculate, I get E1 as minus 13.6 electron volt. Value of n is equal to 1. Value of 2, n is equal to 2, that is minus 13.6 divided by 4. You get minus 3.4 electron volt. E3, put 3 inside it, minus 13.6 divided by 9, that is minus 1.51 electron volt, and so on. Yes, break, I will give break, don't worry, I'll give break. Yes or no? E4, minus 0.85 electron volt, and so on till E infinity, that is E infinity, the energy is 0. So as I said, if the total energy is 0, the electron is not bound to the nucleus. That is the reason at infinity we consider the total energy to be 0. Understood, people? Now tell me, people, is the energy increasing as we increase the orbits? Yes, people? Okay, what I said, that is the energy increasing or is the energy decreasing as we are increasing the number of orbits? As the orbit number increases, obviously you are able to find out this is negative number. It's not decreasing, it is increasing. Arey buddy, minus 10 is greater than minus 12. It is increasing, it is not decreasing, it is increasing. This is minus 13.6, this is minus 3.4, this is minus 1.51, this is 0.85, and it's 0. It is increasing, the energy is increasing. This negative sign only denotes that the electron is still bound to the nucleus. है ना? Yeah. See, in online class you can't do, no? Otherwise, in offline class, you can just say, sir, creases, sir, creases. Everybody will shout creases. The teacher has to, find out whether the students are saying decreases or increases. Sir, creases. Yes. So this is what we know. Okay. This is what we know. Okay, people. So I've already, this is a diagram that you have. Yes. This is a diagram that you already know. So at n is equal to infinity, the energy is 0. N is equal to 1, minus 13.6, n is equal to minus 3.4, n is equal to 3, minus 1.4, n is equal to 4, minus 0.85, and so on. You have to remember these values. Very important. You have to remember this value. Yes, you have to remember these values. So the ground state, n is equal to 1, this is the energy. n is equal to 2, this is the energy, n is equal to 3, this is the energy, and so on. You have to remember these values, hai na? So this is increasing, this is the energy levels that is increasing. Okay people, now what is binding energy and ionization energy? That is something that we'll talk about. Okay, you can take a break, you can take a break. Okay, you can take a break, you can take a break. I'll give you a break. Okay people, I'll give you a break. I think 10 minutes is fine. Okay people, 10 minutes is fine, because we have to complete the we have to complete. Okay, we have to complete as well. Okay, I think 10 minutes is fine. Here you go. Okay, here you go, 10 minutes. Okay, we'll be back by 11:10. Everybody back by 11:10. I want everybody back by 11:10. Okay, yes. Hey guys, I'm back. I'm back. As I promised that I will give you 10 minutes break, and I gave you 10 minutes break. Now it is your time to deliver the promise back that you have to be back by 11:10. Huh? Come on, people. Come on. Let's get this going, people. Let's get this going. Let's get this going. Let's finish it up. Let's finish it up. Come on. Let's finish it up, people. I want you all back again. Okay. Hello, people. Yes. Let's start. Let's start again. I'm starting it again. Your 10 minutes break are up. Okay. Let's see people. है ना? Let's see people. Okay. What will be the class duration? I think more 2 or 3 hours and then we'll be done. Okay, more 2 or 3 hours and then we'll be done. Okay, people, let's have some fire emojis in the chat, so that it is the sign that you have all come back again, hai na? Some fire emojis in the chat and then we'll start again. How many topics are left? In this only some topics are left, people, and the nuclei, the chapter is left. Again, nuclei chapter is very easy. You don't have to worry about it. Okay, people, don't have to worry. Yes. Okay, some fire emojis in the chat, people. Very good. Chalo, let's begin. Okay, let's begin again. So again, these are the energies that we all calculated over here using this formula and everything. Okay, moving ahead. Thank you. Moving ahead, people. This is one question that you have to solve. Let's solve this question fast. Okay. Consider the Bohr's atomic model for hydrogen atom. Okay. The energy of the H atom in ground state is same as the energy of the He plus ion in its first excited state. Let us calculate. Energy of the H atom in the ground state. I think that will be minus 13.6 into Z square. Z is 1 for hydrogen atom and N is also 1 for ground state. So this will be 1 divided by 1. So minus 13.6. Now for helium plus, it will be minus 13.6 Z square. What is helium? Hydrogen helium. Z is equal to 2. So this becomes Z square, that is 2 square, divided by first excited state, that is N is equal to 2. That is again 2 square. So this is the same thing. So yes, this is true. This is true. Okay. Okay, people. Chalo. See, if we want to complete the session as fast as possible, then you need to give me the support. You need to give me the support in the comment section as well. Okay. So this is true. The energy of the H atom in the ground state is same as that for Li plus. In the ground state, it is minus 13.6. We just calculated it now. Let's calculate it for Li plus, Li2 plus in the second excited state. Second excited state will be N is equal to 3. So this will be minus 13.6 Z square. What is lithium? Hydrogen, helium, lithium. That is 3 square. This is 3 square divided by 3 square because N is equal to 3. So again, this comes out to be equal. So this is also true. This is also true. Okay. See, the energy of the H atom in its ground state, that is again minus 13.6, is same as that of the He plus ion for its ground state. No, it is not true, because it is true for this first excited state, not for its ground state, So this is false. The energy of He plus ion in its first excited state, that is minus 13.6 Z square. Hydrogen, helium, Z is equal to 2. And first excited state, that is N is equal to 2 divided by 2 square. This is the energy of He plus ion. Is same as that of the Li2 plus ion in its ground state. So it will be minus 13.6 Z hydrogen, helium, lithium. Z is equal to 3. So this is 3 square. Ground state is N is equal to 1. So this is not equal. So this is also wrong. So only A and B is right. Okay, people. Only A and B is right. Yes. Only A and B is right. Okay. Let's move ahead, people. Now you have to understand Rydberg's constant. Okay, Rydberg's constant. Oh my god, this is 1 Z square is missing over here. 1 Z square is missing. Yeah. Rydberg's constant. What exactly is Rydberg's constant? Now see, this is basically uh, the formula that we got for total energy. This is the formula that we got for total energy. So this same thing. This is the same thing. Where is it? Where is it? Yes, the total energy that we got. This is the total energy that we got, but that expression is for in joules. Okay, in joules. Okay, this formula is corresponding for joules. Okay, people. Now what I'm doing right now? What I'm going to do right now? I'm going to basically multiply and divide by Hc over here. Multiply and divide by Hc over here. Okay, people, multiply and divide by Hc over here. So what I get over here? What do I get over here? I get this as something like this. I get minus m E4 divided by 8 n square h cube c epsilon naught square multiplied by Hc. Multiplied by Hc. This is something that I'm getting over here. Okay. So this n square also I can take it out. This n square also I can take it out. N square also I can take it out. Yes, this is something which I am getting. Okay. Hc and z square by n square. This is something which I am getting. I just multiplied the Hc in the denominator. Now, if you all notice, this is again one constant, people. Mass of the electron, charge of the electron 8 h cube c epsilon naught square. This is one constant, and this is basically your Rydberg's constant. This constant right over here is called as your Rydberg's constant. Okay, and this has the value of r. This has the value of r over here. Okay. This has the value of r. This is called as Rydberg's constant, and it has a value of 109678000 meter inverse. This is the value of Rydberg's constant. This is the value of Rydberg's constant over here. Now, people, do you have to memorize this value? If you can, you can. Okay, it's just like a phone number, but you don't have to actually memorize this value, because in calculations you don't have to use this. In calculations you don't have to use this. What do you have to use? I'll tell you. What do you have to use? I'll tell you. So if this whole fellow is r, people, can I basically write this? Can I basically write this as minus r hc z square by n square? Yes, people, I can write this. I can write this something like this. Now, if I compare this with the original equation, that is minus 13.6 z square by n square, I am able to find out that RHC is equal to 13.6. Oh my god, that is some good value that I am getting. That is, the value of RHC comes out to be 13.6 electron volt. This is the value of RHC that I am getting over here. RHC that I am getting over here. Now, as I said, do you need to find out the value of, do you need to memorize the value of R over here? No, not needed. The thing that you have to memorize or keep in mind is over here. That is, the value of R is 1096700 meter inverse. You need to find out, you need to memorize the value of 1 by R. That also in angstrom, and it comes out to be 911 or 912 angstrom. Whatever suits your calculation, you can take any of these things. Whatever suits your calculation, you can take any of the values. 911 or 912 angstrom. Clear? Clear, people? Is this everything clear? If it's clear, can I have some fire in the chat box, people? Can I have some fire in the chat box? And some green hearts, as HSP sir says. Some green hearts, as HSP sir says. Yes? So this is something that I am able to understand it over here. Okay, clear? Chalo. Let's move ahead. Okay, let's move ahead. That is something that you have to keep in your mind. Okay, that is something that you have to keep in mind. Okay. Now we have to understand what exactly is ionization energy and potential. Ionization energy and potential, very, 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 very important, people. Very, very important. Very, very important. People, it's very easy. It is very easy. Right now, okay, right now, the electron is traveling in an orbit or nth orbit, which has energy En. Or I can basically say something like this. Let me assume let me say that the electron is right now traveling, the electron is right now revolving in an orbit which has an energy of minus 3.4 electron volt. Okay. Ionization energy is basically the amount of energy that I have to provide to this electron. Let me say it is some X energy, so that the total energy of the system becomes zero. Are you able to understand this? The total energy of the system, when does it become zero? The total energy of the system, that means the electron is not bound anymore to the nucleus. That is what we have studied over here. That is what we have studied over here. Where is it? 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 Yes. What does the total energy of the electron, what does the total energy zero of the electron mean? That it means it's not bound to the nucleus. That means, what is ionization energy? Ionization energy is nothing much. Ionization energy is nothing much. The amount of energy that I have to give to an electron in a particular orbit to make the total energy as zero. So, this X right over here, this X right over here, X right over here is basically your ionization energy. So basically, can I say this X comes out to be plus 3.4 electron volt, people? Yes or no? Okay. Okay. Are you all able to understand this? Yes, people. Now, can I say something like this? If I want to generalize things over here, if I want to generalize things over here, okay? If I want to generalize things over here, that ionization energy, is basically the negative of the energy of that particular orbit. That means if in a particular orbit the total energy is minus 3.4 electron volt, how much energy you have to give so that the total energy becomes zero? Obviously positive of this or negative of this value, that is minus 3.4 electron volt. Understood? Understood, people? Yes or no? Yes or no? Clear? Yes or no? Or can I also even say as something like this, that this is basically equal to the negative of the total energy, and also this is also something called as, this is also called as binding energy. This is also called as binding energy. Yes or no? Yes or no? That means ionization energy is basically the negative of the energy of that particular orbit, or negative of the total energy of that particular orbit, or we can also say as binding energy. Clear? Clear basically? Okay. Now, there are many different forms by which you can give this energy. There are many different forms by which you can give this energy. Many different forms. The first method by which you can give this energy is obviously photon. A photon of sufficient energy can strike the electron and just eject it out. The second is atomic collisions. And here also there are two methods of doing it. The first method is an electron collides with an electron, and the second method is an atom collides with an atom. An atom collides with an atom. There are two collisions which can take place. So an electron can collide with an electron and can eject the secondary electron out, or atomic collisions, that an atom and atom can basically collide with each other and the electron can get thrown out. Are you all able to understand this? Okay. Once more, no problem. So basically, what is ionization energy? Ionization energy is basically if the electron is in the first orbit. So the total energy is how much? The total energy right now is minus 13.6 electron volt. How much energy I have to give? If this electron has to jump or eject to infinity? Obviously, you will be saying I'll have to give plus 13.6 electron volt so that the total energy becomes zero. Understood? That's it. Yes or no? Did you all understood it? Yes or no? Yes or no? So plus 13.6 is the ionization energy. That's it. Simple. Now, what is ionization potential? Ionization potential is nothing much. It is ionization energy divided by E. That is the charge of an electron. This is the formula. That means how much potential I have to give. What is ionization potential? What is ionization potential? How much potential difference I have to give so that the electron gets ejected out of the system. That's it. That's it, people. That's it. Simple. Straightforward. We'll be solving questions, don't worry. We'll be solving questions, don't worry. Okay. We'll be solving questions, don't worry. Now, what is excitation energy and potential? Now, this is something which we are very interested about. This is something which we are very interested about. People, very, very easy. Very, very easy, people. This is very, very easy to understand. Very, very easy to understand. If the electron is in the first orbit, so obviously it will be in E1. If he wants to jump to E2, it is very much obvious that it has to gain energy. And what is the gain? It is binding energy. Be means binding energy. It is so obviously, if the electron is in the first orbit, it has E1 energy. If he wants to get excited and enter the second orbit, which has E2 energy, obviously it cannot just excite and go into the second orbit. It has to has E2 energy. So obviously, what will happen? What is the amount of energy? What is the amount of energy? Right now it has E1 energy. How much energy X I have to give so that the total energy becomes E2? And this X right over here, is basically your excitation energy. Are you all able to understand this? Are you all able to understand this? Yes or no? Are you all able to understand this? Are you all pakka able to understand this? That means, people, for example, let me tell you. If the electron right now is in the first orbit, so that will be minus 13.6 electron volt. How much energy I'll have to give so that it gets excited to the second orbit, which has an energy of minus 3.4 electron volt. Just solve this. When you solve this, you get X as 10.2 electron volt. That means you have to give the electron 10.2 electron volts of energy so that it will gain this 10.2 electron volts of energy and jump into the second orbit, which has an energy of minus 3.4 electron volt. Is this absolutely clear? Is this absolutely clear? Yes or no? Yes or no? Very easy. You don't even need the formula for it. It's very easy. But people, again, the definition is very important over here. Excitation energy is the minimum amount of energy needed to move an electron from its ground state to a higher energy level. The main point over here is ground state. It is always ground state. It is the definition. You cannot change the definition. It is always from ground state that you're taking. That is the amount of energy required for an electron to jump from the ground state to any higher excited state is called as the excitation energy. Yes or no? Yes or no? Am I clear? That means, can I basically say something like this? If you want to derive a formula, according to the definition, I'm right now in ground state, that is E1. How much energy I have to give X energy so that it can reach an excited state En. So X is basically En minus E1. This is what the formula is. X is basically, now what is the energy of the system in the nth orbit? It is minus 13.6 Z square by N square. Minus, this will be minus of minus 13.6 Z square divided by 1 square. This is the formula. But you do not need the formula for it. Why are you using the formula? It's quite logical. From this thing. Why are you doing this? You don't need these at all. Are you able to understand this? This is the formula. If you want, you can take the minus 13.6 common. Why do you want to use this formula? No need. We need the concept inside our brain. It is basically what? the amount of energy the amount of energy required by the electron to get excited from the first excited state to the higher excited state, that is called as the ionization energy. Sorry, is the excitation energy. It's not necessary. You can basically use this logic, right? You can basically use this logic. I'll use this logic and solve questions and so show you. So, and what will be the excitation potential then? What will be the excitation potential? Nothing but it will be the excitation energy divided by E. That's it. That's it. If you have understood this, can I have some fire in the chat box? If you have understood this, can I have some fire in the chat box? Can I have some fire in the chat box? Now see this, people. This is again HCV. HC Verma. Question from HC Verma. Question from HC Verma. Question from HC Verma. What does it say? The ground state energy of the hydrogen atom is minus 13.6. That is something which we already know. When its electron is its first excited state. First excited state matlab n is equal to 2. Its excitation energy is. Now, some people get confused over here. What is the confusion? The confusion, I'll also be writing the confusion so that you know you do not get confused during your exam. The question says when its electron is in the first excited state, that means the electron is in n is equal to 2. Now you have to calculate the excitation energy. Now the confusion is that what excitation energy we have to calculate? The amount of energy needed to go for the electron to go from n is equal to 2 to n is equal to 3, or the amount of energy required from n is equal to 1 to n is equal to 2. Which is right over here? Which is right over here? Because according to the question, the electron is in the second excited state. Sorry, the first excited state, that is n is equal to 2. And it has asked us to find out the excitation energy. So many people get confused whether we have to find the excitation energy from n is equal to 2 to n is equal to 3 or from n is equal to 1 to n is equal to 2. Which is right? Exactly. 1 is right. Because according to the definition, we have already said we have to calculate it from the ground state. It is from the ground state. Okay? It is from the ground state. So, the electron was in minus 13.6. So, the amount of energy that is required to make the energy minus 3.4, it is X is equal to 10.2 electron volt. This is your excitation energy. Now, if I want to calculate excitation potential, nothing else. Excitation potential is basically excitation energy divided by E. This will be 10.2 electron volt divided by E, that is 10.2 volt. That's it. This is your excitation potential. Excitation potential. Simple. Yes or no? Yes or no? Is this clear? Is this clear? Is this clear? Please like the session, people. Please like the session, people. Please like the session. Okay. Now we are coming back to de-excitation. Now what happens over here, people? Now what happens over here? It's very easy to understand. It's very, very easy to understand. See this, people. Electron is in the first. Electron is in the ground state. It takes some energy, है ना? It takes some energy, and because of this, it excites. It excites, and it travels to nth excited state or some nth state, and it only stayed in the nth excited state for 10 raised to minus 7 or 10 to power minus 8 seconds. It only stays for 10 raised to minus 7 or 10 raised to minus 8 seconds in that excited state. And then it comes back to the original ground state. Now this is very easy to understand. People. Come, let's, where is the diagram? Yes, this is the diagram. Let me copy this. And this goes over here. Yes, this goes over here. See this, people. See this over here. people? The electron is over here. The electron is over here. Electron is over here. Now this electron wants to go to the third energy level. Third energy level. So it has minus 13.6 right now. It needs minus 1.51. So what is the energy required? Obviously this is the bigger value. So obviously you have to do minus 1.51 minus 13.6. Yes, final minus initial. So this comes out to be minus 1.51 plus 13.6. Plus 13.6. Yes or no? So if you calculate this fast, this comes out to be 12.09. So 12.09 electron volt energy is required by this electron to go to n is equal to 3. So you drop a photon of energy how much? 12.09 electron volt, and due to this it gets excited over here. And this, you can calculate the lambda or the frequency of the photon by h mu or hc by lambda over here. You need mu frequency photon or lambda wavelength photon in order for it to excite over here. Yes or no? Okay. Now it only stays here for 10 raised to minus 7 or 10 raised to minus 8 seconds. And it wants to de-excite and go back to the ground state. Now, obviously it has minus 1.5 electron volt. It wants and it needs minus 13.6 electron volt. So obviously, this is a greater energy, this is a lesser energy. It has to lose energy. So obviously, when this electron comes out, or this is also called as de-excitation, it will release an energy, or it will release a photon which has an energy equivalent to 12.09 electron volt. Simple. No semiconductors included. Semiconductors is a different chapter. Okay. Are you all able to understand this, people? Are you all able to understand this? Yes or no? Yes or no? Yes or no? Are you all able to understand this? Yes or no? It requires 12.09, and when it de-excites, it will release a photon of energy 12.09. That's it. Okay. Now coming back to spectral lines. Now people, spectral lines. What are spectral lines? I've already showed you spectral lines. Okay. Now, if an electron is in n is equal to 5, and if it wants to jump to n is equal to 1, okay, this is the de-excitation. This is the de-excitation that has to happen. Okay, this is the de-excitation that has to happen. How many different types of photon or how many different types of wavelength we can see? How many different types of wavelength we can see? Very easy to understand. Very easy to understand, people. See this. N is equal to 5. This is 4. This is 3. This is 2. This is 1. Okay. See this. This is n is equal to 5. This is n is equal to 4. This is n is equal to 3. This is n is equal to 2. This is n is equal to 1. Now, if the electron is in n is equal to 5, what are the different ways by which it can come down? Obviously, there are multiple ways by which it can come down. One way is 5 to 4, then 4 to 3, then 3 to 2, then 2 to 1. One way is from direct 5 to 1. One way is from 5 to 4, then directly to 1. The third way is from 5 to 4, then 4 to 3, then directly to 1. There are multiple ways by which it can come down. And these multiple ways are basically called as the number of spectral lines, or the different types of wavelength, or the different types of photon that can be released. Are you all able to understand? So, the number of spectral lines formula, comes out to be n into n minus 1 divided by 2. N into n minus 1 divided by 2. This is their formula. That means, board के लिए पढ़ सकते हैं. So how many different types of spectral lines are possible? Just add the value of, just substitute the value of n over here. So what do we get? We get 5 into 5 minus 1 divided by 2, which is basically 5 into 4, 20. 5 into 4, 20, 20 divided by 10. There are 10 spectral lines which are possible, or 10 photons are possible. That is 10 photons of different lambda are possible. Now, what are the number of different ways by which that can come? Now, this is a very good trick that I'm going to show. Okay, this is a very good trick that I'm going to show. Very good trick that I'm going to show. If an electron wants to come from n is equal to 5 to n is equal to 1, what are the different ways by which it can come? One way is that it travels from 5 to 4. 5 to 4. Okay. Second way is that it traveled directly from 5 to 3, or it can travel from 5 to 2, or it can travel from 5 to 1. These are the possible ways. Okay. Now, if it has traveled from 5 to 4, the next possible way is that it travels from 4 to 3, and then it travels from 4 to 2, or it travels from 4 to 1. Now, if it has traveled from 4 to 3, then it can travel from 3 to 2 or from 3 to 1. Now, if it has traveled from 3 to 2, it can travel from 2 to 1. These are all the possible ways. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 possible ways. That is exactly what we have got over here. 10. Have you understood it? Did you understood it? Did you understood it, people? Yes or no? Did you all understood this method? How did we calculate the number of spectral lines? Did you calculate the number of spectral lines? Yes. These are the different types of photons which are possible. Now, the electron can take any of the ways. Depends upon the situation. But these all are possible. Understood? Okay. Now people, very, very interesting thing that I'm going to show. Very interesting thing that I'm going to show. Okay. That obviously, for every transition, there is going to be a photon which is getting released. Okay. For every transition, there is a photon which is getting released, and that photon will have lambda. Yes or no? And you all know the formula from chemistry, I think so. It comes out to be 1 by lambda is equal to rz square 1 minus n1 square 1 divided by 1 by 1 by n1 square minus 1 by n2 square. This is the formula that you get. Hai na? This is the formula that you get. You can keep this in mind, no problem. Keep this in mind, no problem. But this is a very useless formula actually. Hai na? This is a very useless formula. Okay. Now, see over here. This is the formula that you use to find out the wavelength of the photon that is getting released. Yes or no? But you don't keep this in mind. And many people they find it difficult, sir, what should be the value of n1 or what should be the value of n2? This should be a positive quantity, na? This should be a positive quantity. So obviously n1 has to be the smaller one and n2 has to be the bigger one. So over here n2 has to be the bigger one and n1 has to be the smaller one. But you don't have to keep this in mind. What formula you have to keep in mind? I'll tell. It is lambda is equal to 911, that is 1 by r, divided by z square into n2 square into n1 square divided by n2 square minus n1 square. This is the formula that you have to keep in mind. Yes or no? This is the formula that you have to keep in mind. Did you understood it? This is the formula that you have to keep in mind. Now see this. I'll solve a little problems and everything. Okay. See this, people. In a hydrogen-like atom, when an electron jumps from M shell, what is M shell? KLM. This is the third shell, n is equal to 3, to the L shell, KL, n is equal to 2. The wavelength of the emitted radiation is lambda. if an electron jumps from n shell KLMN, that is 4, n is equal to 4, to L shell KL, that is n is equal to 2, the wavelength of the emitted radiation will be how much? Okay, see this, simple. Lambda from 3 to 2, let's calculate. How much is it? 911 divided by z square, and this is hydrogen like atom. ठीक है, चलो z square into 3 square into 2 square divided by 3 square minus 2 square. I have used this formula. I've used this formula. ठीक है, this comes out to be 911 divided by z square, and this is 9 into 4 36, this is 9 minus 4, this is 5. Okay, lambda from 4 से 2, this comes out to be 911 by z square, and this is basically 4 square multiplied by 2 square minus 4 square minus 2 square. Yes or no? So this is 911 by z square, and this comes out to be 16 into 4 64, this is 64 multiplied by 16 minus 4, that is 16 minus 4 12. Yes or no? Now you just have to take the ratio. You just have to take the ratio. Simple. Take the ratio. So lambda of 3 is to 2 divided by lambda of 4 to 2. This comes out to be, if you take the ratio, 911 by z square, 911 by z square gets cancelled. They all gets cancelled. So this is 36 by 5 multiplied by 12 by 64. So this comes out to be this is 18, this is 32, this is 16, this is 9, and this is 4 3s are, this is 4 4s are. This comes out to be 27 by 20. See, you have got 27 by 20. So if an electron from n shell to the L shell from 4 to 2, what is the value of 4 to 2? Acha, so it will be basically lambda of 4 to 2 is basically 20 by 27 of lambda of 3 to 2. This is basically your answer. 20 by 27, option 4. Clear? Can I have some fire in the chat box if you understood this? Now, one more question, JEE 2020. Hydrogen atom in ground state is given an energy of 10.2 electron volt. So see people, hydrogen atom in the ground state is given an energy of 10.2 electron volt. So in the ground state, it has energy of minus 13.6 electron volt. It has been given energy of 10.2 electron volt. So right now, this is minus 3.4 electron volt. It has acquired an energy of minus 3.4 electron volt. That means this I know is in n is equal to 2. This is n is equal to 2. That means from the ground state, it has reached n is equal to 2, minus 3.4 electron volt. How many spectral lines will be emitted due to the transition of the electrons? Number of spectral lines is basically n into n minus 1 divided by 2. N is equal to 2. So this becomes 2, 1 divided by 2, cancel. Only one spectral line is possible. Obviously, only one spectral line is possible. What are the number of transition from 2 to 1? Only one is possible, no? Only from 2 to 1. That's it. Clear? Yes or no? Yes. Chalo. Moving ahead. Now the hydrogen spectrum. Now this is the last topic. Of atoms. Then we move on to nuclei. Nuclei is a very small, cute chapter. We are going to complete it very fast. Okay, people? We are going to complete it very fast. Don't worry about it. Hydrogen spectrum is the last topic, and then we are going to... Okay, thank you, Joanna. Thank you so much. Okay. First step again. Okay, you want the first step again? See this. The hydrogen atom is in ground state. So what is the energy? Minus 13.6, the energy of the ground state. It is given an energy of 10.2 electron volt. So I've given it an energy of 10.2 electron volt. Now what is the new energy? Minus 3.4. Minus 3.4 electron volt. Hai na? So that means if I want to calculate n is equal to 2, you can basically what? This is minus 13.6 into z square by n square. You can basically equate this. And this is hydrogen atom, so Z is equal to 1. So you get the value of N as 2 over here. Or I've already made you memorize that minus 3.4 is N is first excited state, or N is equal to 2. Okay. And that's it. N is equal to 2. So the number of spectral lines will be N into N minus 1, 2. You substitute 2 over here and you get the value of number of spectral lines is N is equal to 1. Now hydrogen spectra. People. Now very important, people. Very important. This hydrogen spectrum, or this spectrum that you get, is actually a fingerprint. Of the atom or the element. It is like fingerprint. Like for example, no two fingerprints match in this whole world. So for every element, there is a unique spectrum, and by this spectrum, you can actually identify the element over here. Okay. Now what is happening? See this, people. Now what is happening? You have a hydrogen sample. And you subject it with electromagnetic radiation. Now, it is not something like we only subject it to visible radiation. We can also subject it to X-ray, UV, X-ray and UV also, and also infrared. But obviously, due to the higher frequencies and lower frequencies, we are not able to see it. The visible region is something which we can see, and it is in the visible region, obviously. Okay. Now, when we pass this continuous spectrum or this electromagnetic radiation into this hydrogen sample, so when you pass this continuous spectra, you get something like this. This is the hydrogen absorption spectrum. That means some discrete frequencies are missing from here. What is this discrete frequencies? This frequency is basically, or discrete lambdas are missing over here. So this lambda or this frequency is basically this thing. Like over here, if the electron was in the in ground state, N is equal to 1, it absorbed 12.09 electron volt electromagnetic radiation. That particular wavelength, that particular frequency, it absorbed, and it went to the excited state. Are you all able to understand it? It went into the excited state. So in the similar way, all the ground state electrons, they absorb the energies which are required by them to move on to the excited state. And that is why where is it? When you pass a continuous spectrum, only some discrete frequencies and wavelengths are missing from it. Are you all able to understand this? And after 10 to the power minus 7 seconds or 10 to the power minus 8 seconds, these electrons de-excite again, and they again send a photon of the similar wavelength that they have absorbed. So you get again the hydrogen emission spectrum. So in a dark band or a dark paper, you again get those wavelengths back again. So this is something like this. Hydrogen emission spectrum plus the hydrogen absorption spectrum is basically equal to the continuous spectrum. Are you all able to understand this? Are you all able to understand this? What I'm saying? What am I saying? Again, you pass the continuous spectrum in the hydrogen sample. The hydrogen sample will only absorb those frequencies or wavelengths which are required by the electrons to excite itself to the excited state. That is the reason only discrete wavelength and frequencies are missing. After 10 raised to minus 7 or 10 raised to minus 8 seconds, all the electrons will de-excite again and release those wavelengths back again. That is the reason you get the hydrogen emission spectrum over here. Yes or no? Is this cool? Yes. So, of all the spectrum over here, you have different scientists who have studied this spectrum, and you have Lyman, Balmer, Paschen, Brackett, Pfund. So how to memorize this, people? LUV BP. Oh, sorry. I'll do something like this. LBP, BP. Okay. See this. This is Lyman, Balmer, Paschen, Brackett, Pfund. Okay. Lyman, Balmer, Paschen, bracket, P fund. How to memorize, in which region do they lie? Simple. Love your BV, otherwise PBP. Okay, what is it? Love your BV, otherwise PBP. That's it. So Lyman, it lies in the UV region. Balmer lies in the visible region. Paschen lies in the infrared, and rest everything in the infrared. Paschen infrared, bracket infrared, and P fund also infrared. Okay. Okay, people. Yes. Love your BV, otherwise PBP. Simple. Okay. So Lyman, it lies in the UV region. This is visible, and rest all of them are in the infrared. Okay. Now what is Lyman region? What is Lyman? Lyman series is basically of all the spectral lines. All the spectral lines that come and end up at n is equal to 1. They belong to the Lyman series. All the spectral lines which end at n is equal to 2, they are the Balmer series. All the spectral lines which end at n is equal to 3, they are the Paschen series. And so on, bracket is n is equal to 4 and P fund is n is equal to 5. Yes or no? Yes or no? Again, all the spectral lines which end up at n is equal to 1 after de-excitation is Lyman. After those who end up at n is equal to 2, Balmer. Those who end up at n is equal to 3, Paschen. N is equal to 4, n is equal to 5. Now, there are some names also. There are some names also for it. This first one, this first line that you are able to see, this first line, this is called as the H alpha line, H alpha. This second line is called as the H beta. This third line is called as the H gamma. This fourth line is called as the H delta, and so on. And all of the line which come from infinity to 1, this is called as the series limit. This is called as the series limit. Series limit for Lyman series. What will be the series limit for Balmer series then? From infinity to 2. What will be the series limit for Paschen series? From infinity to 3. For bracket series, from infinity to 4. From P fund series, from infinity to 5. Are you all able to understand this? Are you all able to understand this, people? Trick अच्छा था ना? Are you all able to understand this? Yes or no? So series limit is basically all of the spectral lines from infinity to 1, Lyman. Series limit for Balmer, infinity to 2, Paschen, infinity to 3, bracket, infinity to 4, P fund, infinity to 5. Okay. Again, same thing, people. Same thing. Now, this is one homework that I am giving you. I'll be solving for Lyman and Balmer. For the rest, it is homework for you all. You have to comment. Okay, you have to comment down in the comment section. Okay, you have to comment down in the comment section. You have to comment down in the comment section. See, for Lyman, the first spectral line, the first spectral line will be what? It will be from n is equal to 2 to n is equal to 1. Yes or no? Yes, sir. It is from n is equal to 2 from n is equal to 1. What will be the lambda? Lambda is very easy, sir. 911 divided by z square, and this will be 2 square, 1 square, 2 square minus 1 square, the formula that I gave you. This comes out to be 911 by z square. This is for hydrogen, okay? This is for hydrogen atom, no? So z is 1 over here. Z is 1 over here. Hydrogen atom, no? So z is 1. So this becomes 911 and this becomes 4 divided by 3. This is your answer. This is the lambda of the first spectral line. First spectral line. Similarly, what will be the series limit? What will be the series limit? Series limit will be from infinity to 1 for Balmer series. From infinity to 1. Now, I'm not going to use this formula because it's from infinity. I can't put infinity over here. So I have to use the original formula. That is 1 by lambda is r z square 1 by n1 square minus 1 by n2 square. Okay? So n2 square will be infinity. So this becomes a 0. 1 by infinity is 0. 1 by n. So this comes out to be 1 by lambda is r. Z is equal to 1 because hydrogen. And this comes out to be, yes, this comes out to be this 1 by 1. And lambda comes out to be 1 by r. which is basically 911 angstrom. So this is basically the series limit. This is basically the series limit. Are you all able to understand this, people? Are you all able to understand this? Are you all able to understand this? I'm just gonna do it for Balmer series as well. I'm just gonna do it for Balmer series as well. Then the rest is homework. You have to comment down. Okay, you have to comment down. Balmer series. What is Balmer series? The first line is going to be from n is equal to 3 say 2. N is equal to 3 say 2. What will be the lambda? It will be 911 by z square, and this will be 3 square into 2 square, and this will be 3 square minus 2 square. So this comes out to be 911. As this is hydrogen, z is equal to 1. This is 9 into 4 36, and this is 9 minus 4 5. Yes, this many angstrom is the lambda of the first one. First line of the Balmer series. What will be the series limit? What will be the series limit? Series limit is from infinity to 2. So 1 by lambda is r z square 1 by n1 square minus 1 by n2 square. So infinity you have to put it over here. So this becomes a 0. So this becomes 1 by lambda is equal to r. This becomes 1 by 2 square. So this becomes lambda is equal to 4 by r angstrom. This is the series limit. This is the series limit. Did you all understood this? Did you all understood this, people? Yes or no? Can I have some fire in the chat box if you understood this? So similarly, you have to find out the first line for Paschen series and the series limit for the Paschen series and bracket and P fund also. This is homework for you all. You have to comment down. Okay? You have to comment down. I'll be looking for the comments. Okay, people? Okay, people? This is homework for you all. Homework for you all. Okay, people? You have to comment it down. Okay, people? Yes. Now, people, just electron in uniform magnetic field. Electron in uniform magnetic field. So if you have an electron which is in uniform magnetic field, you have to understand that the electron will execute uniform circular motion, UCM. Okay, so basically the mv square by r, the centripetal force provided which is required for the circular motion to take place, comes from the magnetic force, that is QVB. Okay, and over here you are able to understand V gets cancelled over here. You don't have, if you don't understand this because you have not studied magnetostatics yet, but don't worry about it. So this right over here comes that R is equal to mv by qb. mv by qb. This is the formula that you get over here. Okay. Yes, I'll give you break. Don't worry. Okay, I'll give you break. Okay, people. I hope so this is understood. This is the radius that the electron travels in the circular orbit. Okay. Just one question, people. Just two questions. Okay. Two questions for you all, and then we'll move on to the nuclei chapter. This is a very good question. This is a very good question, people. Very good question. Okay, very good question. See this. An electron and a proton are separated by a large distance. The electron starts approaching the proton with energy 3 electron volt. So the electron right now has an energy of 3 electron volt. It is approaching the proton. The proton captures the electron and forms a hydrogen atom in the second excited state. That means in the second excited state, matlab n is equal to 3. So earlier the energy of the electron was 3 electron volt. Now the electron is in the second excited state. That means n is equal to 3, the energy of the orbit in the third orbit comes out to be minus 1.5 electron volt. Yes or no? That means the electron has lost energy. Earlier it was 3 electron volt. Now it is just minus 1.5 electron volt. The electron has lost energy, and this lost energy is in the form of a photon. That is what it is saying, that the resulting photon is incident on a photosensitive metal of threshold wavelength ithna. First of all, let us try to find out the energy of the photon. What it will be? It will be just the difference of the energies. It will be 3 minus 1.51. This comes out to be 4.51 electron volt. This much amount of energy, the photon will get released. The photon will get released. Then this is the incident energy of the photon. Can I basically say this is the incident energy of the photon? This photon is incident on a photosensitive metal of threshold wavelength 4000 angstrom. What is the maximum kinetic energy of the emitted photoelectron? I already know from the photoelectric equation that Ke max is energy incident minus the work function. I already know this. So Ke max will be energy incident. What is the energy incident? It is 4.51 electron volt minus what is the threshold? What is the work function? Can I write it as 12400 divided by 4000 divided by 4000. Can I do this? Can I do this, people? Can I do this? Yes or no? Can I do this? Yes or no? Can I do this? What is minus 1.5 electron volt? See this. What is happening? Electron, earlier it has 3 electron volts of energy. Then proton captured it and the electron forms a hydrogen atom in the second excited state. What is second excited state? Matlab n is equal to 3. And what is the energy of the system in n is equal to 3? What is the energy of the system in n is equal to 3? 1, 2, 3 minus 1.5 electron volt. Minus 1.5 electron volt. So this is the energy now. That means obviously it had earlier 3 electron volt. Now it has energy minus 1.5 electron volt. It means it has lost energy, and that losing of energy is basically in terms of photon. In the terms of photon. Yes or no? Yes or no? And this comes out to be 1.41 electron volt. This is the maximum kinetic energy of the electrons. Did you all understood this? Did you all understood this, people? Yes or no? Did you all understood this? Yes or no? Okay, can we do this? This is a NEET 2025. NEET 2025. You must have all solved this. You must have solved this in your NEET 2025 paper. Last question and then nuclei. Last question and then nuclei. What it is? A particle of mass m is moving around the origin with a constant force F. First of all, this question should be challenged actually, because the force is not constant. The force is not constant. Why the force is not constant? Because when a particle m is moving along the origin with a constant force pulling it towards the origin, it is moving in circular motion. The force, the direction of force keeps on changing, no? The direction of force keeps on changing. So if the direction of force keeps on changing, it's not a constant force. So actually there is some problem with the question actually, hai na? So if the Bohr model is used to describe its motion, the radius of the nth orbit and the particle speed v in the orbit depend on n as what? This is what the question is. So basically they are saying that this f, that is mv square by r, is basically a constant k. This is basically a constant k. So basically can I say that v square is k into r divided by m. Now k is a constant, m is a constant. So basically can I say v square is directly proportional to r? Yes, I can say this. I can definitely say this. Now people, see this. I also know that MVR is equal to NH by 2 pi. NH by 2 pi. Okay. Now, from this, can I basically say that R is directly proportional to V square? And also, I can also say V is directly proportional to square root of R. I can basically derive both of these things. I can derive both of these things, that I take the square root. So V is directly proportional to square root of R, and R is directly proportional to V square. So if I put this fellow over here, that R is directly proportional to V square, can I get V cube is directly proportional to N? So R is V square. So I just put V square over here. So V cube is directly proportional to N. And this becomes V is directly proportional to N ki power 1 by 3. N ki power 1 by 3. And then I substitute this value of V over here as square root of R. What is square root of R? Square root of R, can I write this as V is directly proportional to R raised to half, R raised to half, R raised to half. So R raised to half multiplied by R is R raised to 3 by 2. So basically, can I say R raised to 3 by 2 is directly proportional to N. So R is directly proportional to N ki power 2 by 3. This is what we are getting. This is what we are getting. This is what we are getting. And this is the answer. V is directly proportional to 1 by 3. N 1 by 3, R N 2 by 3. Option 3. Okay. I've given a lot of questions, okay? I've given a lot of questions over here for you all to practice. When I send this PPT, you can all practice this questions. You can all practice these questions. And all of these are JEE PYQs and NEET PYQs. Okay. Are you all ready, people? Are you all ready? Are you all ready? Can I have some fire in the chats, people? Or do you want a break? How do you want a break? Or do you want a break? Now I can say that when the class will get over, it will exactly, I think it will take just an hour or something. Okay, just an hour, just little greater, more than an hour. Yeah, greater than an hour. That's it. Okay, you are ready or you want a break? Break? You want a break or something? You want to grab a coffee or something? Yes. 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 Or should we continue? It will just take just an hour or so. Just an hour or so. No break. No break. No break. No break. Okay, chalo. No break. No break. No break. And that's what we are gonna do. Okay. No break. No break. Let's just finish this. Let's just finish this. है ना? Let's just finish this. Okay. Chalo. Let's just finish this. Okay. Semiconductor. I think it will be the next chapter. Okay. Okay. Okay, chalo, no break, no problem, no problem. Acha, nahi to I think what we can do, I think we can just take a 3 minutes break so that I can take a cup of coffee. So that I can take a cup of coffee. Is it possible? Yes. I'll just give you a 3 minutes break. 3 minutes break and 3 minutes break and just I'll take a cup of coffee and come. Okay? Yes, go with the flow. I'll just take a cup of coffee and come. Okay, just a 3 minute break. 3 minute break. I'll just take a cup of coffee. Everyone should be here. Everyone should be here. Everyone should be here. Okay, don't miss it out. Don't miss it out. You're gonna enjoy it. You're gonna enjoy it. Okay, chalo. I'm back, people. I'm back. Yes, let's start. Can we start? Can we start, people? Yes, yes. Can I have some fire emojis in the chats? Can I have some fire emojis in the chat and then we'll start? Can I have some fire emojis in the chat and then we'll start? And please like the session. Please like the session. Let's go. है ना? चलो. Okay. Okay, chalo. Good morning, good morning, good morning. Now I need your support, okay, people, because continuously, teaching for 6-7 hours, it's a little bit, it's a heavy task, okay. I need your support, okay. I need your support, okay. You should encourage me by all those fire emojis, green hearts, red hearts, yellow hearts, any heart possible, okay. Let's start with nuclei, okay. We have studied atoms. Now we're gonna go inside the atom and study the nucleus, okay, people. Again, this is the flow of the chapter that we're going to follow. This is the flow of the chapter that we're going to follow. We're going to first study all about the nucleus or all about the nuclei, which is basically a plural word. Nuclear forces, mass energy equivalence, very important. Mass defect and binding energy, again very important. Nuclear fission and fusion, radioactive decays, and a lot of JEE, NEET and AIMS PYQs. Okay, that's what we're going to do. Okay, let's start. Okay, chalo. Let's start with the nucleus. Let's start with the nucleus. The nucleus, and also like the session, okay? What is nucleus? Nucleus is the central core of every atom, obviously, है ना? It is the central core of every atom. It is situated in the center, है ना? It was discovered by Rutherford in alpha scattering experiment, है ना? So what did Rutherford say? That all the positive charge and all the mass of the atom is concentrated at the center of the atom called as the nucleus, है ना? Then I've already said order of nuclear size is 10 raised to minus 15 meters or 1 FM. Or 1 FM. है ना? And the order of the atom is 10 raised to minus 10 meter or 1 angstrom. There is a difference of 10 raised to 5. That is how much the difference is. That is how the difference is. Okay, people? Yes. Now, there is something that I want you all to notice over here. That is something that I want you all to notice over here. Now, I basically, okay, let's understand this. Okay, let's understand this, people. Okay. I hope so, and I know that you have all attended Wasim sir's lecture of mole concept. Yes or no? Did you all attend Wasim sir's lecture of mole concept? Yes, you did attend. And there he defined one thing. He defined one AMU. Yes, he did define one AMU, right? He did define one AMU. What is one AMU? One AMU as defined by Wasim sir, it was basically 1/12 mass of the carbon-12 atom. Yes, that was basically what it defined as. है ना? What is one AMU? What is one AMU? One AMU is basically 1/12 mass, 1/12 mass of the mass of what? The carbon-12 atom. Yes or no? This is what it defined as. This is what it defined as. Yes. This is one AMU. And this comes out to be 1.66 into 10 ki power minus 27 kg. This is basically one AMU. Yes or no? This is what it defined. Yeah, or 1 by n. Exactly. Now, people, see this over here. Okay. Oh, arey yaar. There is some. People, some corrections over here. Okay. There is some corrections over here. Okay. There is some corrections over here. I just wrote the mass. Okay, this is not 26, this is 44. Okay, this is 44, this is 27, this is 27, and this is not this one. This is 9.1 into 10 raised to minus 31. Yeah, this is what the correct value is. Okay. Yeah. So 1 AMU is defined as 1 by 12th mass of the carbon 12 atom. That is 1.66 into 10 raised to minus 21 kg. है ना? And the mass of the proton is 1.67 into 10 raised to minus 27. And neutron is 1.6744 into 10 raised to minus 27. Electron is 9.1 into 10 raised to minus 31 kgs. This we are not interested. This is a very less mass. This is a very less mass. We can basically neglect it. If I look it in the U units, this is 1.00727, this is 1.00866, this is 0.0055. Relatively, electron has no mass, neutron and proton we can consider it to be equal. Okay. Now where is the concept, people? Now where is the concept? People, I want you to understand. I want you to understand that why is 1 AMU? Why is 1 AMU less than mass of proton and mass of neutron? Why is it less? Yeah, I'll see about the DPPs. I'll have to talk with Yawar sir. This is the most fundamental concept of this chapter. I mean, if I divide the carbon 12 into 12 equal parts, and one part of it is 1 AMU, but still I am getting 1 AMU less than mass of proton and less than mass of neutron. See, 1 AMU is 1.66, proton and neutron is 1.67 and 1.67 over here. Why am I getting this? Why am I getting this? And obviously, over here you are able to understand the mass of neutron is much more greater than mass of proton. Hai na? Why is this? This is the most fundamental concept of this chapter. Please keep this in mind. Please keep this in mind. Mass of proton plus neutron inside the nucleus is less than isolated proton and neutron. मतलब है? What do you mean, sir? What do you mean? That means if there is a proton and a neutron inside the nucleus, the mass will be less. The mass will be less. And if it's an isolated proton outside the nucleus, the mass will be more. Hey? Where is this mass going? Where is this mass going? Where is this mass going? That is E is equal to mc square. That is E is equal to mc square. The mass is getting converted into energy. Are you all able to understand this, people? Are you all able to understand this? Are you all able to understand this? So, the mass of the proton and the mass of the neutron is much more greater than 1 AMU. Why? 1 AMU. Why? Because inside the nucleus, the mass of the proton and the neutron is less than the mass of the proton and the neutron outside the nucleus. E is equal to mc square. We are going to talk about this. We are going to talk about this. Don't worry. And protons and neutrons together are called as nucleons. Protons and neutrons together are called as nucleons. Okay? Like we stay in India, we are called Indians. So protons and neutrons stay inside the nucleus. That's why they are called as nucleons. Simple. Clear hai? Clear? Okay. Let's understand. Let's understand, people. Okay. Now, representation of an atom and a nucleus. Representation of an atom or a nucleus, very, very important to understand, people. I'm sure that you must have studied in chemistry, but it's my responsibility to teach you this again. This is an element X. This is A is the atomic, it's a mass number, and Z is the atomic number. Hai na? So this is your atomic number. This is the mass number. This is basically your mass number, and this is basically your atomic number. This is basically your atomic number. Now, what all these things signify? What all these things signify? Z. Z gives you number of, what does Z give you, people? What does Z give you? What does Z give you, people? Batao. What does Z give you? And please like the session as well. What is Z, people? Can anyone tell me what is Z? Come on, you all studied chemistry. It is very easy for you all. You have all studied chemistry. You have all studied chemistry. What is Z equal to? What is Z equal to? Come on, tell me the answer. What is Z equal to? Z equal to? Z is basically equal to the number of protons inside the nucleus. Number of protons inside the nucleus. Okay, people? And this is also equal to the number of electrons, but with a condition. But this is also equal to the number of electrons with a condition. No, it's not the number of electrons, it's the number of protons. Why, I will say. It is only equal to the number of electrons if the atom is neutral. If the atom is neutral. Now, why do I say so? No, it is always the number of protons, that I am sure of. But number of electrons, that we are not sure of. Why I will say this? People, it is very easy. It is very easy. It is very easy to understand this. See this. If I have Na over here, if I lose one electron, it gets converted into Na plus. It gets converted into Na plus ion. So over here, the electron is coming out, but still the proton number is still the same. Over here, chlorine, it gets one electron and gets converted into Cl minus. It gets one extra electron and gets converted into Cl minus. But yet the number of proton is the same. Here I cannot say that Cl and Cl minus has the exact number of protons. No, it has one extra electron. Here it has one less electron. So in the case of atom, when it is neutral, I can say that number of proton is equal to number of electron. But in all other cases, I can say that Z is your number of protons. I think so. I am absolutely clear over here. Yes or no? Yes or no? Yes, clear. Okay. Now, so this is number of protons and number of, which is equal to number of electrons. So Z over here is proton, which is equal to electron. Very good. Number of proton equal to number of electrons. है ना? ठीक है. Cool. Okay. Now, what is mass number? Mass number is basically the number of nucleons. And what is nucleons? Number of nucleons is basically the total number of neutrons and protons, the total number of protons and neutrons inside the nucleus. That is exactly what is, that is number of nucleons. So can I basically say that this is number of proton plus number of neutrons. Yes or no? Yes or no? Clear? Okay. Okay, people. Okay. So A is number of nucleons or number of proton plus number of neutrons. Now, if I denote number of neutrons with N, so can I basically say N is basically your A minus Z. Is this clear? Sir, how, sir? I'll explain. What is A? It is the number of nucleons. From nucleons, if you minus Z, that is number of protons, what do you remain? What is remaining? Number of neutrons. So number of neutrons is A minus Z. I hope so this is very clear. I hope so this is very clear. Yes or no? If this is clear, can I have some fire in the chat box? If this is clear, can I have some fire in the chat box, people? Yes or no? Okay, very good. Let's move ahead. Okay, chalo. Question for you all. A nucleus represented by the symbol this has what? Z protons and A minus Z neutrons, Z protons, A neutrons, A protons, Z minus A neutrons, Z neutrons and A minus Z protons. Come on, people, this is very easy. This is very easy for you all. Very easy for you all. Very easy for you all. So obviously baat hai that Z is number of protons. So Z is protons. So this is wrong and this is wrong. And what is A? A minus Z is the number of neutrons. This is right. Option A is right over here. ठीक है? Okay. Next. The mass number, okay, now this is a very important question. Very important question. Very, 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 very important question, people. Please read it. Please read it. Please read it and tell me the answer. And tell me the answer, what do you think? The mass number of a nucleus is always less than its atomic number, always more than its atomic number, sometimes equal to its atomic number, and sometimes less than and sometimes more than its atomic number. What do you think? What do you think? It's a 2003 NEET question. 2003 NEET question. 2003 NEET question. Yes. Yeah, actually, I'm a Chennai Super Kings fan. Yeah. Point to be noted, I'm a CSK fan, Chennai Super Kings fan. Okay. Yeah. Okay, most of you all think it is B. Yeah, see, you have again fallen into the pit. You have again fallen into the pit. Again, you have fallen into the pit. NTA sets up a trap and you just fall into it. Easily, you just fall into it. I'll give you an example. I'll give you an example. People, what do you think of hydrogen? Hydrogen, sir, is mass number is 1, atomic number is 1. Sometimes it is equal also. C. C is your answer. C is your answer. Hydrogen. you again fell into the same trap that the NTA set. Okay, people, it's a good question. You can mark it. Okay, it's a good question. You can all mark it. Next. Okay, people, chalo. In the nucleus of sodium, the number of protons, neutrons and electrons will be how much? First of all, let's calculate protons. Sir, protons will be Z is equal to 11. This is protons for you. This is protons. Simple. Sir, number of neutrons. Sir, neutrons is, sir, A minus Z, sir. A minus Z. A minus Z is 23 minus 11, sir. So, this is 2. This is 1. This is number of protons. What is the number of electrons? Electrons. Sir, electrons will be also, sir, 11 only, na, sir. It will be 11. It will be 11. Sir, I think, sir, answer will be 11. 11, 12, 11. 11, 12, 11. It's not there. Eh? Did we do something wrong? Are Baba, we have talked about nucleus. Is there any electron inside the nucleus? No, it's not there. So the correct answer is 11, 12, 0. 11, 12, 0. It's not there. Okay. Okay. Even if they try, even if they have told us to find out the number of electrons, they have already told that we have to find out inside the nucleus, not inside the atom. Not inside the atom. So the correct answer is 11, 12, 0. Yes. Clear? Okay. Now, types of nuclei. Now, types of nuclei. People, how to remember this? How to remember this? Can you all tell me how many people over here have difficulty remembering this? Have difficulty remembering this? Have difficulty remembering this? How many people over here have difficulty remembering this? What is an isotope? What is an isotone and everything? How many of you all have difficulty remembering this? Again and again being trapped. I know, see, as a teacher, I know where you will get trapped. No, that's why. Okay, tell me how many of you all have difficulty remembering this? I have a very, very good trick for this. See this. See this, people. Isotope. P. This is P over here. That means same number of protons. Same number of protons. See, 92, 92. Same number of protons. That is isotope. Same Z, but different neutrons. Different number of neutrons. Isobar. Bar in Hindi it means weight, no? In weight, mass, bar, hai na, weight. It means weight. Isobar, same A, mass number, it will be same. 40, 40, 40, 40, 40. Same number mass, same number of nucleons. Isotone, N, same number of neutrons, A minus Z. See, 36 minus 16 also 20, 37 minus 17, 20, 38 minus 18, 20, 39 minus 19, 20, 40 minus 20, 20. So, isotone, same number of neutrons. In the spelling only they have kept the clue. Isotope, P, same number of proton. Bar, weight, same number of mass number, same mass number, that is same number of nucleons. Isotone N, same number of nucleons. How was it? How was it? It's not even a trick actually. Okay. Okay, now let's talk about isotopes of hydrogen. Very important, people. Isotopes of hydrogen, very important. Isotopes of hydrogen, very important. Okay, chalo. See this, people. This is the normal hydrogen that is found, 1H1, called as the protium. It has basically how much? It has one proton, one electron, and 0 neutrons. What is deuterium? Deuterium, everything is same, just one addition of neutron. One proton, one electron, and one neutron. What is tritium? Tritium is very unstable and it is found very less. One proton, one electron, but two neutrons. Yes or no? Yes or no? This is what exactly is protium, deuterium, tritium. Isotopes of hydrogen. Very good. Moving ahead. Size of the nuclei. Size of the nuclei. Okay, people. Let's understand size of the nuclei. Let's understand size of the nuclei. Okay. Now, people, as the number of nucleons in the nucleus increases, its size also increases, and relationship between its radius and mass number is what? See, this is very much, logical. है ना? As the mass number is increasing, the number of nucleons is increasing. If the number of nucleons is increasing inside the nucleus, obviously the radius of the nucleus has to increase to accommodate the nucleons. Yes or no? Yes or no? What did I say? More nucleons, that means more will be the radius of the nucleus. है ना? That is what the relation that we are getting. The relation is radius of the nucleus, this is radius of the nucleus, okay, is directly proportional to A raised to 1 by 3. A raised to 1 by 3. This is the relationship that we are getting. And if we take out the constant of proportionality, if we take out the proportionality, so R is basically equal to R naught A raised to 1 by 3. This is the relation that we are getting over here. This is the relationship that you are getting over here. And over here, R naught is basically 1.1 Fermi, or 1.1 into 10 raised to minus 15 meter. This is the relation. This is the relation. Okay, people? Yes. Yes. Very good. 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 Who all are full of excitement and full of strength till now, people? Who all are full of excitement and full of strength now? Yeah. Who all have promised me that they will end up till the end of the session? Okay. Those who promise me that, can I have some fire emojis, people? Okay. Next, volume of the nuclei. Volume of the nuclei. It's very easy, people. What is volume? Volume of the nuclei is 4 by 3 pi r cube, because I already know that the nucleus is a sphere. So the volume of the sphere is 4 by 3 pi r cube. So volume is going to be 4 by 3 pi into r cube. What is r cube? This fellow. R naught A raised to 1 by 3, 3. If I open this, what I get? I get 4 by 3 pi r naught cube and A. So see this A raised to 1 by 3 and this 3 gets cancelled. This fellow gets cancelled. Now, if you all notice over here, this whole thing is a constant. 4 by 3 constant, pi constant, r naught cube constant. Only A is the variable thing over here. So I can definitely say that the volume of the nucleus is directly proportional to the mass number. Clear, people? Clear? Is this understood? Is this understandable? Yes or no? Is this understandable? Yes or no? Very good. Very good. Okay. Okay. Now, before moving it, one more topic over here, that is nuclear ratio. I forgot to add the slide over here. So nuclear ratio. Okay? Okay. Nuclear ratio. What is nuclear ratio? I'll say. See this, people. Okay, okay, no problem, no problem. Nuclear ratio. What is nuclear ratio? Nuclear ratio is basically the ratio of the ratio of neutrons, the number of neutrons and protons. That's it. This is basically the nuclear ratio. This is basically the nuclear ratio. Okay, people. So see this. So nuclear ratio is basically your n by z. It is n by z. N is your number of neutrons and z is your number of protons. Okay, sir. Sir, can I write n as a minus z, sir? Yes, you can definitely write it as a minus z divided by z. Sir, can I also write this as a minus z divided by minus 1? I've just divided it. I've just divided it. Yes. This is basically the nuclear ratio that I'm getting. So sometimes in questions they may ask you to find out what is the nuclear ratio of this nuclei. What is the nuclear ratio of this nuclei? Okay, so you have the formula over here, and then you can basically calculate it. Okay, people. Moving on. Mass of a nuclei. Mass of a nuclei. Yes, we will do a little bit of question practice. Okay, we will do a little bit of question practice. Okay, people. Now see this, people. Mass of the nuclei. Now, mass of the nuclei. Can I write this as? This is very easy. This is very easy to understand. Okay. Can I write this as? It is the mass of the neutrons. That is number of neutrons into mass of neutrons plus z into mass of the protons. Can I do something like this? Can I write something like this, people? No, this is not the last topic. People. This is not the last topic. N is the number of neutrons into mass of neutrons plus number of protons into mass of protons. This is exactly the mass of the nuclei. I can also write this as A minus Z into mass of neutrons plus Z into mass of proton. Yes, sir, I can also definitely write something like this. I can definitely write something like this. Now, as we all know, mass of neutron is approximately equal to mass of proton. We all know this. है ना? So I can basically write this as this mass of neutron as A minus Z into mass of proton plus Z into mass of proton. I take the mass of proton common. This becomes A minus Z plus Z. So this becomes A into mass of proton. A into mass of proton. Yes or no? Don't worry, we are going to complete it very fast. And see, because it's very important. It's very important, people, because many questions are coming. Do you want to fulfill your wish of becoming a doctor? See, it's very simple. I am also, working hard over here. You should also work hard. It is not right if the teacher only works hard and the student does not, right? है ना? So mass of the nuclei can be written as A into mass of proton. Simple. Or A into mass of neutron. That's your wish. Okay, people? Yes. Now let's talk about the density of the nuclei. Yes, the density of the nuclei. Let's understand the density of the nuclei. Density is basically, rho is basically mass divided by volume. Yes, sir. Sir, what is mass, sir? Sir, mass is A into mass of proton. That is what we have studied right now. A into mass of proton. Yes, sir. And volume can be written as 4 by 3 pi r naught a raised to 1 by 3 cube. Yes or no? And if you all notice over here, This comes out to be A into mass of proton, the whole divided by 4 by 3 pi r naught cube and A. Over here, if you'll notice, the A and A gets cancelled out. What you receive is MP divided by 4 by 3 pi r naught cube. This is what you're getting. And this is a very important observation, people. The density of the nucleus is not at all dependent upon the number of nucleons present. Oh my God. Are you all able to understand this? Are you all able to understand this? See this? Mass of proton is constant, 4 by 3 is constant, pi is constant, r naught is constant. This whole thing is constant. That means for any nuclei present over there, any nuclei present over there, the density of a nuclei is gonna be a constant. Because it is not dependent upon the mass number. It is not dependent upon the mass number. And the value is 2.3 into 10 raised to 17 kg per meter cube. That means any nuclei, yes, it is sufficient for JEE means. Any nuclei in this whole world, the density of that nuclei is going to be 2.3 into 10 raised to 17 kg per meter cube. Why? Because it is not depending upon the mass number. Clear? Chamka? Yes or no? Can we move ahead? Can we move ahead, people? Can we move ahead, people? Yes or no? Yes or no? This is constant. Okay, people? Chalo. Let's move ahead. This is one question, people. One question from 2006 NEET. From 2006 NEET. What is it? The radius of germanium nuclide, okay, the radius of germanium nuclide is measured to be twice the radius of beryllium. Twice the radius of beryllium. This is the relation that we are telling. Then the number of nucleons in germanium is. That means, simple. We all know R is R naught A raised to 1 by 3. This is the relation that we know. Just substitute over here. So this becomes R naught A raised to 1 by 3 is equal to 2 times of R naught. And what is the mass number for beryllium? Mass number is 9. So 9 raised to 1 by 3. Yes or no? Okay. So R naught and R naught gets cancelled. I'm cubing on both sides. I'm taking cube on both sides. So this becomes A is basically 2 cube becomes 8, and this becomes 1 by 3. The 1 by 3's cube becomes 1. So this becomes 8 into 9, that is 72. So the mass number of germanium comes out to be 72. Clear? Clear, people? Chamka? Yes. Can I get some fire emojis in the chat if you understood this whole concept? Next question, people. Next question. What is the question? Two nuclei have their mass numbers in the ratio of 1:3. Okay. So basically they are saying the A1 by A2, they have told us 1:3. They have told the ratio of their nuclear densities. I've already told you nuclear densities is a constant for all nuclei, and the value is 2.3 into 10 raised to 17 kg per meter cube. This is constant. It does not depend upon the mass number. Irrespective of everything, it is going to be 1:1. Because the density of the nuclei is same for everything. That is the reason the ratio of the densities will be 1:1. 1:1. Simple. Chamka. Acha, chamka in Hindi means you have understood. Okay. Chamka in Hindi means you have understood. Okay. Clear? Clear, people? Arey, where is your chat? Yeah. I mistakenly. Okay. Okay, chalo. Let's move ahead. Okay, chalo. Let's understand forces acting inside the nuclei. Okay. This is all colorful notes for you all. है ना? Colorful notes for you all so that you find it easier to study. है ना? Okay. What are all the forces which are acting inside the nucleus? The first force is the gravitational force. The gravitational force. Obviously, The gravitational force is basically these neutrons and protons, they have masses, and obviously masses, they have the force of attraction. But this force, this gravitational force is a very weak. It is the weakest force of nature. So basically we can neglect it as well. We can neglect it as well. We can neglect it. The second one, is the electrostatic repulsion. Obviously, inside the nucleus we have protons. Inside the nucleons we have protons. We have many protons, and obviously these protons are going to exert repulsive forces against each other. Now you may have this question: inside the nucleus, we have so many protons. Then how is it possible? How is it possible that the nucleus is not just just tearing apart? Why isn't it the nucleus just tearing apart? Why isn't the nucleus just tearing apart? So obviously there is electrostatic repulsive forces as well. But why isn't the nucleus just tearing apart? It is due to this nuclear force. It is the strongest force. It is the strongest force. It is the strongest force. Strongest force. I'll tell you why. See. So inside the proton, है ना? So inside there are protons and neutrons. So this proton and proton, they are going to have repulsive forces against each other. So obviously they'll try to break the nucleus. But this nuclear forces, they act, they are charged, so these nuclear forces, they act irrespective of the charges. You have to understand that the force between neutron and neutron, the force between proton and proton, and the force between neutron and proton, all are same. They don't care about the charge that you have. And nuclear force is the strongest interaction. It is a very strong force. It is a short range force. It only works in short distances, but it is a very strong force. And this force is attractive in nature. And this force is responsible for gluing the nucleus together. Are you able to understand him? Are you all able to understand me, people? Yes or no? Are you all able to understand me? Yes. So even though the electrostatic repulsive forces, they want to break the nucleus apart because of the repulsive forces, the nuclear force, being a very strong force, they try to keep the nucleus glued together. Are you all able to understand this? Yes or no? Yes, strongest force in the universe. Okay. See, features of nuclear force. Strongest force in the nucleus. है ना? Strongest force in the nucleus. Works only between the nucleons. Very short range force. Independent of charge. Does not care whether it's a neutron, it's a proton, nothing. Does not care. It is spin dependent. Now obviously, as electrons also have spin, the nucleons, the neutrons and the proton also have spin. So they are spin dependent. So basically, the nucleons which have the same sense of spin, up spin and down spin, which have same spin, they will have much more stronger nuclear force between them. Okay. And it is not a central force. See, when we are studying electrostatic, Coulomb's law and gravitational, Newton's laws of gravitation, we always say that the force is acting along the line joining the two bodies. Yes or no? But this is not a central force. Okay, people, this is not a central force. है ना? And this does not follow this nuclear force. This nuclear force over here is not directly proportional. It's not directly proportional to 1 by r square or something. It's not directly proportional. Okay, people? Okay. Now, let's understand Einstein's energy mass equivalence. Let's understand energy's mass equivalence. People, I'll tell you something. I'll tell you something. Okay. See, those who want to go, they can go. Okay. I have no issues. है ना? Those who want to go, they can go. I have not forced you to sit over here. Those who want to study, they will study. Those who don't want to study, you can turn off your devices and then go to sleep. It's not mandatory for you all to sit. Okay. And you don't have to tell that, please end, sir, please end, it's over, khatam. No, you don't have to say it. I have prepared the content. I will teach to those who want to learn. Simple. It's very simple. It's very, very simple. Okay, then don't waste my time over here by saying end and end and end. Okay, because others want to learn and let them learn. You are not the one who's deciding who when will I finish it. Okay, now sir, according to Einstein, mass can be converted into energy and energy into mass. This relation is given by obviously this energy. So this relation is the famous E is equal to mc square. E is equal to mc square. Over here we are basically saying that energy can be converted into mass and mass also can be converted into energy. But is it is it something which I am saying something like this, that this bottle is also some mass, I can convert this into energy, this phone is also some mass, I can convert it into energy, or this cup over here, this has some mass, I can continue to with I can convert it into some energy. No, 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 it's not valid for every case. It is only valid, it is only valid, it is only valid for nuclear energy or the nuclear reactions. It is only valid for nuclear energy and nuclear reactions. It is not valid for everyone. Okay? It is not valid for everything. Okay, people? Now let's understand. Now let's understand what exactly do I mean this. Take it? Okay. See, this is the question. Very, very important question. If in a reaction, 1 AMU mass is converted into energy, then using Einstein's mass energy relationship, the amount of energy released is. The amount of energy released is. So basically they are saying, please use E is equal to mc square. E is equal to mc square. And please tell me what will be the energy that is getting converted. What will be the energy that is getting produced when you convert 1 AMU mass into energy? That is what the question is. That is what the question is. Very important derivation, people. You have to keep the end result in your mind. You have to keep the end result in your mind. Okay? Okay. So this is energy. This is mass. That is 1 AMU. 1 AMU into C square. Into C square, that is 3 into 10 ki power 8 C square. Okay? That is the speed of light. Okay? Now, I have to convert this into SI unit. So this becomes 1.656 into 10 raised to minus 27 into 3 into 10 ki power 8 ka square. This is the energy that I am getting. This is the energy that I am getting. Now, if I divide this, if I divide this, what am I getting? What am I getting? Let's divide this, people. Come on, let's divide this. So 1.656 into 10 ki power minus 27. This is 9 into 10 ki power 16. This comes out to be 1.84 into 10 raised to minus 44 into 10 raised to, I did a mistake. 1.656 into 10 raised to minus 27 into 9 into 10 ki power 16. Yes. So this comes out to be 1.4904 into 10 raised to minus 10 into 10 raised to minus 10. This is what we are getting. Okay, this is what we are getting. Okay, so this amount of joules of energy we are getting. Now I need to convert it into electron volt. I need to convert it into electron volt. So in order for it to convert it to electron volt, I divide this whole thing by 1.6 into 10 raised to minus 19 in order for me to convert it into electron volt. Okay, so what am I getting over here? 1.4904 into 10 raised to minus 10 divided by 1.6 into 10 raised to minus 19. This is what I am getting, and this comes out to be 9.315 into 10 raised to 8 electron volt. This is energy. This is energy. Now people see this. Now see this, people. Very, 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 very important. Very important. Very, very important. Now, can I write this as something like 931.5 into 10 raised to 6 electron volt? This 10 raised to 6 electron volt, can I write this as mega electron volt? Because I know 1 mega electron volt is 10 raised to 6 electron volt. So I can write that energy is basically 931.5 mega electron volt. Very, 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 very important, people. Very, very, very important. Very, very important. This you have to remember. That means if I convert 1 mu into energy, the amount of energy that we are going to get is 931.5 mega electron volt. This you have to keep in mind. This you have to keep in mind. That is the amount of energy that will get converted. Sorry, the amount of mass. Sorry, the amount of energy that we are gonna get if we convert the mass into energy. That is 1 AMU mass into energy is 931.5 mega electron volt. This you have to keep in mind. People, let's just put this 931.5 back to this equation again. So what do I get? I get 931.5 mega electron volt is basically equal to m into c square. So what I'm getting? I'm getting m is basically 931.5 mega electron volt divided by c square. Sir, we have actually we have already we know that the unit of mass is kilogram, gram, milligram and everything. What is this unit, sir? Mega electron volt divided by c square. Yes, this is a unit of mass. This is a unit of mass. Are you able to understand this? Are you able to understand this? I can convert energy into mass, and I can convert mass into energy. You have to understand this. You have to understand this. Did you all understood this? So if I convert 1 AMU into energy, the energy will be 931.5 mega electron volt. Did you all understood this? Did you all understood this? Yes or no? Now comes the most magical part. Now comes the most magical part, that is mass defect. That is mass defect. This is all feeling, people. This is all feeling. This is full feel. This is full feel of physics. No rattabazi. No mugging up. This is just feel. This is full concept I'm going to tell you. This is full concept that I'm going to tell you. Full concept that I'm going to tell you. Full concept that I'm going to tell you. Hai na? See this. People, I've already told you that the mass of an isolated proton or a neutron outside the nucleus will be greater than the mass of the proton or the neutron inside the nucleus. Yes, this is true. I'll explain it. See, this is the proof. This is the proof. The mass of the entire hydrogen atom, if you calculate it, you are getting 2.014102 AMU. This is the mass that you are getting with mass spectroscopy. Mass spectroscopy. So it is very much intuitive. So people thought, if I basically, so we know that hydrogen has one proton. Okay, so the mass of one proton is this much. Mass of one neutron is this much. One electron is this much. So if I add everything together, I should get the mass of the atom. But when I did, I got 2.016490 AMU, which is basically greater. What is this happening? What is this happening? This is called as the mass defect. The difference in masses is called as the mass defect. The mass of hydrogen atom is this much. But if you take the individual masses of every constituent, mass of proton, mass of neutron, mass of electron, and add it all together, you get this value. This value is much greater than this value. That is called as mass defect. That is called as mass defect. Are you all able to understand this? Are you all able to understand this, people? Yes or no? This is called as mass defect. So basically, can I say something like this? That is delta m or the mass defect is basically equal to, yeah, I'll tell you. Okay, I'll tell you. How many protons are there? Sir, Z number of protons are there and the mass of the proton is ZMP. Okay, sir. How many neutrons are there? How many neutrons are there? Sir, A minus Z neutrons are there and the mass of the neutron is Mn. Mass of the neutron is Mn. Mass of the neutron is Mn. Okay. This is the mass of the neutron. Okay. Plus Z number of electrons are also there. So Z into mass of the electron. Z into when less topics are remaining. Okay, less topics are remaining. This is the total mass of the individual constituents. Individual constituents minus mass of the entire atom. Minus mass of the entire atom. This is basically the mass defect. Now you all know that you can consider the mass of the electron as 0. So this term becomes 0. So I can definitely write Z into MP plus A minus Z into Mn minus mass of the atom or mass of the nuclei. Chalo, mass of the atom. Is this clear? Is this clear, people? This is the mass defect. This is the mass defect. So this is the mass of the atom by mass spectroscopy. But when you added all the constituents together, the neutrons, the electrons, the protons and everything, you got greater mass. You got a mass which is much greater than the mass of the atom. What is this happening? What is this? How is this possible? So this difference of mass is called as the mass defect. This difference of mass is called as the mass defect. Are you all able to understand this? Are you all able to understand this, people? Okay. Now let's understand why this thing is happening. Now let's understand why this thing is happening. Binding energy. Okay. Now binding energy can be understood by two different ways. It can be understood by two different ways. Okay. Let's understand this. Binding energy is basically if I have protons and neutrons over here, है ना? And if I take all the neutrons and protons and club together to form a nucleus, I form a nucleus and I also get some energy. This is the energy that is being released is called as the binding energy. Again, what I am saying that if I have some individual neutrons and protons and I take it together and I club it together to form a nucleus, it forms a nucleus and it also releases energy, and this energy is called as the binding energy. This is the first definition. What is the second definition? The second definition is basically the energy required to break this nucleus into its constituents neutrons and protons, into its constituent neutron and proton is called as the binding energy. That means the amount of energy that I have to give to this nucleus to break this nucleus apart into infinity, to separate into nucleons is called as the binding energy. Are you all able to understand this? Are you all able to understand this, people? Yes or no? Yes or no? Yes or no? Now comes the most interesting part. People. The whole mass of this separated nucleons, let me assume it to be M over here. है ना? Capital M over here. Now we all know that this mass would be greater than this nucleus. This is small mass. है ना? This capital M would be greater than this small m because of mass defect. Now you will be like, sir, what about mass conservation, sir? Where is mass conservation? Why is mass conservation not happening over here? Actually, mass conservation is happening. You know, in reality, there is actually no mass conservation which is happening. It is always energy mass conservation which is happening. I'll tell you why. See, people, this is smaller mass, this is bigger mass. So for order both of these to be equal, I have given here some energy, and this energy is basically the mass, the difference of mass which has been getting converted into energy. Did you understood? Yes or no? Did you understand this? Yes or no? This is of greater mass. है ना? This is greater mass. This is of greater mass. This has smaller mass. Where is mass conservation? Actually, there is happening. The mass conservation is actually happening, but energy mass conservation is happening. So this is greater mass, this is smaller mass. In order for me to balance this, I have given it some energy over here. And this, what is this energy? This energy is basically the difference of masses. This energy is basically the difference of masses. And this energy is basically your binding energy. And I can write this binding energy as delta m into c square. Delta m into c square. Did you all understood this? Did you all understood this? Did you all understood this, people? Did you all understood this? Yeah, mass conservation is not happening. Energy mass conservation is happening. Energy, mass is getting converted into energy. So, technically what is happening? What is this mass defect? What is this mass defect basically? Very simple, people. Very simple. Very simple. This has greater mass. This has 2.016490 AMU. This has 2.014102 AMU. Mass is not getting conserved. Why? Because some mass is getting converted into energy. If you add this mass defect, into this, you will get this. Did you understand, people? So this separated nucleons has a mass capital M. This nucleus has a mass small m. Obviously, m is greater. Obviously, mass small m is greater. Not greater. Small m is less than capital M. So for order to balance this, I have to add an energy term over here. And this is the energy that is arised from the mass defect. The mass defect, the difference of masses, gets converted into the energy. Clear? Yes or no? BE is equal to delta MC square. Now it is conserved. Now it is conserved. Now it is conserved. Now it is conserved. Because the mass over here gets converted into energy. Binding energy of a nucleus is the energy required to split into the nucleons. Binding energy. It is always positive and numerically equal to the energy equivalent of mass defect or equal to the energy liberated when it was formed. Is it absolutely clear, people? Absolutely clear. This has to be literally absolutely clear. Okay. People, so I've already told you, binding energy is mass defect into c square, delta m into c square. Okay, a nucleus has mass represented by so and so. Okay. But the binding energy, we have to calculate the binding energy, people. The binding energy we have to calculate. So what is binding energy, people? Binding energy is delta m into c square. This is the binding energy. So first find out the mass defect. Sir, what is the mass defect? Sir, mass defect is basically the difference of mass between the separated nucleons and the complete nucleus. Are hi Anna. So see this, delta m, mass of proton plus mass of neutron minus the mass of the atom or the mass of the nucleus into c square is the binding energy. Isn't this the definition, people? Isn't this the definition? This is the wrong only. Because it should not be z over here, no, it should be a minus z. So this is wrong. This is the completely wrong. This is again wrong. They are minusing mass of atom with the separated nucleons. Wrong. Clear, people. Is it absolutely 100% clear? 100% clear. Yes or no? If you have understood this, can I have some fire in the chats? Can I have some fire in the chats, people? Yes or no? Chalo. Now, the mass of the proton, okay, this is very good. This is very good, people. See this. Good question. 2003 NEET. The mass of the proton is this much. And that of a neutron is this much. The binding energy of helium will be how much? The binding energy of helium will be how much? That means, people, in order for me to make the nucleus of helium, what I'm doing basically, I'm taking two protons and two neutrons, and I'm combining it together. To form a helium nuclei. And also some binding energy. Hai na? And now it's conserved because this side the mass is more, this side the mass is less, but it is still conserved because the remaining mass gets converted into the binding energy, or that is basically the mass defect. Okay, now we need to find the binding energy. Binding energy is basically delta m into c square. This is basically your binding energy. This is basically your binding energy. Hi Anna. Okay. What is delta m? Can I write delta m as number of protons is number of protons is 2. Number of protons is 2. What is the mass of proton? 1.0073 plus mass of neutron. 2 neutrons are there. So 2 into 1.0087 mass of neutron. Okay. Minus the mass of the helium nucleus is 4.0015. 4.0015 into c square. Yes or no, people? Yes. I know who all are there. Now, people, if you minus this, if you minus this, people, what you're gonna get? You're gonna get 0.03 as the mass defect into c square. 0.03. Ruko. 0.03 AMU into c square. Now you don't have to convert AMU into joules again, AMU into kilograms again, then multiply it by c square. No, you don't have to do it. Simply, you know na, that 1 AMU is 931.5 mega electron volt divided by c square. You already know this relation. So just multiply the 0.03 by 931.5. That's it. So this is 0.03 into 931.5 mega electron volt. This comes out to be 28.4 mega electron volt. Option C. Is this clear, people? Is this clear? Understood what did I do over here? Is this clear what did I do over here? Yes or no? Absolutely understood, people. Yes or no? Okay. So binding energy. What is binding energy? Mass of the separated nucleons. So 2 into protons plus 2 into neutrons minus the mass of the atom or the nuclei into c square. Now I don't need to find out this because I already know 1 AMU is 931.5 mega electron volt divided by c square. So I just substituted 931.5 over here. That's it. Khatam? Crystal clear? Kya baat hai? Binding energy per nucleon. Okay. Okay, people. So no. Binding energy per nucleon or binding energy divided by A. है ना? This is the graph that you see in your NCERT textbooks. Okay. Now you don't have to basically mug up this graph, but you need to have some certain idea of this graph. This is binding energy per A nucleon, and this is mass number over here. है ना? This is mass number over here. Okay. You just need to have a small idea about how this graph looks. This graph is something like this. This is the only idea that you should have. है ना? Yeah, more 30 minutes, है ना? More 30-35 minutes and then it will be done. Okay, more 30-35 minutes and then it will be done. Okay, people? More 30-35 minutes and then it will be done. So over here you get helium and over here you get carbon. And the most stable nuclei is iron over here, according to your NCERT. Now why I am saying this? Because people, the binding energy per nucleon is directly proportional to the stability. Of the nuclei. Binding energy per nucleon is directly proportional to the stability of the nuclei. Are you all able to understand this, people? Yes. But keep one thing in mind. This does not mean binding energy is directly proportional to the stability of the nuclei. No. This is wrong. Wrong. binding energy is not directly proportional to stability. No, no, no. Binding energy per nucleon is directly proportional to stability of nuclei. I'm going to prove this by help of a question as well. Okay. Now, why did I say that according to NCERT FE that iron is the most stable nuclei? Why? Because it's actually a mistake. If you actually calculate the binding energy per nucleon, the most stable nuclei is actually nickel, for nickel. Okay, but okay, we have to follow the NCERT and everything. So iron is the most stable because it has the highest number of binding energy per nucleon. Okay, people. Okay. So over here we are able to find greater the binding energy per nucleon, the more stable the nucleus. It is maximum for isotope of iron 26 Fe and it is 8.8 mega electron volt nucleon. It is the most stable nucleus. Okay, people. Chalo, let us understand. Okay. Now this is the question. Which center? Bangalore itself. Now this is the question by which I will be proving it to you that how much, why binding energy is not directly proportional to stability and why binding energy per nucleon is directly proportional to stability. Okay. So see this. What is the question? The question over says, if the total binding energies of hydrogen, helium, iron and uranium are so and so in mega electron volt, then identify the most stable nucleus out of the following. Now, if I say from this thing that binding energy is directly proportional to stability, hai na? So you will say, sir, 1768 mega electron volt binding energy for uranium. So that means uranium is the most stable. Uranium is the most stable. But that is not true. That is not true because stability is directly proportional to binding energy per nucleon, binding energy divided by A. So let us try to find out the binding energy per nucleon for each of the things. For hydrogen it will be 2.22, that is the binding energy per nucleon. How many nucleons are there? 2 nucleons are there. Okay. Next, for helium, it is 28.3 divided by 4. Okay, sir. Next, it is 492 divided by 56. Next, it is 1768 divided by 235. Yes. Yes or no? Now, if you calculate 2.22 divided by 2, this comes out to be 1.11, and 28.3 divided by 4, this comes out to be 7.07, and 492 divided by 56, this comes out to be 8.78, and 1768 divided by 235, this comes out to be 7.52. So see this. The binding energy per nucleon is a maximum for iron or for iron over here. That is the reason it is the most stable. Clear, people? Is this clear? Yes. Is this clear? Yes or no? Is this clear? Yes or no? Yes. Yes, Krupshika. Okay. Now, what about binding energy of a hydrogen nuclei? What about binding energy of a hydrogen nuclei? What is binding energy, people? What is binding energy? Binding energy, binding energy is basically the energy required, hai na, to basically pull out all of the nucleons from the nucleus till infinity. That is basically binding energy. But for a hydrogen nuclei, what does an hydrogen nuclei consist of? Hydrogen nuclei, it consists of just one proton and no neutron. No energy is required. So the binding energy is zero for a hydrogen nuclei. And I'm talking about only protium over here. I'm talking about just protium over here. And it's already a nuclei. It's already an isolated proton. है ना? This is already, if I talk about hydrogen nuclei, this is already an isolated proton. No, this is already an isolated proton. No energy is required. It's already an isolated proton. So binding energy of an hydrogen nuclei is zero. Okay. Okay, people. Binding energy of an hydrogen nuclei is zero because it's already isolated. You don't need to give energy for making it isolated. It's already isolated. Yes. Okay. Yes. One question over here, people. One question over here. What is it? The mass of proton, neutron, helium, nucleus are respectively so and so. the binding energy of the helium nucleus will be how much? I think this we have solved, no? Arey yaar, this we have solved it. The binding energy we have solved it. है ना? We have solved this question. है ना? Crew Miksha. Okay, okay, Crew Miksha. है ना? We have already solved this. This is 28.4. I already remember the answer. Okay, let's move on to Q value. Okay, let's move on to Q value. Very much less is left, people. Okay, very much less is left. Okay, very much less is left. Q value. Okay, chalo. See this, people. This is one reaction that I've written over here. One nuclear reaction. Okay, one nuclear reaction. One nuclear reaction, I've kept it over here. Now, if you see over here, people, if you calculate the mass of the hydrogen over here and nitrogen over here, this is 2, this is 4. If you add, it comes out to be 16.017. And the product side, it comes out to be 16.02602. है ना? There is a difference. And what is this difference? Obviously, you are able to find that this has much more greater mass, this has less mass. So obviously, what has happened? This difference of mass has got converted into energy, and this energy is basically Q. Are you all able to understand? Are you all able to understand, people? This mass, the reactant mass over here is 16.01. The product over here is 16.002. You are able to understand that the initial mass is much greater than the final mass. What is this? Where is this difference going? This difference is going to the energy. It has got converted into energy, and that is plus Q over here. That is plus Q over here. So basically, can I basically write? Just ignore the scammer. Just ignore the scammer. Okay, that is what we do. So this Q value can be written as M initial minus M final. The mass of the initial, that is mass of reactant minus mass of product into C square, and which is also equal to binding energy final minus binding energy initial. Or we can also say binding energy of the products minus binding energy of the reactant. Okay, people? This you have to keep in mind. This is reactant minus product into C square. This is just product minus reactant, no C square over here. This is R minus P, this is P minus R. Here we have C square, here we don't have C square. Just keep in mind. Okay, people? Okay? Okay. Okay, can we? Okay, let's do this. Let's do this, people. Okay, what is the difference between binding energy and Q? I will tell. Don't worry. I'll tell, don't worry. Okay? I'll tell. Sorry. Okay, see this. Binding energy is basically the energy to destroy or to basically separate out the nucleons from the nucleus. Okay? What is this Q value? Q value again is actually the same thing. No difference over there. But additionally, this energy is also used to give kinetic energy to the products as well. Kinetic energy to the products as well. Are you able to understand? Binding energy is just destroying the nucleus into its nucleons. Okay, are you all able to understand? But Q additionally also gives kinetic energy to the products as well. Okay. Okay, let's solve this, people. Again, it's a very important question, people. It's a very important question. Very important question, people. Very important. The binding energy per nucleon of lithium and helium are given respectively. In the nuclear reaction, the value of energy Q released is what? We already know Q is basically mass of initial, mass of final into C square, or binding energy of the products minus binding energy of the products minus binding energy of the reactants. This is what we know. This is what we know. Yes. Now, this is not given, so we have to calculate binding energy. People, you have to understand, you have been given binding energy per nucleon. You are not given binding energy, you have given binding energy per nucleon. So see this, what will be binding energy of the products? I have two helium nucleus over here. Okay, I have two helium nucleus over here. So 2, है ना? 2 What is the binding energy per nucleon for one helium? It is 7.06. So 7.06. But I also have to multiply it by 4 over here. Why? Because this is binding energy per nucleon. In the formula, I need only binding energy, not binding energy per nucleon. I need binding energy. So I have to multiply it by the number of nucleons it has to get the binding energy. So 2, why did I multiply 2? Because 2 helium nuclei are there. 7.06 is the binding energy per nucleon. For how many nucleons? For 4 nucleons. So this is the total binding energy of the products. Okay. This is Q. Minus binding energy of the reactant. This is hydrogen nuclei. Binding energy is 0 over here. This is 0. Now what about this? It has 7 nucleons and binding energy per nucleon is 5.60 and 5.60. This is basically your Q value. This is basically your Q value. Did you understood it, people? Did you understand it, people? So this comes out to be 17.28 mega electron volt, and that is 17.3 for you. Now you have to keep in mind whether in question they have asked binding energy per nucleon or binding energy. If it was binding energy, then you can directly subtract it. But over here it is binding energy per nucleon. That is the reason I multiplied it by the number of nucleons also. Clear? Clear? Okay. Now people, nuclear fission. Nuclear fission. Now very interesting part is coming. Okay, very interesting part. Very interesting part. Very interesting. Okay, very interesting. I'm going to sail through it. And then we're going to complete it. Okay, and then we're going to complete it. Nuclear fission. Okay, nuclear fission. Okay. See what happens in nuclear fission. What happens in nuclear fission? See this, people. I'll just explain you with the help of this curve. This curve. Hai na? See this, people. All of the, if you notice, Fe is the most stable nuclei of over here because binding energy per nucleon is the maximum over here. Hai na? All of the lighter nuclei wants to combine with each other so that they can reach stability. They want to combine, and combination is called as fusion. All of the heavier nuclei, they want to break apart into daughter nuclei so that they can attain stability. That is called as fission. Meaning, if there is a nuclei of mass number 200, it will break into 120 and 80. It will break into mass number 120 and 80. So that 80 will be over here, 120 will be over here. So they have reached over here, they have attained more stability. Are you all able to understand this? So fusion, lighter nuclei fuse together to attain stability, and fission, heavier nuclei break apart into daughter nuclei to attain stability. That's it. Everyone wants to attain stability. That is the whole motto of this chapter. Okay. So nuclear fission, what is happening? Simple. This is very much simple. Splitting of heavy nuclei into 2 or more lighter nuclei when struck by a neutron. So obviously, it is very much obvious that I have to initiate this reaction. It cannot break apart on its own. I have to initiate the reaction. And this initiation is done by a neutron. What happens is, a neutron, a fast moving neutron, it strikes a heavier nuclei. Uranium over here. Hai na? It breaks apart into barium and krypton. See, barium is 144, this is 89. It has broken into lighter nuclei. It has attained more stability. And again, because of this breaking apart, 3 more neutrons are released. And then these 3 neutrons then again strike a uranium. So a chain reaction is attained over here. See, something like this. This is one neutron, strikes a uranium, breaks into barium and krypton, releases 3 neutrons, and these 3 neutrons again go strike uranium. So this chain reaction keeps on happening. And this is what exactly happens in an atom bomb. This is exactly what happens in an atom bomb. Yes or no? Okay. This is exactly what happens in an atom bomb. So this is what exactly is happening. Hai na? Fusion, lighter nuclei fuse together. Fission, heavier nuclei break apart into smaller daughter nuclei to attain the stability. Okay. Yes. Clear? Okay, got it. Let's go. Okay, this is something that I will do it later. Yeah, now coming back to nuclear fusion. Yes, it is a nuclear reaction. Nuclear fusion. Yes, Oppenheimer. Yes, exactly. The fuel of the sun. The fuel of sun. है ना? So which reaction happens inside the sun? Nuclear fusion. Okay, nuclear fusion. It's a very good photo, है ना? Nuclear fusion. So what happens in fusion? Deuterium and tritium, they come together, they release energy, they form helium. Heavier nuclei. Okay, heavier nuclei. And a neutron comes out. Simple. So basically over here, lighter nuclei fuse together. Lighter nuclei fuse together to form helium. Then helium and lithium, they form nitrogen, and again and so on and so on and so on and so forth. Are you able to understand this? So lighter nuclei fuse together to form much more stable nuclei. Clear? Okay. Now the question, the main question: hydrogen bomb versus atomic bomb. है ना? So in atomic bomb, you have to understand, atomic bomb, nuclear fission takes place. Nuclear fission takes place. है ना? So a neutron comes and breaks the uranium into barium and krypton. Then again the 3 neutrons, they go and break the other uranium. This chain reaction goes on. But hydrogen bomb, nuclear fusion takes place. Nuclear fusion takes place. In hydrogen bomb, nuclear fusion takes place. And which is more efficient? Nuclear fusion is much more efficient. More amount of energy is there in nuclear fusion. So that is the reason hydrogen bomb is much more powerful. Actually, what happens in a hydrogen bomb is that there are 2 nuclear fissions happening. First 2 nuclear fission happens, and due to this nuclear fission, this nuclear fusion is getting initiated. Okay, people, you must have seen in Oppenheimer or something. Okay, so in a hydrogen bomb, first nuclear fission happens, and due to this nuclear fusion takes place, and this nuclear fusion is very powerful. Okay, people. Okay. Now let's start nuclear reactor, and then we're gonna end it very soon. Only alpha, beta, gamma decay, and then end. Okay, people. This is I'm just gonna go through what happens in your nuclear reactor. Okay. So in nuclear reactor, you have to understand, obviously there has to be a nuclear fuel. There are 2 types of nuclear fuel that you can use. One is uranium and the other one is plutonium. Okay. Now plutonium is not naturally available. Okay. That is the reason we use uranium. That is exactly what is written over here. But in theory wise, plutonium is the best, but it's not available in nature. That is the reason we use uranium more. Okay. Moderator. What is a moderator? Okay. Now when you know, see, all of the neutrons that are getting produced in the fission and the fusion reactions, they are all fast moving neutrons. Now obviously, I'll take one example. है ना? I'll take one example. If a ball is coming at you at a higher speed, you're not able to catch it. But if the ball is coming at a very lower speed, you are able to catch it. Same happens with neutrons. No, radioactivity is not deleted, people. Radioactivity is not deleted. For example, in JEE as well, radioactivity was deleted from the syllabus, but still questions came through it. In NEET also it happened. Radioactivity is not deleted, people. It is not deleted. है ना? So rolling motion is also deleted, but still rolling motion came. है ना? You can't trust NTA. है ना? It's better to study one more extra topic than not getting a seat in medical college. So what does a moderator do? The moderator's function is to slow down the neutrons so that you can catch the neutrons. Are you able to understand this? And the most commonly used moderator is heavy water, that is D2O. You have all studied it in chemistry. D2O, deuterium water. Yes or no? Okay. Then control rods. Control rods are made up of boron and cadmium. They help to capture the slow neutrons. So moderator, it slows down the neutrons, and after the neutrons have been slowed down, the control rods capture the slow neutrons. Are you able to understand this? Okay. And the coolant. which is basically obviously high amount of energy is released, the temperature goes on increasing and increasing, and if the temperature is not controlled, a nuclear blast will take place. A nuclear blast will take place, like Chernobyl disaster. है? And for cooling the nuclear reactor down, we generally use water. We generally use water, normal water. Okay, people. So this is आपका nuclear reactor. Now the last topic, people, that is radioactivity. The last topic, that is radioactivity. We are just gonna understand each and everything in detail, but yet skim over it in a very fast manner. Okay, yet skim over it in a very fast manner. Last topic, and then we are done. Last topic, and then we are done. This marathon of modern physics is complete. This marathon of modern physics is complete. Okay. Okay. See, radioactivity. So spontaneous emissions of radiations from the nucleus is known as radioactivity. And why does radioactivity takes place? Because the atom or the element wants to attain stability. That is the reason it is showing radioactivity. It is unstable. It wants to become stable. That is the reason it's showing radioactivity. And these substances showing this property are called as radioactive substances. Clear? Only unstable nuclei exhibit this property. Obviously, why would stable nuclei exhibit this property? Because they're already stable. Why would they? Why would they? Okay. A particular nuclide or an element can radiate only a particular type of radiation at a time. That is, at a one particular time, it can only show alpha decay, or it can show beta decay, or it can show gamma decay. At one particular time, it cannot show alpha, beta and gamma together, never. And depending upon the situation, it can show alpha, beta or gamma, but never together, one at a time. This phenomenon was discovered by Becquerel and everything. Okay, these are scientists. This is Marie Curie and this is Becquerel for you. Okay. Now, alpha decay. Let's understand alpha decay over here. Okay, people, alpha decay. What happens in an alpha decay? See this, people. Alpha decay is very easy to understand. Very, very easy to understand. This is the parent nuclei. In alpha decay, what happens? A helium nucleus gets eliminated. Not eliminated, the helium nucleus gets ejected. What is a helium nucleus? A helium nucleus is something like this is 4 and this is 2. And obviously, you had to conserve the charge and the mass. There is always a daughter nuclei which is going to be ejected. Now, how to calculate this? It is very simple. This has to be A minus 4. This has to be Z minus 2 because charge and the mass has to be conserved. See this? This is A and Z. This is X. Helium nuclei ejected out. So obviously the mass number of Y has to be A minus 4. See, A minus 4 plus 4 is A. Z minus 2 plus 2 is Z. Did you understood? Did you understood this? Yes or no? Did you understood this reaction? Did you understood this reaction? Did you understood this reaction? Simple. This is alpha decay. This is alpha decay, and alpha decay is generally shown by the heavier members. Heavier members. Okay. Okay, heavier members. Okay. Now, if I want to calculate the Q value of this reaction, Q value. See, I've already told you what is Q value. I've already told you it is mass of the reactant minus mass of the product into C, or is equal to binding product minus binding energy reactant. So over here, where is it? Can I write basically the Q value is basically going to be mass of X, that is mass of the reactant minus mass of helium plus mass of Y into C square. This is the Q value. Simple. This is the Q value. Simple. Let's move ahead. Beta decay. What is beta decay? Beta decay is magic. Sir, what is magic, sir? I'll tell you. I'll explain it. Okay? I'll explain it. Beta decay is Magic. Just give me a second, guys. Just give me a second, okay? Okay, just give me a second. Just give me a second. Yeah. What is beta decay? Beta decay is basically a process in which a neutron gets converted into a proton. Huh? Neutron gets converted into proton? Huh? How is this possible? Neutron gets converted into proton. Yes. And neutron gets converted into a proton, and as we have to balance the charge, see, because over here it's a neutral particle. That is the reason an electron also comes out. See, proton plus electron, it's a neutral molecule, no? So neutron gets converted into a proton, and an electron is ejected, and along with an electron, and anti-neutrino is also injected. This is anti-neutrino. This is anti-neutrino. This is basically an antiparticle. You don't have to go into the structural understanding of it. You just need to understand that whenever a neutron is getting converted into proton, an electron is also getting ejected for conserving the charge, and also along with the electron, an anti-neutrino gets ejected out. Simple. Now people, do you want to understand? How is neutron getting converted into proton? I brought a good animation for you. Not a good animation, basically it's a very good way of understanding. Do you want to see it? Yes or no? Then you will be able to understand why neutron is getting converted into proton. Yes or no? Do you want to see? Yes or no? If you say yes, then only I'll show. If you say yes, then only I'll show. Tell me. Yes, do you want to? Okay, chalo. See this, I brought. See, what happens is, see, first of all, what keeps a nucleus stable? Sir, what keeps a nucleus stable? So, sir, we have a bunch of protons over here. So, these are not stable because they will repel each other and the nucleus will not form. So, what will happen? I just throw a bunch of neutrons over here. Chalo. I've just thrown a bunch of neutrons, and neutrons act as a glue, and because of that, a stable nuclei is formed. So I have 8 protons and 8 neutrons, so I have a stable nuclei over here. Yes or no? Yes. So that means, does it mean, if I throw more neutrons, it will be more stable? Does it mean that? No, it does not mean that. Does it mean if I throw more protons, only 2 protons and neutrons, if I throw more neutrons, will it be more stable? No, it will not be stable. It will be super unstable. Helium-16 does not exist. It does not exist. Huh? We just came to know that neutrons over here are the ones who act as glue inside the nucleus because of the nuclear forces. That is the reason 1608 exists. But helium-16 does not exist. It is super unstable. What is happening? See, people, as we all know, electrons, how are they always there? In energy levels, right? In energy, different energy levels, and no two electrons can have the same quantum numbers. No two electrons can have the same quantum numbers. Yes, you have studied in chemistry, है ना? So this electron has upper spin, this electron has lower spin. A third electron cannot accommodate over here. Otherwise, these 2 electrons will have the same spin. So this third electron has to accommodate into the higher energy level. Okay. And that is how you fill the electrons also. Hai na? In the same way, people, now let us look why this is not possible. You know, like the electrons also, The nucleus also has energy levels. The nucleus also has energy levels. So first you fill the 2 protons over here. So the next 2 protons will, so the first 2 protons are over here, and the next 14 neutrons should it be filled over here? No, it has to be filled in different energy levels, because there are two different there are two different subatomic particles. There are two different subatomic particles. So what I do is I start filling the neutrons over here. I start filling the neutrons over here. I start filling the neutrons over here. Okay, and now I have filled it. Now I have filled it. Okay. Now people basically, in nature, it always tries to attain stability. Now just see over here. This is 2 protons over here, and all of these neutrons have attained higher energy levels over here. Neutron is like, arey yaar, I also want lower energy levels. I also want stability. So what to do? Simple. What it does? The neutrons gets converted into protons, and then these protons can accommodate this lower energy levels. Are you all able to understand this, people? Are you all able to understand this, people? That why the neutron is getting converted into proton, so that it can attain the lower energy levels and attain stability. And this is exactly what is beta decay. And this is exactly what is called as beta decay. Clear? Yes or no? Clear? Yes or no? Clear? Yes or no? Now did you understand? Now did you understand, people? Yes. Now did you understand? Okay. So over here you have to understand, in beta decay, a neutron gets converted into proton. For charge conservation, an electron also gets ejected, and an anti-neutrino also gets ejected out. Okay. So now I will be basically making you understand some representations as well. See, a proton can be written as, this is one mass and it has one charge. It has one mass and one charge. Neutron is, it has mass 1 but zero charge. This is neutron. What about electron, sir? Sir, electron is E with charge, with mass 0 but charge -1. Are you all able to understand this? This is the representation I'm showing you. This is proton. This is neutron. And this is electron. Okay? You can also write this electron as beta -1 and 0. Beta -1 and 0. Okay. So in beta minus decay, what happens? In beta minus decay, neutron gets converted into proton. For charge conservation, electron also gets ejected out, and an anti-neutrino also gets ejected out. Simple. So see what is happening. No problem. We are coming to the end. So this is AXZ. This is the element. It is undergoing beta minus decay. है ना? So obviously one electron is coming out. What is one electron? -1 charge and 0 mass. है ना? -1 charge and 0 mass. And an anti-neutrino also. Now obviously a daughter nuclei also will get ejected out. What will be the daughter nuclei? Simple. You just have to conserve the charge. Now this is Z over here. It is -1 over here. So shouldn't it be Z plus 1 over here? See, Z plus 1 minus 1 is Z. Yes or no? Yes, sir. So this is A over here. This is 0 over here. So obviously this will be A over here. Clear, people? Clear? Yes. Very good. Now what happens in beta plus decay? In beta plus, the proton gets converted into neutron. Now for charge conservation, a positron comes out. Positron is not a proton. It's an antiparticle. Of an electron. It has the same mass of electron but plus charge. And along with it, neutrino also gets ejected out. This is neutrino. Also gets ejected out. neutrino. Okay, clear? So what happens over here is same. This is AXZ. Beta plus decay is happening. Beta plus decay is happening. So E or beta 0 plus 1, a beta particle is ejected plus beta particle, or a positron is emitted out. Positron is emitted out along with neutrino and plus a daughter nuclei. What will be the daughter nuclei? So this is Z over here and this is plus 1 over here. So this should be Z minus 1. This is A, this is 0. So obviously this has to be A over here. Clear? The reaction is clear over here. The last, gamma decay. Gamma decay. Now people, we have already learned that the, yes, I will speed up a little. This is the last topic, last topic people. Okay, last topic. We have already learned that in gamma decay, we have already learned in atoms that electrons can get excited and can attain higher energy levels. Haven't we studied it? Yes, we have studied it. So in the same way, the nucleons in the nucleus also can attain energy and go into excited states. Now what happens is, after an alpha decay or a beta decay, the nucleus itself gets excited. Arey haan, hai? Yes. So over here, the nucleus XAZ, this gets excited after what? This gets excited after an alpha decay or a beta decay. See, similar to an atom, the nucleus also has certain energy levels and nucleons occupy them. After alpha decay or beta decay, daughter nuclei may be in excited state and return to ground state by emitting photons of higher energy. So basically what is happening? What is happening? This is an excited nuclei. After alpha decay or a beta decay, the nucleus is in excited state. It wants to come down. It wants to attain stability. So what happens is, it gets converted into the ground state nuclei. Okay, it gets converted into A and Z, but also a gamma particle is also emitted out. Yes, what is gamma particle? Gamma particle is nothing, people. Gamma particle is just high energy photons. It is high energy photons. And it is the only reaction in which you can see the A and the Z and the A and the Z is not changing. It is the only reaction. So basically, what is gamma decay? Gamma decay is basically after the alpha decay or the beta decay, the nuclei gets into an excited state. And this nuclei wants to come back to the ground state. So in order for it to come back to the ground state, it emits a gamma particle, which is basically high energy photons, and this energy is in the form of mega electron volt. So this star over here or this asterisk over here symbolizes excited state of nuclei. Sir, what does positron do? So basically, people, you have to understand in this world, there are particles and there are antiparticles. For every particle, there is an antiparticle. So electron is the particle, positron is the antiparticle of electron. Now, right now in this world, there is no antiparticles. Why? Because antiparticle and particle, when they mix up together, they form energy. They get destroyed. They form energy. So in reality, right now there is only particle. But you have to understand, for every particle, there is an antiparticle. And in a nuclear reaction, for a very small amount of time, that is for 10⁻⁷ seconds or 10⁻⁸ seconds, the antiparticle is formed and it gets destroyed. So the antiparticle of an electron is positron. The antiparticle of a neutrino is antineutrino. Did you understand? Yes. Okay, people. Can we just solve 3 more questions, people? Just 3 more questions and then we are done. Okay, just 3 more questions and then we are done. For the given reaction, the particle X is what? So C11.6 plus C11.6 gives B11.5 plus beta particle. Matlab positron. It is positron. This is positron. Positron plus X. Obviously, we just have to balance the charge and everything. See, this is 11, this is 11, this is 0. So that means this has to be 0. This has to be 0. है ना? This has to be 0. Semiconductors, it's a different chapter. 6. So this is 5 plus 1, 6. It's already balanced. It's already balanced. It's already balanced. That means this is also 0. Hey, what is this, sir? Arey, obviously, this is beta decay, no? This is beta plus decay. So obviously a neutrino. This is a neutrino. Neutrino, charge 0. Not anti-neutrino. No. See this. This is very important. This is very important. Very important. Very important. See. अरे यार किधर गया? Very important, people. You have to understand this. See, in beta minus decay, an electron is emitted and an anti-neutrino is emitted. Electron, anti-neutrino. But for beta plus decay, you have to understand a positron and a neutrino is emitted. Positron and neutron is emitted. Did you all understood this? Did you all understood this? Yes. Now this over here. See, this is a nuclear fission taking place. Uranium is bombarded with 1 neutron. Barium is formed along with some element, and 3 neutrons are formed. This is what nuclear fission reaction. So see, urium 235 92 plus neutron gives barium 144 and 56 plus something and 3 neutrons, are also formed. है ना? तो बस कुछ नहीं, charge and mass conserved, that's it. Over here it is 236. See, 235 plus 1, 236. Over here it is 236. Over here it is 144 plus 3 because 3 neutrons are there. 144 plus 3, 147. Over here it is 147. So obviously the extra mass number should be what? This is 16, this is 13, this is 1, this is 0, this is 9, and this is 9. एक मिनट. This is 236 and this is 147, right? 147. 16 and 12. Okay, huh? So this is 9 and this becomes 12, this becomes 1, this is 89. So this has to be some 89 something, 89. And over here 92 plus 0, this is 92 and this is 56 over here. So 92 minus 56. So 36 over here. So 36. 89, 36. 89, 36, that is krypton. Arey, 89, 36 krypton. Yes, I itself said the answer because nuclear fission, no? I already know barium and krypton. Yes. Last question of the day, people. Last question of the day. Last question of the day. Last question of the day. A radioactive element emits 1 alpha particle and 1 beta particle, then mass number of the daughter new element is. So I have a radioactive element that is A or Z. Alpha particle takes place. What is alpha particle? Helium nuclei. This is 4, 2. है ना? Then the daughter nuclei will be what? It will be what? It should be A minus 4 and Z minus 2. This is the daughter nuclei. Then this daughter nuclei undergoes beta minus decay. So if the decay is not there, you have to assume it to be beta minus decay. So what is beta minus decay? An electron gets emitted out. है ना? An electron gets emitted out. That is what is happening. है ना? Electron gets emitted out. So electron is this is minus 1 and this is 0. And obviously this changes to some D or something. This changes to some D or something and along with some anti-neutrino. है ना? So an electron is getting ejected. So this becomes A minus 4 because see, A minus 4 plus 0 is A minus 4. And this will be how much? This will be how much? This has to be Z minus 1 because see, Z minus 1 gives us Z minus 2. Yes. So the mass number of the daughter nuclei is A minus 4, that is decreased by 4. Decreased by 4. People, this is the Telegram channel that you can join. You will get the class notes over here. And people, and also people, if you want to if you want to solve the NEET PYQs, if you want to solve the NEET PYQs of dual nature, atoms, nuclei, you can all find it on NEET Alchemy by Unacademy. I've solved it everything. So dual nature, atoms, nuclei, ray optics, kinematics, electric charges and fields, I've solved it everything. You can all visit this and solve it. Okay, people. And for the DPPs and everything, people, I've already told you there are a lot of questions. See this. There are a lot of questions that I've given you over here. I have marked it. This is your DPP. This is your DPP. This is your DPP. The DPP is included inside the PDF itself. For every chapter, after every chapter, I have given you DPP. After every chapter, I have given you extra questions. Okay, you can solve it from here. Okay. Yes, people. Yes, it is in English. It is in English. Okay. So that's it, people. So this is, yes, NCERT reading is compulsory. You should read NCERT for all these chapters once. You should read this NCERT. Yes. Okay. No, this is sufficient. This is sufficient. Okay. This is sufficient. You can just practice this and this is sufficient. Yes, they are in English only. So people, this is Jonathan Matthew signing off from Unacademy NEET English. We'll meet with one more we'll meet with one more marathon, and I think it's going to be semiconductors. Till then, take care, study well. Thank you so much. And do comment what all chapters do you need inside the comments, and do comment that how did you like the chapters and everything. Thank you so much. Take care. Bye bye. Love you all. Sayonara. Bye bye. Okay? Chalo bye.